Technology that makes work and life easier. We have mastered the fundamentals and cover all products that communicate with wireless technology or depend on it. Where communication implies responsibility and values, it requires special protection. Information also means reducing uncertainty, radio monitoring and radio location, secure communications, broadcast and media, and test and measurement. That is our world. For almost a century, we've been helping to shape the technology-driven universe we live in. We were there at the very beginning, set milestones, and drive the developments of our time. We have always been and will continue to be an independent company. Development, production, and worldwide service under one name. We create solutions. We are Roda and Schwartz.
Good morning, ladies and gentlemen. I'm Ardita Septiani. I'm honored to be here to become your MC for today and tomorrow. We are delighted to welcome you to the 11th International Conference on Radar, Antenna, Microwave, Electronics, and Telecommunications, or ICRAMET 2022. This year's theme is Emerging Science and Industrial Innovations in Electronics and Telecommunications. The ICRAMET 2022 lasts for 2 days, covering 4 keynote talks, 4 patron talks, and 50 oral presentations from 7 conference tracks. There are remote sensing and radar system, antenna devices and techniques, radio frequency and microwave theory and devices, electronic materials, devices, components, and circuits, wireless and wired communications, signal and image processing techniques, control system, robotics, and mechatronics. This conference is an opportunity for us to explore the exciting new developments in both electronics and telecommunication. We are fortunate to have some of the experts in the field here to share their knowledge and insights on emerging technologies on electronic and telecommunications. I hope that ICRAMET 2022 will provide a great opportunity for prospective participants to share their recent theoretical advances, research findings, and also novel technology in the electronics and telecommunication field. It is my pleasure to introduce to you all our very special guests of honors. From the National Research and Innovation Agency, or BRIN Indonesia, we are delighted to have them here with us today. Head of Research Organization for Electronics and Informatics, Dr. Budi Prawara. Head of Research Center for Telecommunication, Dr. Nasrullah Armi. Head of Research Center for Electronics, Dr. Yusuf Nurwi Jayanto. Head of Research Center for Computing, Dr. Rifki Sadikin. Head of Research Center for Smart Mechatronics, Dr. Yanuandri Putrasari. Head of Research Center for Data and Information Sciences, Dr. Esa Prakasa. Head of Research Center for Artificial Intelligence and Cybersecurity, Dr. Anto Satrio Nugroho. Also from our technical co-sponsor, Dr. Wahyudi Hasbi as the Chair of IEEE Indonesia section. Our keynote speakers, Insinyur Renus Andor Maulana Sijabat from PT Line Industri Indonesia, Professor Thomas T. Antopoulos from King Abdullah University of Science and Technology, Saudi Arabia, Professor Hu Junin from the University of Manchester, United Kingdom, Professor Goib Wiranto from National Research and Innovation Agency or BRIN Indonesia. We are also welcome our esteemed patrons, Mr. Kwek Chiao and Mr. Firdaus Gutri from Radian Swartz, Mr. Jian Waitan and Mr. Ivan Pati from Mitra Sistematika Global and Kisa Technologies, Mr. Steve Fries, Mr. Gumbira, and Ms. Alistirta from Andritsu and Unitronic Jaya, and Mr. Jamie V. Confido from Indonesia Telecommunication and Digital Research Institute or ITTRI. As well, Mr. Mas Huri Wahab from PT Radar Telekomunikasi Indonesia. As well, I would like to welcome all presenters and participants. Before commencing our opening ceremony, I would like to provide you with the speakers we have this morning. First, we will hear an opening remark from Dr. Yana Tariana as the chair of ICRAMET 2022. Next, an opening remark from Dr. Nasrullah Armi as the head of Research Center for Telecommunication, National Research and Innovation Agency, or BRIN Indonesia, followed by a remark from the representative of our co-technical sponsor, Dr. Wahyudi Hasbi, as the chair of IEEE Indonesian section. Finally, Dr. Budi Prawara will officially open ICRAMET 2022. Before we proceed to our first agenda, let us hear Indonesia's national anthem, Indonesia Raya, to pay homage to all soldiers and civilians who fought for Indonesian independence. Now we are hearing the first remark from the chair of the 2022 Conference on Radar Antenna Microwave Electronics and Telecommunications. Please welcome Dr. Yana Tariana.
Assalamualaikum warahmatullahi wabarakatuh. Your Excellencies, Head of Research Organization for Electronics and Informatics, Mr. Prawara, Head of Research Center for Telecommunication, National Research and Innovation Agency BRIN Indonesia, Mr. Nasrullah, distinguished Head of IEEE Indonesia section, keynote speakers, presenters, participants, sponsors, ladies and gentlemen. On behalf of the organizing committees, it is a great pleasure and honorable for me to welcome you to the annual International Conference on Radar, Antenna, Microwave, Electronics, and Telecommunication, which is carried out regularly by Research Center for Telecommunication. This conference will be held virtually for 2 days because, as you know, we still face the COVID-19 pandemic situation, so we cannot see each other directly. Ladies and gentlemen, under the term of the conference, Emerging Science and Industrial Innovation in Electronic and Telecommunication, we aim to bring together researchers, engineers, students from academic institutions, experts from industry, and practitioners to open sharing of knowledge about the advanced technology of electronic and telecommunication. And we also invite for refutable keynote speakers who are experts in their field. They are from Thomas D. Antopoulos, from the King Abdullah University of Science and Technology, Saudi Arabia, from Prof. Hun Jun Yin, from the University of Manchester, England, Prof. Goe Biranto from the Research Center for Telecommunication, National Research and Innovation Agency, Indonesia, and the last, Insinyur Linus Andor Maulana Sijabat from PT Land, Indonesia. Ladies and gentlemen, let me inform you that the ICRAMET 2022 continue to track many participants and paper submission from worldwide. The participants come from Indonesia, Malaysia, China, USA, Japan, Sri Lanka, Turkey, South Africa, South Korea, Palestine, Taiwan, Germany, and Saudi Arabia. We have received 102 submitted papers, whereby 55 papers have been selected and accepted to be presented, of course, after undergoing a double-blind reviewing process with an acceptance rate of 54%. And also, the peer review was conducted by academicians and researchers from 15 different countries. The subject ranged from description of new techniques and methods in their field of remote sensing and radar system, antenna device, microwave theory and device, electronics material, wireless communication, signal and image processing, control system, and other related topics. I'm sure the selected topic will provide you with the wealth of information and many discussion opportunities. Ladies and gentlemen, this conference resulted from many parties' hard work, support, and dedication. So we thank all the committee members who worked tirelessly for this conference. We also thank all the funding sponsors for their support of the meeting. We are also very thankful to the IEEE Indonesian section as the technical co-sponsor for helping us to organize such a big event. Last, we express our heartfelt thanks to the invited keynote speakers who, despite their busy schedules, manage their times, and have kindly agreed to deliver highly stimulating discussion. Finally, we look forward to having a successful conference, and we hope that all the attendees enjoy and benefit from this conference. Once again, welcome, thank you, and have a nice day. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr. Riana Tariana. Moving on, we will hear a remark from the head of Research Center for Telecommunication, National Research and Innovation Agency Indonesia, or known as BRIN. Please welcome Dr. Nasrullah Armi.
Thank you, Ms. Dita. Assalamualaikum warahmatullahi wabarakatuh. Good morning, all. Respected keynote speaker, head of Research Center, chairman of Research Organization for Electronic and Informatics, and then chairman of IEEE Indonesian section, and all participants. It is my great pleasure to welcome you to ICRAMET 2022 International Conference on radar, antenna, microwave, electronic and telecommunication. This is the first conference event organized by Research Center for Telecommunications in collaboration with Research Center for Electronics, National Research and Innovation Agency, BRIN. For your information, BRIN is established at the beginning of this year, 2022. Previously, ICRAMET is organized by Indonesian Institute of Sciences, LIPI, and the Research Center for Electronic and Telecommunications in 2015. Participants of ICRAMET 2022 are coming from many countries, as mentioned by Chairman, from Malaysia, China, Sri Lanka, Germany, etc. Mostly coming from Indonesia with various professions as a student, researcher, academician, and practitioner. The technical program of ICRAMET 2022 include keynote talk, pattern, and technical oral session that will be completed within 2 days. In this opportunity, I would like to express my gratitude to the chairman of ICRAMET and a committee, and then IEEE Indonesian section, technical advisory panel, researcher and staff, and all sponsors, and all of whom have assisted and supported ICRAMET 2022. Lastly, to the authors and delegates, it is you who have made this event success. Finally, I hope this ICRAMET conference is a venue to find new collaborator actually, and sharing your latest work. Thank you very much for your attendance and supporting ICRAMET 2022, and enjoy this event. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr. Nasrullah Armi. It is now my pleasure to welcome to the chair of IEEE Indonesia section as the technical co-sponsor of ICRAMET 2022 to deliver his remarks. Please welcome Dr. Wahyudi Hasbi.
Distinguished guests, colleagues, researcher, professional, ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh. Very good morning, Shalom, Om Swastiastu, Namo Buddhaya, Salam Kebajikan, a prosperous and warm greetings. First of all, please allow me to greet the excellencies, all my colleagues and friends, head of Research Organization for Electronics and Informatics, Dr. Engineering Budi Prawara, Head of Research Center for Telecommunication, Dr. Nasrullah Armi, Head of Research Center for Electronics, Dr. Yusuf Nur Wijayanto, Head of Research Center for Computing, Dr. Rifki Sadikin, MCom, Head of Research Center for Smart Mechatronics, Yanwandri Putrasari, Meng, PhD, Head of Research Center for Data and Information Science, Dr. Esa Prakasa, MT, Head of Research Center for Artificial Intelligence and Cybersecurity, Dr. Anto Satrio Nugroho, BEng, Meng, Conference Chair of ICRAMET 2022, Dr. Yana Tariana and my colleagues in BRIN, distinguished keynote speakers, patron representative, all distinguished speakers, committee participants, ladies and gentlemen. It's such an honor and pleasure for me to be able to greet you all and give a few words to represent the IEEE Indonesia section at the opening of this conference. On behalf of the IEEE Indonesia section, I would like to express my sincere gratitude and welcome you all to the 2022 International Conference on Radar, Antenna, Microwave, Electronics, and Telecommunication, or ICRAMET, as the 11th amazing year of conference. The conference is an annual event organized and sponsored by Research Center for Telecommunications, National Research and Innovation Agency, and also supported by IEEE Indonesia section, that aims to bring together researchers, scientists, engineers, scholars, students, and practitioners interested in the advanced technology of communication and electronics, including remote sensing and radar system, antenna devices and techniques, RF and microwave theory device, electronic material device and component circuit, wireless and wired communication, signal and image processing technique, control system, robotic and mechatronics, and all related topics. Distinguished guests, colleagues, researcher, professional, ladies and gentlemen. As we all know, engineering, especially electrical engineering, has helped solve our daily problems and our production needs by applying scientific knowledge, technical methods, design, and management principles. Indeed, aspect of human life greatly expanding the scope of electronics and communications. From your pocket FM radio to televisions, laptop, mobile phone, and even high-end satellites, electronics have become an integral part of our daily life. While some segment of ICT, electronics, electrical and electronic industry like consumer goods, consumer electronics, aviation, and automotive have seen massive dismissal of workers, the demand for semiconductors and devices related to data center and next generation of high-speed communication network system like 5G and also 6G initiative is steadily growing. Even currently, we are facing low supply of chips and semiconductors around the world. The pandemic also accelerated technology related to Industry 4.0 like robotization and artificial intelligence, ICT, electrical, electronics workers in telecommunication, energy, and healthcare division report a higher workload than usual. In such so, I believe that the theme of this conference, emerging science and industrial innovation in electronic and telecommunication, is very important in highlighting the innovation to accelerate the shift to innovation and transformation for digital era and global community. Distinguished keynote speakers, ladies and gentlemen, IEEE Indonesia as a regional organizational unit of IEEE was founded in 1988, and over the past 34 years, we already contributed significantly to have various activities that encourage science and technology for humanity in Indonesia. Together with all volunteers, members, and stakeholders, IEEE Indonesia has produced various activities by supporting more than 70 high-quality conferences every year, including supporting this 11th year of IEEE conference. Compared with the previous year, for example, in 2021, the conference supported by IEEE Indonesia is increased by 50%. And as we all know, the high-qualified conference papers within the scope of the IEEE are published in the IEEE Explore Digital Library, indexed by Scopus Web of Science and any other major databases, with more than 6 million publications and more than 15 million downloads every month. Besides that one, IEEE also developed industrial standards such as IEEE 802 as a standard Wi-Fi that we use in our daily life. In electricity standard, for example, standard 1547 has been a foundational document for interconnection of distributed energy resources with electric power system of the grid. Besides that, IEEE Indonesia also holds more than 40 professional, technical, non-technical, and administrative activities every year for all our members. And currently we have more than 2,400 Indonesian members and more than 80 senior members consisting of professional, industry, academia, and government researchers, including our colleague from BRIN as well. IEEE Indonesia also supported 26 technical society chapters and joint chapters, and also including 34 university student branches and 9 IEEE student branch chapter. In 2021, we already established a cooperation agreement with Directorate General of Higher Education, Research and Technology, in which IEEE Indonesia actively support and synchronize the Indonesian Ministry of Education and Culture Research and Technology Program, including taking part in the Campus Merdeka or Merdeka Belajar or Independent Campus Freedom to Learn. This historical collaboration will strengthen the development of Indonesian higher education, especially for the 8 leading indicators of higher education in Indonesia. We are also actively exploring cooperation with Indonesian industry in various activities and actively involved in providing input in preparing related government regulation. Several times we also submit our opinion about, for example, the Communication and Information Ministry regulation as well. So I would like to encourage all of you also to contribute for providing input in related government regulation. We are also already established an MOU with Indonesia Telecommunication and Digital Research Institute, or ITDRI, also known as the Telkom Corporate University, in learning, research, and innovation collaboration through publication, empowerment, and education to develop Indonesia's technology leadership, innovation capability, and digital talents. Hence, I would like to invite the latest development and advanced information, knowledge sharing, and any other activities in the current and future technology by becoming our IEEE members. Ladies and gentlemen, in this occasion, I would like to express my gratitude to all of the committee, especially to Kang Yana, Bu Riri, and all the team who have worked very hard in preparing this high qualified IEEE conference. I'm very aware that putting together a conference of this size is not an easy task. Therefore, I hope for your cooperation and active participation in all of this conference program. I hope all of you will have an enjoyable and valuable experience during this conference event. Please share your best knowledge in your area of research and professional activities. Please stay active, stay healthy. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr. Wahyudi Hasbi. Now, please join me in welcoming Dr. Budi Prawara for officially opening the 2022 International Conference on Radar, Antenna, Microwave, Electronics, and Telecommunications. Please welcome Dr. Budi Prawara.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Very good morning. Distinguished keynote speakers, invited speakers, ladies and gentlemen. It is my pleasure to be here to welcome all of you to the 11th International Conference on Radar, Antenna, Microwave, Electronics, and Telecommunications, or ICRAMET 2022. I am Budi Prawara, Head of Research Organization of Electronics and Telecommunications. National Research and Innovation Agency, or BRIN, Indonesia, and I am here on the behalf of the organizing committees. The theme of ICRAMET conference this year is Emerging Science and Industrial Innovation in Electronics and Telecommunication. I hope that ICRAMET conference this year accommodate the discussions and the discovery, the research of electronics and telecommunication. We have carefully curated papers that are covered in 7 conference tracks. We also welcome our keynote speakers that has been thoughtfully selected to online recent development and updates in the electronics and telecommunication technology. First, Insinyur Linus Andor Maulana Sijabat from PT Land Industri Indonesia. Second, Professor Thomas D. Antopoulos from King Abdullah University of Science and Technology, Saudi Arabia. Third, Professor Hu Junyin, the University of Manchester, the United Kingdom. Last but not least, Professor Goib Wiranto from our own institution, National Research and Innovation Agency, Indonesia. We also welcome our distinguished patrons, Mr. Kwek Chi Yao from Rode and Swas, Mr. Jian Wei Tan from Mitra Systematica Global, Keysight Technologies, Mr. Jamie F. Confindo, Indonesia Telecommunication and Digital Research Institute, and Mr. Steve Reyes from Andritsu Unitronic Jaya. This conference was started from National Scientific Meeting at 2006, organized by Research Center for Electronics and Telecommunications, Indonesian Institute of Sciences, entitled Seminar Nasional Radar. This meeting was held annually until 2011. It was developed as the International Conference, called International Conference on Radar, Antenna, Microwave, Electronics, and Telecommunications. Since 2015, the proceeding of ICRAMET has been published globally in IEEE Explore Digital Library until now. We would like to express our utmost gratitude to all past and this year participants, speakers, sponsors, organizing committee, members, and all involved parties who have supported ICRAMET through the years. We would like also to express gratitude to IEEE Indonesia section as the technical co-sponsor of ICRAMET conference this year. Therefore, I officially open the ICRAMET 2022 and warmly welcome all the academics, scientists, and practitioners from all over the world to take part and deliver their idea and research findings. I wish that you will have 2 productive days of interesting and stimulating discussions. Also, I do hope that the conference would serve as a platform to provide incremental improvement and solutions to the problems in the electronics and telecommunication. Last but not least, I would like to thank all of you for being able to join this virtual conference. Please enjoy the conference. Thank you very much.
Thank you, Dr. Budi Prawara. On behalf of the committees of ICRAMET 2022, I would like to say thanks to our patrons who have supported the ICRAMET 2022. Rode and Swas, Mitra Systematica Global and Keysight Technologies, Andritsu and Unitronic Jaya, Indonesia Telecommunication and Digital Research Institute or ITDRI, and PT Radar Telekomunikasi Indonesia or PT RTI. We want to thank you for your generous contribution to ICRAMET 2022. Your support was instrumental in making this event a success. Next, we move on to the screen capturing session. I would like to request all honorable guests, distinguished speakers, presenters, and all of the participants to turn on your cameras. We will capture the frame 3 times, so I will do 3 times of the signaling. For the first frame, in 3, 2, 1. Thank you. For the second frame, in 3, 2, 1. And for the last frame, in 3, 2, 1. Thank you for all your assistance in the screen capturing session. Ladies and gentlemen, we have concluded our opening ceremony. I would like to thank all honorable guests, distinguished speakers, and all of our participants for the participations and attendance in the opening ceremony of ICRAMET 2022. Now, we are beginning our first agenda. That is to hear a talk from our esteemed patron, Andritsu and Unitronic Jaya, which will be delivered by Ms. Steve Reyes. I also would like to welcome Mr. Gumbira and Ms. Alice Tirta, representing Andritsu and Unitronic Jaya. Thank you for joining us on this session. This session will be moderated by Dr. Budiman Putra Asmaur Rahman. Dr. Budiman Putra Asmaur Rahman receives his PhD in Kumamoto University, Japan, in Human and Environmental Informatics. He joined Indonesian Institute of Sciences in 2015. His current research interests are radar signal processing, ground penetrating radar, and microwave remote sensing. Please welcome Dr. Budiman Putra Asmaur Rahman.
Okay, good morning, ladies and gentlemen. I'm Budiman Putra Asmaur Rahman, a researcher at the Research Center for Telecommunication BRIN. Will be serving as your moderator in this session. And welcome to patron session of Andritsu and Unitronic Jaya. Firstly, let me introduce about the company. So Andritsu Unitronic Jaya is the company focusing on the development, manufacture, and sale of electronic measuring instrument, quality assurance system for food and pharmaceutical, information and telecommunication equipment and devices. And we'll be hearing a presentation from Mr. Steve Reyes. So Steve Reyes is a senior product manager at Andritsu company, focusing on wafer broadband PNM measurement. He has been involved in the sales, marketing, of microwave test and measurement equipment for over 35 years. Steve received a BA degree from the University of California, Davis, and an MBA degree from Santa Clara University. This session is 45 minutes long, including the question and answer. For the participant who would like to ask a question, please use the raise hand function on your Zoom. And by the end of the presentation, I will call out your names and please briefly introduce yourself and then deliver your question. Now, moving along to our session, please welcome Mr. Steve Reyes, who will be speaking to us on 5G, 6G application and measurement solution using a broadband 70 kilohertz to 220 gigahertz VNA. Mr. Steve, time is yours. Hello.
Thank you. So are you able to see my screen now?
No, we cannot see the screen. Yes, we can see now.
Okay, good. Let me put it into full screen.
Yes, please.
And okay, so is it okay now, full screen?
No, we can see the full screen. Right. Still the same.
Okay, let me.
It's better.
Okay.
Okay now.
Yeah, I can't get presentation, but I can just use this mode. Okay, well, thank you very much. And hello, everybody. And it's good to see so many people attending. And the presentation that I have is related to VNA measurements and focusing on 5G and emerging 6G measurements. And what I will do is first go through an introduction and talk about the the different aspects of the emerging technologies, and then we'll go into some discussion and description about 5G and 6G measurement challenges. And then what I thought I would do is go into some VNA fundamental reviews that might apply to different types of measurements that you need to make with VNAs. And so we'll look at things like antenna measurement systems and measurement techniques, talk briefly about optical systems, and then talk about millimeter wave. And on wafer measurements will be the focus in that section. And we'll discuss antenna measurements, but also general on wafer measurement requirements. And then we summarize. So first, to talk a little bit about the evolution of cellular standards. And I think we all are very familiar with how things have progressed over the last few decades, really. And it's been a constant pressure for increased data rates. And so being able to optimize data rate transfer is a key aspect as we evolve from 3G to 4G to 5G, and now we're defining 6G. But it's all being driven by the requirements for more and more data rate throughput. And there's other aspects that constantly are being improved, such as latency. We're constantly trying to reduce the latency. Of course, improving reliability, extended the battery life, and higher density per channel. So, so antenna design has been a key aspect in this improvement of channel efficiency. But in terms of higher data rates, there's a number of factors that take place. And the way to support higher data rate is through higher modulation rates. In order to support higher modulation rates, then we find the need to go into higher carrier frequencies. And so that's one aspect for migrating up into the millimeter wave bands, is in order to support higher modulation rates in order to provide higher data throughput. And so there is this constant migration. Also, the reason why we're constantly falling on the same areas as we go into higher frequencies is the absorption band, physics of transmission of the signals, the wireless signals, and so we tend to get combined into certain areas, such as 60 gigahertz, where it's high attenuation, or up in the 80s and 90 gigahertz range, where there's low attenuation. And there's different reasons for that. Being an unlicensed band, 60 gigahertz is more appropriate for homeowners, etc. Whereas where your signal is going to propagate over a long distance, then you need licenses, and that's why the 70, 80 gigahertz E-band radios were popular. And so E-band was somewhat common and useful in support of 4G cellular bands, and E-band was considered somewhat of a backbone, or the ability to provide the data links. So the backhaul links was used in the E-band for 4G, and then as we migrated to 5G, we are now in D-band radio territory. And so we're now at 170 gigahertz. And so that's why there's so much design going on in the D-band and D-band radios. So again, that's a lot of the reasons why we have been constantly going up into higher frequencies. Okay, so I thought I would review some of the fundamentals of VNA measurements. And so if we just look at a typical measurement performed with a benchtop VNA, the key measurement capability of a VNA is to perform S parameter measurements. And so the forward and reverse transmission of a DUT or a system can be quantified through the S21 or the S12 parameter. And so in terms of matching the device in the system, that would be S11 and S22. And so you have these different ratios of measurements that are happening in order to quantify the measurement performance of a DUT. So S21 is simply measuring the output of port 2 compared to the input of port 1, et cetera, et cetera. So when we get into the inside of a VNA, this is what's actually taking place. We have sources, and it's sometimes one source that's transfer switch, or it could be two sources. But basically, in order to obtain 4 S parameters, you need both a forward and reverse signal projection through the DUT. Now, since the DUTs that we're talking about are operating at high frequencies, then we need to downconvert those signals. So in our block diagram, we see that we are sampling the forward signal, in other words, the reference signal, and going into a downconverter, a sampler. And so that downconverter converts that microwave, RF microwave or millimeter wave frequency down to an IF frequency, and that's labeled here A1. And the through signal going to port 2 is now going into the sampler B2, and now we have our IF at B2. So again, ratioing B2 over A1 gives us the S21 parameter. And so that's a typical measurement. The key point here is that everything is integrated into the VNA, and ideally you're going to locate the DUT very close to the test port. And so the test port is the direct link to the test and reference samplers. Also, notice that there's an LO that's very important here, and the LO is being distributed to all 4 samplers in order to make everything integrated and referenced to each other in a meaningful manner. And so that means not only magnitude but also phase. So what happens if we start to measure long cables? Well, the long cable is going to attenuate the signal, and so that's going to reduce our dynamic range, or the SNR, signal to noise ratio. And so long cables are going to degrade our measurement capabilities of the system. So even though the DUT is the same, the signal to noise ratio or the dynamic range is reduced, and so that limits how much of a measurement we can perform on this DUT. The other very important aspect is that these long cables are susceptible to variations in magnitude and phase due to temperature changes in the room and cable flexing after calibration. So we may all be aware that we can calibrate our VNA in order to get a good reference. So we can normalize the signal, and we could do that even with these long test port cables. But if there's variation, if we move the cables after that calibration or normalization, then that's going to affect the accuracy in our measurement. So that's why it's very important to keep your test port cables as short as possible. So that was an example on a benchtop. Now, as we go into higher frequencies, because we are going into microwave and millimeter wave frequencies for all of these systems, the 5G and merging over to the 6G system, we have to start thinking about even higher frequencies and how the test port cables can have an impact. And so this is just a quick diagram of a millimeter wave system where we have the VNA providing the RF and LO signals to a millimeter wave module. It's a waveguide-based millimeter wave module that's combined with the what we call baseband VNA in order to do a broad frequency sweep. However, in this case, we have a test port cable going to the probe. So we're doing on-wafer measurements in this case, but it doesn't necessarily need to be a probe. It could be just a test port at that end. But the key here is to notice that our test signal is attenuated quite a bit by the long test port cable. Now, when we do a calibration, we measure the errors in our system and correct for them. And so the directivity error is measured, and then we can compensate for that and get a calibrated measurement of return loss. Okay, so that's typically what we would do. The problem is if you send that signal through a long test port cable, you attenuate that signal and it becomes very small, and it can be even smaller than the error signal. And so that's a pretty bad situation, because after calibration, if we have any kind of temperature variations, then then our calibration is not valid. So again, the primary message here is to keep your test port cables very short in order to maximize your system accuracy and measurement accuracy. So now we can start to look at some examples of measurements. And the first case on the left is using a standard VNA, like I was showing before, and using long RF cables, and we're measuring the cable inside this aircraft. Okay, and as you remember, that long cable is going to degrade our overall measurement capability. And so using this technique, which is the traditional way of making measurements of long cables in an aircraft, you can see that there's limitations, especially when that cable is very long and you need to have the VNA halfway in between with long cables on both the input port and the output port. So that's a situation that you would like to try to avoid if at all possible. So the answer to that dilemma is to locate your test and receivers right on the test port, right on the RF cable of the DUT. And so if you can do that, then you've reduced the test port cable requirements. and therefore you have optimized the overall measurement capability. And so that's what we're doing here. And what this is doing is locating our test modules right on the cable itself. And the way that we're doing that is with our shock line VNA that's using these modules. And in addition to that is something that's called the phase link technology, which basically is measuring and correcting for the drift and phase issues in the two modules. So really, if you recall the LO frequency requirements, how we wanted to have them very close to both the reference signal and the reference sampler and the test sampler, what we're doing here is we're compensating for this long cable separation and monitoring the LO and then controlling everything through this system in order to optimize performance. So this is how we would make our measurements now using our shock line technology or shock line VNA technology with the phase link reference capabilities. And we can, in this system, separate the two modules by up to 25 meters. So that gives you an idea of the capabilities using the shock line technology in measuring a long cable. Another example is if you're measuring OTA, providing OTA measurements in an OTA chamber. Again, on the left, we're using long cables to connect our VNA to the two antennas. And the same issues are here as well, in that the dynamic range is reduced because of the signal loss. You have more measurement uncertainties because of the variations in the long cables and very bad phase stability. So again, using the modules and locating our test and reference samplers at the antennas gives us the ability to overcome those limitations and provide a full VNA dynamic range measurement rather than a reduced VNA dynamic range. Okay, so that's examples of how we can do antenna measurements using the shock line VNAs. So now I wanted to move over into the higher frequencies. So you saw how the systems were constantly migrating up to the millimeter wave frequencies. And so we're doing a lot of millimeter wave system design in order to handle the high data throughput requirements. So when we start to make measurements of these systems, what people are doing is they're performing what's called device characterization, which is basically measuring the individual devices. And that could be a transistor, a capacitor, an inductor, and we're sweeping that over a very broad range. And from that, we then can insert that into our circuit simulations. So we're modeling these devices so that we can simulate the circuits before we actually go to prototype. And when we go to prototype, then we can measure and determine if our circuit is working properly. If it's not, then we have to go back and redesign, recharacterize, etc. So this is a very typical scenario of measurements at the microwave and millimeter wave frequencies. And so you can imagine that as you start getting into on-wafer measurements, characterizing devices becomes very challenging because of the the geometry involved. We're talking about devices that are very small and they're located many layers down on a wafer. And so characterizing the signal paths to the DUT becomes quite a bit more challenging as you go on wafer and making on wafer measurements. So in terms of on wafer measurements, the VectorStar VNA has been optimized and provided with a number of different capabilities. It operates at baseband frequencies, which again, baseband is the standard frequency in the fundamental instrument, and it can go up to 40 gigahertz and 70 gigahertz. But if we want to go to higher frequencies, then we add millimeter wave modules. And the millimeter wave modules can then be combined with the baseband frequency to go up to 110, 125, 145, and 220 gigahertz. And this is utilizing what we call NLTL modules, nonlinear transmission line modules. And that's a technology that gives us an improved performance at millimeter wave frequencies using the nonlinear transmission lines. And we have a number of papers that describe this technology a little bit more in our websites. But in any case, we are able to extend the frequency of VectorStar up to 220 gigahertz. And again, still starting at 70 kilohertz. So that is quite an extension of frequency capability. And most typical millimeter wave broadband VNAs can go up to 110 gigahertz, but we are unique in being able to go up to 145 and 220 gigahertz. So this is a little block diagram of what's inside the nonlinear transmission line modules. And you can see that we have the test and reference samplers, again, inside this module. So very similar to Shockline, where we have the test and reference samplers inside our VNA modules. We do the same thing when we go up to the higher frequencies. And again, the primary reason why you want to do that is to maximize measurement performance and to get the best possible stability over a period of time. After you do your calibration, you want to be able to have a stable calibration so that you can continue to make accurate measurements. So the test and reference samplers operate from 30 gigahertz up to 220 gigahertz, and the sources are operating from 54 gigahertz to 220 gigahertz. And so all of these modules inside the module is coupled onto the DC transmission line. So in order to get good directivity in a system, you need to use good directional couplers. If you were to combine them with just combiners, then it would be very poor directivity. And raw directivity is a very important aspect of a VNA measurement. And so this is a photograph of a 220 gigahertz VNA system. And you can see that it has the network analyzer, and it's feeding RF and LO signals to the millimeter wave modules. And the millimeter wave modules are connected directly to the 220 gigahertz probes. There's also some bias T's connected in order to do bias T of the biasing of the DUTs. So again, being able to locate the test and reference samplers close to the test port is very important, and minimizing test port cables is also very important, especially as you get up into the millimeter wave frequencies, because insertion loss is very high at higher millimeter wave frequencies. So that becomes even more important when you're doing millimeter wave on wafer measurements. Okay, and the one other point about the bias Ts is that if you have a DC path through your millimeter wave module, then you're able to connect an external bias T and feed the bias through the module to the DUT. If you don't have a DC direct connect path in your module, then you will need to mount the bias T internal inside the module, which that basically eliminates the design options that you have if you want to change the capabilities of the bias T at a later date. Okay, so and I wanted to include one more example of how we are progressing to the demands for 5G and 6G measurements. And I mentioned about D-band radios. D-band radios are driving the need for differential measurements and differential devices, to improve the overall noise performance of your receivers, in a radio, etc. So differential measurements are becoming more and more important. And so we have been able to configure our VectorStar system into a 4-port 220 gigahertz VNA. And that means, with the addition of a differential probe to perform true differential measurements up to 220 gigahertz. And this is something that we're working on with MPI, and they are about to release a new differential probe operating up to 220 gigahertz, and you can see that it's made to mount directly to our modules and without any test port cables. So that is very exciting news, and something that many radio design engineers have been asking for, and now we'll be able to provide. So, people that are doing E-band, D-band, and even G-band work will now be able to perform differential measurements. So in addition to device characterizations on wafer measurements, there also is antenna measurements that would be on wafer. There's many different ways to measure antennas, and there's many different form factors of antennas. And sometimes they will be an antenna on the chip. Sometimes they'll be in a package, but they all need to be characterized by a VNA. And so, so there are different ways that that you can perform these antenna measurements, and they could be either far field or near field. And especially if it's going to be on chip, then it most likely is going to be a near field measurement. And so what you would do is, convert that to a far field measurement. And so far field measurements usually take place in an anechoic chamber, and so you have to have your VNA connected to the transmission module and transmission antenna, as well as the receive antenna. And again, I was showing how some of these measurements could be performed with the shock line. The shock line can go up to 43 gigahertz, but VectorStar can go up to 220 gigahertz. So when you start getting into some of these higher millimeter wave frequency antennas that are mounted on chip, then you definitely need to get into the on wafer VectorStar millimeter wave systems. And so that's what we're showing here in order to make measurements. here we're showing the 3743 module that goes up to 110 gigahertz, but you can include any of our other millimeter wave modules. And so so that's another example of how you can do far field measurements of antennas in an anechoic chamber with the Beckett-Starr system, as well as on-chip measurements using the the on-wafer setup. So there's also an increase in optical measurements, optic electronic measurements using a VNA, and basically the the higher data throughput requirements is taking the need for high data rate communication on a chip-to-chip level, and even on a system-to-system level. And so more and more people are using the optical fiber to connect and modulate the signal with a baseband frequency, and those are going to higher frequencies from 70 gigahertz and even up to 110 gigahertz. And so these modulators and photodetectors on chips, such as TOSAs and ROSAs, etc., can be measured. And so that's another example of VNA measurements, up into the millimeter wave frequency, to support optical measurements. And then finally, another aspect for VNA measurements is the ability these days to do spectrum analysis. So especially when you're on wafer and you're touching down on a wafer to make a measurement, you would like to make as many measurements as possible. And if the VNA has the ability to measure the spectrum at the same time that it's measuring the S parameters, then that's even more valuable. And so we do have a spectrum analysis option that can work with any of our systems. So therefore, we have the ability to do spectrum analysis work from 70 kilohertz up to 220 gigahertz with our G-band VNA. And so that is something that's also been very popular, and people are using that quite a bit. Okay, so to summarize then, the aspect that I was working on and describing is how to optimize your measurement performance and accuracy, both at microwave frequencies and at millimeter wave frequencies. And so we started talking first about microwave systems and the fact that we want to keep our test port cables short in order to maximize dynamic range. And usually on a benchtop system, you can use cables up to about a meter or so before you really start to deteriorate your measurement capabilities. When you go to higher or longer cable lengths, then that's when you would want to use things like locating your test and reference receivers as close to the ends of the DUT cable as you can, and that's where we were showing the shock line phase link capabilities. Other aspects is what I was talking about was the need to minimize cable movements. That's very important in all systems. After you do a VNA calibration, you want to minimize any kind of cable movement of your test port cables because that will have an impact on your measurement accuracy. And also regulate the temperature variations in your room. So for instance, you wouldn't want an air conditioning fan to be blowing directly onto your system while you're making measurements, because that will have an impact on the stability of your measurements. And same thing with millimeter wave systems. Try and locate your test and reference receivers as close as possible to the DUT. You're going to probably also use some de-embedding techniques. So you want to keep that in mind. And but basically, you just want to keep those losses as low as possible in order to maximize dynamic range. And then as you go higher in frequencies into the millimeter wave regions, you want to connect your modules directly to the probes or directly to the DUT test ports in order to maximize dynamic range as well. But even more important is raw directivity in order to provide good measurement stability. Okay, so that concludes my presentation. And if there are any questions.
Okay. Thank you very much, Mr. Very interesting talk, and we have learned a lot from this presentation. So we learned about the vector star arm provided by Andrew that can be applied for many applications. For on-wafer device measurement, optoelectronic, and also communication. So from the Zoom, we get one question from Mr. Yusuf Nur Wijayanto. So the question is, as you mentioned in the presentation, that we use ultrawide band from 70 kilohertz to 220 gigahertz. It is very interesting and hot issue for future application. One problem coming in the measurement setup, especially loss due to mismatching in the microwave connection or cable, to have and some special method to solve it. Thank you. So that is the first question. Maybe Mr. Steve Reyes can answer first.
I'm sorry, but your connection was kind of dropping off right towards the end. Could you again repeat that? Summarize the question again.
So the main point of the question is the problem coming on the measurement setup in the high frequency is the loss because of the connection and the cable. Maybe Mr. Steve can give comments about this issue.
Okay, yes. And let me see if I can get back to, well, maybe you started off by talking about the 70 kilohertz to 220 gigahertz. So the key on this system, again, is the connection of the test port of the module to the probe. That's where your most challenging aspect of the integrity of the connection will be. Now, behind the module, you see the blue cables. Those cables are only operating up to about 40 gigahertz. And so the connection to the module is pretty reasonable for a microwave VNA, operating up to 40 gigahertz. And so everything else inside the module is taking place, on the wafer of the module itself. And so again, so that green box is the millimeter wave module, and all the lines going in at the top, the reference IF and LO. The IF signal is at 12 megahertz, and the LO is up to 20 gigahertz. So, so those connections are not as critical as the connection at the test port of the module. And that's where the probe connects directly. Now, the connection at that point is important, of course, and critical. What we have is we developed a 0.6 millimeter test port connector, coax test port connector. And so the test port output of the module is 0.6 millimeter. That's because 1 millimeter connector only operates up to 110, maybe 120 gigahertz. But to go to higher frequencies, you need smaller geometry connectors. So that is quite important. But we have the 0.6 connector on both the probe and the test port of the module. And I'm sorry, I don't have that included in my presentation, but we have photos of that. And if you're interested, I can send you those photos. But the actual connection is quite solid and stable. So it is a true coax connection, and there's no cable in between. So that's how we are able to optimize and make measurements from 70 kilohertz to 220 gigahertz. I hope that answers your question.
Okay, thank you, Mr. Steve, for the answer. I think it's answer the question. So because the time is limited, maybe I have one more question, but please answer with the short answer. The second question is about the millimeter wave. It is possible to measure the millimeter wave frequency with this equipment?
Yes, it is. And again, it's because the module includes the receiver samplers, and so it receives the signal through the DUT and therefore makes the measurements up to 220 gigahertz. Now, if by millimeter wave you mean higher frequencies, yes, you can connect higher frequency modules. So you take off the the NLTL module and you attach waveguide modules. And with waveguide modules, you can go all the way up to 1.1 terahertz.
Okay. Thank you very much, Mr. Steve. So time is up. I would like to summary of this session. So the VNA presented by the Mr. Steve, vector star VNA from Andritsu, is VNA with very broadband frequency rings, and it is possible to apply the VNA on wafer device characteristic of the electronics and also telecommunication. And thank you very much for Mr. Steve Rice for addressing this interesting topic. And on behalf of the committee of ICRAMET 2022, we would like to present you with a token of appreciation. So this is...
Okay, well, thank you very much. And I very much appreciated the opportunity.
Okay, thank you, Mr. Steve. And thank you also for all participants for joining this session. And thank you for Andritsu and Unitronic Jaya for providing patronage to ICRAMET 2022. And finally, I return back the time to the host, Ms. Dita.
Okay, goodbye.
Thanks to Dr. Budiman Putra Asmarohman. Also, thank you to Mr. Steve Rice and Andritsu and Unitronic Jaya for having brought to us the first patron session. Next, we will have our first keynote talk by Insinyur Linus Andor Maulana Sijabat from PT Line Industri, Indonesia. This session will be moderated by Dr. Yuliar Firdaus. Dr. Yuliar Firdaus received his Doctor in Science from Department of Chemistry, KU Leuven, Belgium in 2015. He then joined King Abdullah of Science and Technology, Saudi Arabia as a postdoctoral fellow prior to joining National Research and Innovation Agency or BRIN in Indonesia in 2021. His research interest covers device physics, photovoltaic devices, and energy harvesting devices. Please welcome Dr. Yuliar Firdaus.
Thank you, MC Ms. Adita, for your kind introduction. Ladies and gentlemen, good morning. Assalamualaikum warahmatullahi wabarakatuh. Welcome to the keynote talk session of ICRAMET 2022. My name is Yuliar Firdaus from the Research Center of Electronics, BRIN. It is an honor to moderate this first keynote talk. I hope we will have an engaging discussion in all of the ICRAMET 2022 sessions. Also, let's welcome our first keynote speaker, which is Insinyur Linus Andor Maulana Sijabat from PTLN Industry. Mr. Linus, I think, is already present with us in this virtual room. Mr. Linus, are you ready?
Yes. Okay. Allow me to share my screen.
Okay. Before you talk, let me first introduce you. So I will read out your profile. Mr. Linus took his bachelor degree from Institut Teknologi Bandung, majoring in electrical engineering. He graduated in 1994, and I assume he immediately started working in PTLN industry afterwards. So please correct me if I'm wrong. He had so many work experience, among them as technology and operation director at PTLN Railway Systems, General Manager UB Systems PTLN Industry, Director Operation 1 from 2017-2020, and from 2020 to this present day is a Director of Business Strategy and Portfolio at PTLN Industry. Insinyur Linus is a well-known figure in the railway sector in Indonesia and has a lot of contribution to PTLN Industry. So his research interests are railway signaling system and solar power plant. The second one is quite overlap with my research interest actually. However, he will talk more about this railway signaling system. The title of his talk is Implementation of Open Hardware Platform for Railway Signaling System. Okay, Mr. Linus, your keynote talk would be in total 45 minutes, including the question session. And maybe I will remind you in case the time for your presentation is almost up. Is that okay?
Yes, okay, of course.
Okay, then without further ado, the floor is yours. You can start your presentation if you're ready.
Okay, thank you. Good morning, gentlemen, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera buat kita semua. Everybody can see my screen? Okay, let me put it to slideshow.
Yes, we can see your screen. Just
Okay.
waiting for the full screen.
Okay, it's ready?
It's full screen now, yes.
Okay, thank you. Today I will present you regarding the implementation of the open platform, hardware for the railway signaling, which is my company, PTLN Industry, is the strongest point in the world. Yeah, I think we are the first company in the world who initiate this by using the open platform hardware for railway signaling. Okay. Yeah, as I'm Linus, I'm from PTLN. Now I become a senior executive vice president for PTLN Industry. Okay, this is what will be in my presentation. Of course, first I will some introduction, and then of course some signaling system overview, and what is the open platform, and how it be implemented on the railway. So we have implemented this on the APM, which called People Mover in Soekarno-Hatta Airport, International Airport, and conclusion in the end. Okay, if you see, this is the evolution of the electronics in the railway. So first, I think it's control, especially in the railway signaling. So in the beginning, people use mechanical, and then go to electromechanical at the second, and then some relays and railway signaling. Yeah. So far in the electronics, what we have is using proprietary solutions. So some company, big company, they develop their own electronics. Yeah, their own electronics, and the result is expensive. As you know, signaling of a product is not produced in big quantity, not in the thousand, not in the million, maybe only some even 100, not achieve 100 in a year. So if we develop by proprietary solution, the NRE, non-recurring cost, will be borne to small quantity of the product. So that's why the electronic for the signaling is very expensive. So Indonesia, I think we develop our railway, but as you know, how do we develop our railway? By very limited budget. Yeah. So in this we have to do some improvise. Yeah. So what we do is we using the codes. Yeah, commercial of this component. So or we say the open platform hardware. Yeah. So the result is, of course, the open platform is developed by third parties and can be used in other sector as well, and support not only to dedicated usage in the application. So the cost will be very effective. Yeah. So only flexible and is easy to use and high performance, of course, because it's developed. It's using always the last technology. Yeah, develop. So if we see the application in this is a big application in the railway. So here we have is like we said in our company, we get Silfu is more in the operation control center. Yeah, to control the traffic, like scheduling, timetable, etc. We call it our product. We call it Silfu, and then of course we have trackside equipment to control the route control, the traffic, yeah, in the wayside. And of course, we also have the ATP, the what we call it train protection, yeah, train protection for the train, yeah, and also some, if you see how, and on the onboard equipment, we call it a seal move. So on the route control, to control the infrastructure, we call it seal safe. And to control the train is seal move. It is can be using to be the driverless. If a driverless train is applied, so definitely we need some onboard equipment. Yeah. Okay, this is the signal system overview. So I think the purpose of signaling, of course, is to ensure safe movement of the train. Yeah, they do by locking. Yeah, locking the movable track. This is the movable track on the left side, and of course, the driver should see the line side signal. It is be able to pass to proceed or not, and of course also how to detect the train movement. Yeah, train movement. Yeah, and also train presence. Yeah, so we need some, we call it Excel counter to detect that. Yeah, so this is the purpose of the signaling system. And if you see, there is a conventional one and modern signaling. Yeah. So as I mentioned before, there are two part in the signaling now in the modern urban railway. Yeah. So one is route control and the other is train control. So in the route controls, there is no interaction between the train and the signaling system. So the drivers have to interpret it from the signal he saw. Yeah. He saw. And how to drive the train, yeah. And in the train control, there is some there will be interaction between train system and signaling system. So in that we need a computer to calculate the movement authority of the train, to guarantee the safe operation of the train. And because this is a public transportation, it is require high safety. So railway signaling normally they have in SIL4, in SIL4 the tolerable hazard rate will be in SIL4, so the tolerable in between 10 power minus 9 and 10 power minus 8. This is the requirement for the signaling system. Some other system may be required less, but for the urban who is heavy duty, definitely we need the level of the system in SIL4. And of course, some safety related electronic standard applied to that, of course, for the hardware. So for the hardware is, I think everybody know, they have the Euro norm 50129. It's first announced in 2003. And for the software, so there are also some standard for that. The Euro norm is 50128, is published first in 2011. And the total RAMs, reliability, availability, maintainability, and safety, for the EN 50128, in 2017. So of course, it should be followed the full life cycle to guarantee that all the process is done correctly, and some validation and verification must be applied to meet all these standard. So what is the open platform? So open platform and modular railway platform, it is based on the standard hardware and software. So we don't develop any new software, but we use the codes, what the possible codes, what the available codes in the market now. And then we do some freely programming. We also do not develop our own development system, IDE. We choose the IDE that available in the world, available now in the market, But of course, it should be certified up to SIL4 to meet all these requirements, Requirement for the EN, the RAMs, and 50128 for the software and 50129 for the hardware, And a scalable safety level, solely determined by the application requirement, So we have to do some application to meet this. So it's not directly we got the hardware from the market and it achieves some SIL4. We need some, what we call it, some application requirement, And in some, it's come from the what vendors come from certificate packages, like the hardware that you can see on the left side have the certificate packages, from TÜV, This hardware before we get from Micro, now I think it's merged with Duagon, so this will be part in Duagon Safe Control. We call it DSG. So this is some the hardware that we need the support of the application of signaling. Of course, they need some how to calculate the movement of the train. We need the vital system controller. And the other one, of course, we need more I/O, so we need remote I/O as well. So we call it KT8, and some digital output, safe digital output K1, and this digital output in high side K1, and in low side it will be K7, and some digital safe digital input. We name it K2, and all of this part they have their own certification, by TÜV. So this is how the software, safe software, developed, to meet the SIL4 requirement, So this is later on I will show you all the detail of the hardware, but of course this including the PASI and the BSP, all is certified in SIL4, And of course there is some part also from the software. We no need to be SIL4. So like, so we use in this case some Linux or other software. Yeah. So the product actually they are pre-certified. Yeah, certified functionally. Yeah. So it of course will save the cost, time, and risk with the pre-certification. Yeah, we are following the packages. The package already delivered. We follow that. And get synergy for all safety critical application and can be used in all safety related application on board and trackside. Yeah. So we have also modularity in I/O configuration and software, the flexible configuration for the control unit, and modularity in terms of software. Only the part that are really needed we develop and configured in the system. So it's not like we get some full operating system and then everything in the system. No, we choose only the dedicated one, which is really needed in the hardware. Yeah. And then of course, because this open platform, they will be independent from suppliers. So as you know, now because of proprietary in the word of the signaling, so there will be some vendor lock. So in this case, no, there are no vendor lock. So customers they have free to choose who is supply even for the next development of the line. Yeah, and standard base. Yeah, so we use the standard OS, Unix, Linux, and also some standard POSIX programming. Yeah, of course, because this is open platform, the system is the system will be long-term availability. Yeah, so the system is based on the open industry standard in hardware, software, and communication with broad acceptance on the market. So this guarantees alternative for the every function. Yeah, and the end user is protected from the obsolescence issues. Yeah. So this is some detail of the hardware architecture. So we have in the following, first we have controller, which consists of safe CPU, compact PCI peripherals, and real-time Ethernet board. And this is the picture in the left side, and in the right side is the remote I/O. Yeah, this is purely a real-time Ethernet board. Yeah. So the single CPU, the F75 is a 2 out of 2 architecture. Is according to it comply with the EN 50129. And for the safe I/O, have SIL4 compliance also to the 2 out of 2 architecture using the unit of SIL2 I/O and dual channel. Yeah. So this is the more detail on the architecture. So we have, as I mentioned before, this is 2 out of 2. Of course, they will have 2 CPUs. Yeah, CPU1, yeah, and CPU2, yeah, and there is some I/O processor, yeah, and some communication using the FPGA. Of course, this will be black channel, yeah. So this is we combine two with white channel and black channel, yeah. So the detail of the hardware is 3 Intel Atom computers on the one board, 2 processor for the safety related, and 1 processor for non-safety related, yeah. The processor for safety is configured 2 out of 2. Configuration. So yeah, this is the software architecture. As I mentioned before, there is some software with no need to be SIL4, and some software that definitely we have to SIL4. So this is 2 like non-safe domain. We call it general purpose user software, and then Yocto Linux. We use Yocto Linux, and some safe domain is safe application software. Yeah. And PASI, and of course a safe kernel or safe BSP, yeah, board support package. And then we uploaded it to the safe open hardware platform. Yeah. So this is, of course, there will be some separation. We should be clear separation between vital software and non-vital software. Yeah. With one is using the SIL4, with one should be definitely safe separation. Yeah. And safe application interface as well. Yeah. So this is a more detail of the communication black channel, because in the in the board, in electronics, not everything can be clearly be white channel, and some will be black channel because of the complexity. So it's difficult to define white channel. Yeah. Some will be black channel like communication. It's difficult to define algorithm. So definitely we don't explore the detail in the process. but we detect, we call it the output, the consistent of the output. Some methodology can be used for that. Yeah. So in order to guarantee the appropriate communication, between the safe computer, the controller, and the safe I/O function via real-time Ethernet, the black channel approach is applied. Yeah. And the requirement to transfer safe data of untrusted communication are defined also in EN 501559 and realized using FSOE, fail-safe over Ethernet. Now, this is how this will be implemented on the real world. So we have a project in the Soekarno-Hatta Airport for the people mover. Yeah. So if you see in Soekarno-Hatta, this is the connecting between the Terminal 1, Terminal 2, and Terminal 3. So this is the picture. You see the curve. It's nice curve. Yeah. So it means that we really need the what you call a reliable system because of the curve. Yeah. And PT Land Industry has implemented the open platform hardware in the only people mover system at the Soekarno-Hatta Airport. So this is some picture of that. And below there is some driver side, which is controlled now by our onboard equipment. Yeah. And also the SCADA, we call it the SILFU. Yeah. This is the, what you call it, the detail of the project. Yeah. So train have maximal speed, it's 70 km/h, and passengers 176 passengers. And the signal is, we use CBTC. So this using the moving block. Yeah. Yeah. And this is rubber tire. So in the left side, you see the detail of the project. Even the value of the project is 561 billion rupiah, yeah, something like that. So and it's very tough. You see the schedule is very tough. Only 345 days. So if we do the preparatory, I think we cannot match this. You cannot match this. You cannot do this project in this because this is open platform and everything is available in the market. So we can finish the project in 345 days. Yeah. And the train set is 6 train set and 3 km line, and the capacity is 2,100 passenger per hour per direction. Yeah. So the reason I put this detail is especially for the value of the project, 571 billion rupiah, is meaning that the open platform already proved that this can be controlled as the heart of the big project. So I think 561 million rupiah is almost like 40 million, yeah, close to 40 million US dollar. So 40 million US dollar is, I think, quite big project, yeah, quite big project, and it's proof that using the open platform, I think we can control also the big project. And this train is driverless. So this is in the system, in the umbrella system. So we do what we do. What we do is we do the model design. Yeah, of course we have some research and some requirement and design. So and we have some simulation, of course. Yeah, simulation, of course, in the top, yeah, top left, some modeling simulation, and then we know the performance, whether the performance already achieved the requirement or not. And then with this achieve the requirement, and then by the simulation we can see it, and then we generate implementation to the do the implementation and implemented it to the safety computer, which I mentioned before, the open platform system, and then we do the integration. And this system, we call it and deploy the system to upload it the source code, yeah, the code to the SILMove, yeah, we call it SILMove 4000. So this is the picture of the hardware, yeah. So in the left side, it is the interlocking system with more handle in the root control, yeah, controlling the infrastructure, switches, lamp, and Excel count, etc. And the ATP side is more in control of the train, who give the movement authority to the train. And of course, we have the ATP on board, which is become driverless. Yeah, so we can control the train, so the train can be driverless. So this is the driverless operation. Yeah, this is like a schematic. So I think this is the PI. Yeah, PI control. Yeah, so we can implement the PI control here for the ATO. Yeah, for the ATO application, automatic operation of the train. Some conclusions. Yeah, with open hardware platform solution, we considerably reduce costs compared with proprietary system. Yeah. Moreover, spare parts are quick and easy to obtain worldwide and can be quickly installed. The open hardware platform also can be more flexible, yeah, faster and more cost efficient. So PT Land has successfully installed the open hardware platform in the APM in Soekarno-Hatta International Airport with driverless mode that can be operated without a driver. So I think will be the end of my presentation. Thank you very much for all of your attention. I will be open for any question if you have. Thank you.
Thank you, Mr. Linus. That's very encouraging, actually, presentation to know that our own human resource can develop such kind of system, which we also use. We have been using it for the application in the railway system in our airport. So I think we are now in the question session. I have seen several questions in the chat box room, but I encourage some people who already asked questions in the chat box room to ask directly, maybe because we still have time. So I will suggest Mr. Ananda to ask the question first. If you are available, we can ask question. Mr. Ananda, are you there?
Yes. Thank you, Dr. Firdaus.
Yes, go ahead.
Yeah. Good morning, Mr. Linus. Since this is a safety critical system, I'm concerned with how do you ensure the robustness of your software, especially your custom developed software.
Now I answer or waiting, Pak? Hello?
Dr. Firdaus?
Yes.
Should Mr. Linus answer my question directly or wait for other questions?
Yeah, Mr. Linus, you can answer directly the question. Yes. Go ahead.
Okay, yeah, as I mentioned you before, that the software we develop is compliant to the standard, yeah, to the standard EN 50128, yeah, and luckily because parties who audited it is come from BPPT, Pak. So BPPT need 14 months to audit, and until we get the certificate from BPPT that the software comply with 50128. But it's not as difficult as that. As I mentioned before, this is the open platform. Actually, the product already will come with some certification package, yeah, even the software and even the hardware. So we follow all the packets there, yeah, which predefined by TÜV, yeah. So the Duagon at the time hired the TÜV, yeah, to audit the safety package, yeah, safety package of that. So we follow all the packets, which meaning that we don't have to read from the beginning all the EN. Yeah, of course we need some training for that, of course, but we follow that. And then it's go to the auditor, and this already certified. So the output already been there. We follow everything, and some test requirement also. And BPPT need 14 months, Pak. 14 months to audit that and to test everything until it issue the certificate that compliance with 50128. Is that answer, Pak?
Yes, thank you.
Thank you.
Okay, maybe we have the second question. I think, Pak Michael, you can ask directly the question if you are ready.
Yeah, thank you, Dr. Juliar. Good morning, Mr. Linus.
Morning, Pak.
Yes, my question is about sale also concern the maintenance or the repair phase of product life cycle.
Yeah.
how land can ensure the short time of MTTR, mean time to repair, if the hardware is made by third party? Thank you. I think the second question is already asked by Mr. Ananda.
Okay.
Thank you.
So if you see all of the life cycle, so the life cycle of the RAMs, RAMs, I think is we have to follow for the railway, especially for, it's not only in the base development or is in the execution project, of course, also in the maintenance, and after sales. It is written in the EN 50126. This is the total RAMs, So we follow that, So we know how to mean time to repair. So that is why, like the readiness, like the availability of the part. So when you say that your product comply to 50126, is meaning that you guarantee for 25 years availability of the spare part. So that, of course, there will be some purchasing strategy for that, because even this is the codes, the commercial of the share. Of course, there is some delivery, but it's not like what you call proprietary system. So proprietary system normally like job order. When you get the order, then you do, then you produce the product, some part, you do the part. But this is because this is the codes, is meaning that have regularly produced the product, like yearly maybe. So we indicate to the vendor that some indication to the vendor how much we need for the this year, for the next year, something like that. So we give some indication to them, and they manage by themselves. So they have a regular production of the product. So that is how to reduce the MTTR. So in this case, it will be much easier to maintain this open platform compared to proprietary system. Is that answer, Pak Yukesen?
Yes. Okay. Thank you. Thank you very much.
Okay. Thank you, Pak Michael, for your question. Maybe I will read also one question from our head of Research Center of Electronics. He is now in meeting, so I will read his question for you. Yep. So his question is related to trend signaling in order to establish, I mean, this system is trend signaling in order to establish safety transportation. So as we know, a couple of days ago, earthquake is coming in Java Island. We have some procedure to identify condition of railway tracks after the earthquake to avoid railway accident. Is this maybe already included in the system? Maybe that kind of question. Thank you for your explanation.
Yeah, for the kind of disaster, actually, like earthquake or flooding, actually, it is not in the it's not embedded in the signaling system, but it can be inputted to the signaling system. So we have the other system, we call it DPS, this disaster prevention system. So DPS, that kind of normally like urban or high speed, they have what do you call it? They have their own disaster prevention system, and then we interface to the signaling system. What I call it OCC. So give some indication. Let's say if some earthquake happen and it automatically generate some signal, and the signal do how to like reduce the speed of the train or even to stop all the train. So that is in that is the what happened what now in the world. The system we have in the world, but never disaster prevention system will be embedded in the signaling system, because disaster prevention is very complicated system, and it until now there is no DPS system which comply to SIL 4, because it's very complicated and no. So normally have some intermediate people who interpret if there is some signal generated by DPS system, disaster prevention system, and some operator have to do action to signaling. Even it's only push one button. But until now it's never been automatically. But of course it depends on the regulator. If we depend on the regulator, in this case of course Ministry of Transport, Minister of Transport, who decide that whether it will be intermediate between some operator or automatically shut down or automatically go to the signaling. That's
Okay, thank you for your question. I think for your answer, I think that's quite clear. We have also one question from Dr. Yuyu Wahyu. So Yuyu Wahyu, you can ask the question directly as well.
What is the question?
No, there is a. I mean, I will encourage Dr.
Okay.
Yuyu to ask the question directly if he is available. If not, I mean, maybe I will read it. So, Dr. Yuyu Wahyu has two questions. The first one is how to integrate the signaling system with various products. The second question, what is the percentage of error in the signaling system made by land industry?
Can you say it again? I'm not quite clear.
Okay, maybe the first one.
Yeah.
How to integrate the signaling system with various products?
Oh, okay. I answer this one first, yeah.
Yes,
So
sir.
yeah, of course, this is the various product. Why you say various product? Because it's come from a different vendor, and because vendor they have their own it's proprietary, their own standard. It's not open. So that is the solution we give to the railway, yeah, to the railway now. So let's say if some lines already installed by some product, the next line will be dead, will be continued dead, and its commercial aspect is not good. They can they can increase the price something. We cannot control the owner cannot control the price. Yeah. So what we here is using if like the Ethernet, Ethercat, yeah, Ethercat, safe Ethercat. Safe Ethercat is communication standard. Yeah. So we can do so even though some line already implemented by some product, and because there is open platform and open standard, yeah, so it can be the other vendor. So they will be more price competitive. Yeah. So this is the best thing. One of the value also from solution we give to the customer. So that is, yeah. Of course, for some other product with its proprietary, we cannot do that. Yeah, you have to contact the original vendor to integrate that. But in here we are freely because everything is open and standard. Yeah. Please for the next question, Pak.
The second question is, what is the percentage of error in the signaling system made by land industry?
I think it's not land or not, but every supplier have to meet with the EN. Yeah, have to meet with the EN standard. So that is the standard now using in all over the world. Yeah, like SIL4. So you see the tolerable hazard rate is between 10 power minus 9 and 10 power minus 8. The tolerance should be in that value. Yeah. So this is not from it should comply. Yeah, it should comply from that by the EN. Yeah, comply to EN.
Okay.
Okay,
Maybe
thank you.
Okay, Mr. Yu, is that answering your question? So I suppose so. So maybe I have one question for you, because now the question is this system also already or will be implemented in other railway system in Indonesia? So now maybe this is like more a subway or in the side train. So is it possible for, I mean, any other type of railways, like, for example, intercity railway, something like that?
Yeah, okay. The idea of this is, the idea of the system is, if you see now, Microsoft and Apple, yeah, Macintosh, yeah. So they dominate all the software in the world, yeah. And they're big enough, they have a big R&D for that, yeah. So how do you compete with that? Yeah, how do you compete? They're already big. They're already big. We cannot compete with them. Even like PT Land, I think it's very hard to compete with the well-established multinational company. The idea of this is like this. If you see now, if you see Android and Linux, they put, what do you call it? They put open platform. Yeah, they offer it free to the world, because he know that he himself cannot fight with the Apple or Microsoft. He cannot fight with that. But if he opens some, he gives something to the world and ask all the world to participate in that, participate in that value, in that OS, so it can compete. So we see now like Android. So Android now available in many Android phone and Android because it's open. It's all the world participate in that. So this is the idea. So this system is generated by PT-Land with some. The idea is coming from PT-Land, the main idea, and then we offer to the German company, as you said, Micro and Duagon, which is now merged with Duagon, and we open that because how to compete with well-established vendor, multi-vendor. So we open that, and now many in Korea, in China, in Russia, and in Japan, they now, most of them now follow this. So we have now more friends, So that is why now develop many of the cards, many of the product now, So that is the idea. This can be implemented in high speed. This is because this is the open platform. This use the latest technology compared to the some product now already developed by multi company. Is using maybe like 10 years technology, 10 years before or 15 years before. But this technology is technology now. If the speed and the performance and everything, so it will be is very faster and more robust. Does that answer your question, Pak?
Maybe the question is more about, for example, like we have now the fast train from Bandung to Jakarta. Are they using this kind of system, or they are using like different kind of system, and then whether your system also will be implemented like in normal railway in the whole Indonesia? Because what I see now you have shown that it has been used for like a SkyTrain to the airport, right?
Yeah. So it will be more in the commercial part. So like high speed. Of course, this can be used in the high speed. The hardware performance is much better than what they have now, the ETCS or CTCS, much more advanced than that, But in the commercial, we cannot push because it's come from the China and Indonesia, something like that. So we follow some commercial, So that is the problem. But now I think the system we have the system we call it TKDN, the local content. So this is the only system in Indonesia with local content, So this can be national strategic product, So in the mainline, we already like 90% in our mainline, Indonesia mainline, and we already implement this almost in 90% of our mainline system, and we just awarded for some railway using the system in the Philippines, in Manila. And Bangladesh already, I think we get three times contract for Bangladesh, and now we're looking for other in the regional or in the global market.
Okay. Okay, Mr. Linus, thank you very much for this discussion and also your presentation. I think there is no more question, and I will summary. We have seen that you have show us this what also called open hardware platform, which will reduce the cost, and then it will also give us a quick and easy part to obtain for installation as well. We can get all this installation easily, and then will provide us all this flexible, faster, and cost-efficient railway signaling system. And also, encouragingly, this is already implemented in Indonesia and in other parts of the world, as you said. So as a conclusion, I think we will just say thank you to your presence and your presentation. We will give you this token of appreciation, and hopefully this will also open the collaboration between PT-Land, more collaboration, and also National Research and Innovation Agency BRIN. And that's all from me. I think I will return the floor to Ms. Adita, the MC.
Thank you, Pak. Thank you.
Yeah, thank you, Pak.
Yes, thank you to Dr. Yulia Firdaus, and also thank you to Dr. IR Linus Andor Maulana Sijabat. Next, we will have a morning break until 10:45. After that, we will proceed to the first parallel session. The 3 parallel sessions will be conducted in the breakout rooms. Our host will first assign presenters who are presenting in the respective session based on the program schedule. For the rest of the participants, you are free to move between rooms by clicking the breakout rooms to join the available rooms. Some reminders for presenters that has also been outlined in the guidelines. 1, keep the naming convention according to the guidelines so our host can monitor if any presenters are in the incorrect rooms. 2, we encourage you to keep logged on even during the breaks. 3, for the presenters that are in their assigned sessions, please turn on their video for the whole session, including when you are not presenting. 4, please be reminded it is compulsory for presenters to be present at their respective Q&A sessions. Also, do not forget to fill the attendance form as the presenter when you are in your own session. 6, please have your presentation slides ready for the Q&A session. For all the participants who want to ask some questions during the Q&A sessions, please use the raise hand menu that can be accessed from the reactions menu in your Zoom application. We also welcome honorable guests and keynote speakers to join our presentation sessions. The presenters will be directly assigned by our host according to the program. After the first parallel session finishes, the lunch break will take place until 1 p.m. for the second keynote talk. We encourage you to stay logged on during the breaks. I would like to thank all of the speakers, panelists, and attendees for taking the time to be here today. I look forward to an exciting and productive day. Thank you and enjoy the conference.
Recording in progress. Recording in progress. Recording in progress. Recording in progress.
Warts.
Assalamualaikum warahmatullahi wabarakatuh. I am Ted Kurniawan as a moderator in this parallel session. Today we will talk about control system, robotic, and mechatronics. And in this session we have 5 presenters. Oh, sorry. Anyone can hear me?
Yeah, yes, can hear you.
Okay, we will start our parallel session. I am Dad Kurniawan as a moderator in the session. Today we will talk about control system, robotic, and mechatronics. We have 5 presenters with different topic, and I think all of them is interesting. The first presenter is
million kilometer square of tropical ocean.
Please, technical team, please don't interrupt my voice. Okay, we have 5 presenters. The first one is Dr. Purwadi from BRIN, and the second one is Ricky Dwi Puryanto from Ahmad Dahlan University, and the third one is Eric Edi Wiguna from BRIN, and the fourth is Maidrim from BRIN, and the last one is Sarjono Trihatmo from BRIN also. So before we start our discussion, we will inform you that all participants and presenter, please don't leave this room until finish, because we have capture session. And then please don't forget to fill attendance form. The attendance form will be shared in the chat box. And for the audience, if you have any question, please using question function or type your question in the chat box. And the time is already, so we are going to the first discussion. The first presenter is Dr. Purwadi. We'll talk about non-linear injection control of isolated DC to DC converter for cable-based C-bit observatory platform. So, Dr. Purwati, this is your time. Please, technical committee, please play the video presentation of Dr. Purwati.
Good morning, ladies and gentlemen. In next few minutes, I would like to describe our research on power supply of subsea monitoring platform entitled Nonlinear Injection Control of Isolated DC-DC Converter for Cable-Based Seabed Observatory Platform. As you know, Indonesia is an archipelago country with 3.3 million kilometers square of tropical ocean and also a gateway of water transfer between Indian Ocean and Pacific Ocean. A lot of micromaterials come from both sides. So it is important for Indonesia to have a reliable and flexible ocean monitoring system. It means it can collect data for a long period of time and different kind of measurement depending on research occurred. So we envision an ocean monitoring system as shown on the right, where power and data are transferred from shore station through subsea cable. We have already one pilot project for such system deployed at north of Labuan Bajo City in East Nusa Tenggara. There are two platforms, we call it Ocean Bottom Unit or OBU, placed on the seabed. The first one, the closest to the shore, is about 34 kilometers from shore at 2,110 meter depth. The second one is about 54 kilometers from shore at 4,100 meter depth below the sea surface. The power supply unit in shore station is a current controlled power supply, such that we pass through the cable, so the lowest power loss. Today, the current is about 18 milliampere. In OBU, the current is converted to the voltage through Zener diodes and DC-DC converter. However, the current that flows through Zener diode depend on the load. If there is no load, then all 18 milliampere current will flow through the Zener. Also, if the load in the other OBU needs bigger current, for example 50 milliampere, then all that current, 50 milliampere, will flow through Zener of the OBU that has no load. So the Zener will become hot. That is the reason of our research. So we propose a current fit isolated DC-DC converter. The topology of converter is shown at the left side. We call S12 is the status of controllable switch S1 and S2. S34 is the status of controllable switch S3 and S4. When S12 is on, then the current on primary side of transformer IP is positive. But when S34 is on, then the current on primary side of transformer is negative. Because the system is supplied by current source, we should avoid that all switches become off. So we use the overlap turn-on strategy, where it is possible to have all switches on Short circuit occurs, but since the current is controlled, then the switches are okay. They are not getting fire. As you can see, there are diodes in secondary winding of transformer. So the output current IO is always positive. We can see that the main model dynamics of the system, that like the output voltage in function of duty cycle, D, is linear. Duty cycle is ratio when the switch is on to period of switching. So we propose the feedback control algorithm, proportional integral with a nonlinear compensation as duty cycle, as you can see in the last equation in this page. There are also coefficient K1 in the proportional parts and K2 in the integral parts in order to tune the control algorithm. The model and the control algorithm is verified using MATLAB Simulink Simscape software package. Simscape is used so that we can do a physical system simulation, as shown in the upper part of this picture. Not only the functional multi-domain system using MATLAB Simulink that you can see in the lower part. Theoretically, the system is stable, but not controllable all the time, especially when the output current is 0. It means when the system starts or when there is no load at all. So for that, when powering or starting the system, we fix the duty cycle during certain time and run the control algorithm after, as shown in block B. The compensation is calculated in block A. We put output capacitor 28 microfarad and the switching frequency at 10 kilohertz. We also increase the load 4 times or 400% at time equal 0.003 or at 3 milliseconds. We can see in the left curves that the system behaves as a first order with response time proportional to the output load. Response time decrease when load decrease. The right curve shows the response of system faster when we define the constant K1 and K2. We do also simulation when two converters are put in series without coefficient K1 and K2. So we see every system behave as it is independent one to another and converts to the desired output voltage as first order system. The desired output voltage is a 24 volt DC. So as conclusion, the simulation shows with the proposed nonlinear injection, the system behaves as a linear system for different load and after a load changings. Also, the simulation proved that the system is stable and independent even when the converter are put in shunt. The result remain the same. For the future work, we would like to develop the prototype of this converter and do experimental testing in our laboratory to prove that this control algorithm can linearize the system. We also would like to develop a new control framework in order to define the coefficient K1 and K2 in this control algorithm proposed. That's all my presentation. Thank you very much for your attention.
Thank you very much, Dr. Purwadi. Any question from the audience? And maybe Mr. Budiman, you have any question to Dr. Purwadi? No. Oh, okay. I think I have one question to your research project. Based on your simulation, how about sea wave? This is included in your simulation. Sea wave effect. Dr. Purwadi, please unmute your mic.
Okay, thank you for the question. So the question is about if a sea wave impact to the to the system, yeah.
Yeah.
Yes, but we think that sea wave will not be mostly impact our system, because C in our system is a return current. So there's only the resistance of C is not quietly different with the current wave, yeah, with the speed of current. So I think it is not much difference, the result, if the sea wave is higher or not. Thank you, Pak Dayat.
Okay. Maybe second question about your method. If possible to implement like neural network control, maybe in your system.
Well, that is another method for controlling the system. Yeah, yes, of course, there are a lot of paper would like to control such system with neural network, but I think for our application, this is seabed observatory platform. Yeah, it is very expensive system. Very expensive system. If something go wrong, then we have to rent a ship, a cable ship, in order to pull up that system. So we think that we have to be more conventional. I think we are more sure about what happened in this power supply unit. So if your question if it is possible, yes, of course it is possible, but in our case where the reliability is utmost, we prefer to have a more conventional and certain control algorithm. Thank you, Pak Dayat.
Okay. Thank you, Dr. Purwadi. Any question from other audience? If not any question, I think your time is up, Dr. Purwadi, and thank you very much for your sharing with us. And now we can moving to the second presenter. The second presenter is Mr. Ricky Dwi Purianto. He will talk about robot-based design of collision-free trajectory of wheeled mobile robot using artificial potential field. Mr. Ricky Dwi Purianto, Are you ready?
Yes, I'm ready.
Okay. Please, technical team, please play video slide from Mr. Riki Dwi Puryanto.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Before I start my presentation, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Before I start my presentation, I want to introduce myself and my research team. My name is Riki Dwi Puryanto, and my research team are Ika Wandari, Alfian Ma'arif, Haris Imam Karim Fatur Rahman, and Iska Aditya Rosyadi. Today I will present about our research with the title of Webot-based design of collision-free trajectory of wheel mobile robot using artificial potential field. There are several points that I want to explain at this moment. When the first is background of the research, and then path planning algorithm, and then contribution, proposed method, result and discussion, and the last is conclusion. For the background, we know that today we live in Industry 4.0 era. There are several frameworks that make up the Industry 4.0 era. One of them is advanced robotics. The implementation of robotics in daily life covers the field of industry, health, military, and the others. There are two types of robot called fixed robot and mobile robot. Mobile robots are mostly implemented in our daily life to help us to complete our work. Mobile robots are generally developed to be able to work autonomously. However, the main problem in implementing an autonomous mobile robot is the navigation system. We know that the navigation system for the robot consists of three main components. On the first, mapping, and then localization, and the last is path planning. The combination of these two or three components produce the new research area of the navigation system. For example, mapping and localization produce a research area of SLAM, or simultaneous localization and mapping. And the combination of the three components produce the integrated approach research area. In this navigation system, path planning is important to implement in the autonomous mobile robot, because it can be reduce the financial investment and development time. One of the type or algorithm in path planning that use in robot or autonomous mobile robot is artificial potential field path planning algorithm. How artificial potential field or traditional artificial potential field work can be seen in the picture. Could generate an artificial attractive potential field to attract the robot to the goal. In addition, the obstacle generates an artificial repulsive potential field to push the robot away from the obstacle. The attractive and repulsive potential field can be equation can be seen from the slide. From the attractive potential field, or UATT, attractive is 0.5 multiplied by Ka, or gain, attractive gain, and multiplied by Euclidean distance between robot and goal powered by 2. And repulsive potential field, or UR, will be activated when the robot near the obstacle or in range of R, R is safe distance from the robot. DOR is Euclidean distance between obstacle and robot. This is the equation of the repulsive potential field. The drawback of traditional artificial potential field is a robot can be trapped in a local minimum condition. So the researcher have modified the traditional artificial potential field. The modification, one of the modification is modified artificial potential field that use Euclidean distance between robot and goal powered by N in repulsive potential field function in here. In this study, aims to integrate and implement the path planning algorithm on the wheel-mover robot kinematic model and prove it into the simulator, namely WeBots. For the proposed method, we use the mapping, the global mapping, to define the initial position, goal position, obstacle position in the memory of the robot. And then for the localization, we use encoder that the data used in the kinematic model of wheel-mover robot. And then the path planning algorithm in here, we can generate or calculate the fx and fy of the total potential field function. Fx and fy is a negative gradient of the total potential field function. The total potential field function is addition of U attractive or attractive potential field and repulsive potential field. From the kinematic model of wheel-mover robot, we can get the current position of the robot, or X and Y. So the last, we can get the robot motion or trajectory, safe trajectory, that collision-free trajectory get away from the obstacle. For the system, we start from the initialization of some parameter like initial position, obstacle position, goal position, and the gain of the some parameter. And then it used to calculate the fx and fy value of the modified artificial potential field algorithm. And then after that, we calculate the position of the robot, the current position of the robot, or X and Y, based on a kinematic model of wheel-mover robot with the type of differential drive mover robot. After that, we can get the robot position, X and Y, and robot angle, or heading angle, theta. When the robot reaches the goal, it will be N. And if the robot is not reaching the goal, it will come back to the initial initialization and continue to calculate fx and y and etc. From the result of my research and our research, we can see from the video. In here, from the first environment or first test, we use the SAROC simulation. SAROC is symmetrically aligned robot, obstacle, and goal. The robot in initial position and obstacle and the goal in line in symmetrically. So this is the local minimum. It can be produced local minimum condition, and the results show that robot can avoid the obstacle with the error from the goal less than 0.01, and the distance traveled by the robot is 1.76 meter, and the robot travel time from the initial position to the goal position is 273 seconds. For the second test, we use the goal non-reachable due to obstacle nearby. This is the obstacle very near from the goal. So this is the second problem in local minimum, or we can say a GN run problem, goal non-reachable due to obstacle nearby. From the simulation, we can see that the robot can avoid the obstacle and reach the goal. The distance between the obstacle and the goal is in the coordinate is 0.2, the nearest distance, and then the traveling distance from initial to the goal is 317 seconds, and this error is less than error between robot and goal less than 0.01. For the conclusion, in this study, the modified artificial potential field algorithm has been integrated into the wheel-mobile robot kinematic model. The test results show that the trajectory produced by wheel-mobile robot is able to reach the goal and is free of collision. And the Euclidean distance of robot to the goal powered by n parameter reduce the value of the repulsive potential field generated by obstacle located very close to the goal. However, the gain and ICC parameter setting need to be investigated to reduce robot oscillation when avoiding the obstacle. Okay, it is enough for my presentation. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Suaranya belum kedengaran, Pak Dayat.
Okay. Sorry. Thank you for Mr. Ricky for your next presentation. Any question from the audience? Maybe Dr. Purwadi have a question. Oh.
Yes, Pak Dayat, thank you.
Yeah.
Mr. Ricky, thank you very much for your nice presentation. I would like to know this algorithm is pre-calculated, yeah. I mean, before the robot move, the algorithm is already calculated or not. I think or it is a real-time algorithm. Thank you, Pak. Masih di mute, Pak Riki.
Okay, thank you. I'm sorry. Yes, this algorithm is a time algorithm that implemented in the mobile robot. So we use data from the encoder and locally sensor that in the robot, and then the data used in the path training algorithm, and then calculate the negative gradient of the fx and fy to use to determine the heading angle of the robot.
So how the robot know about the position of obstacle then?
Okay, for the mapping to determine the obstacle, goal position, and initial position, we include the data in the memory of the robot. So this is called a global mapping.
Okay, so the obstacle is still there, yeah. I mean, it's not moving, or we cannot add a new obstacle when the robot is already running, yeah.
Yes.
Okay,
yes. Thank you, Mr.
Okay. Maybe the last one, Mr. Sarjono.
Okay, thank you, Mr. Dayat. Is my voice here? Hello, testing.
Yes, Mr.
Yeah, because
Sarjono.
I have heard noises around me. Okay, it is very interesting to explore the artificial field path planning. It is an old method, but yeah, I think it is developed and more developed by researchers. My question is actually similar to Mr. Purwadi, yeah, with Mr. Michael. So I just, yeah, short question: Is it algorithm is applicable for the dynamic environment for the obstacle? For example, when the obstacle is, for example, a person that, for example, move on amongst the environment. Thank you very much.
Okay, thank you, Mr. Sarjono. I think it can be implemented into dynamic environment, but we must use accurate sensor for the robot, and I think we can make a mapping of the environment, so the robot can detect the dynamic obstacle. For example, a human. I think it is possible to implement it in the real implementation, especially in dynamic environment.
Yeah, just a short question. What I mean with the dynamic here, we focused on what is the what is that? Local minimum. Yeah, local minimum.
Yes.
Now,
yes.
if the dynamic environment is dynamic, so the local minimum, it can be also disappear. Yeah. How do you cope with that?
Okay. For the explanation about local minimum in this research, this is two type of local minimum. It produced when, for the first test, when the robot obstacle and goal in a symmetric position. This is produce the local minimum in front of the obstacle. This is the first type of local minimum in this condition for become a drawback of traditional attributable potential field. And the second is when the obstacle very near from the goal. So if we use dynamic environment, I think the local minimum to form cannot be happen, because the probability for the position, like for the test, robot, obstacle, and the goal in a symmetric line, for example, it is very low probability.
Okay, thank you very much, Mr. Rizky, yeah, Mr. Dayat.
Yes.
Thank you very much. It's a nice discussion for all of the audience. If you have any question, you can send a direct email to Mr. Rizky. Okay, before we going to the next presenter, to all presenter, please fill the present form. It's available in the chat box. So we can going to the next presenter. The third presenter is Eric Ediwiguna from BRIN. He will talk about sampling time value determination method for design a real-time control system with non-deterministic time elements such as rotary encoder and SPI. So Mr. Eric, are you join with us? Okay. Please take it.
Thank you, Chairman. Today, I would like to share with all of you about our result on sampling time value determination method for designing a real-time control system with non-deterministic time elements such as rotary encoder and SPI. Outline. Outline of the presentation is organized as follows. Section 1 is introduction. Section 2 presents the modeling of open-loop control system architecture. Section 3 describes the method we use to determine the sampling time value which result and discussion are presented in Section 4. Finally, in Section 5, a conclusion is drawn. Introduction. In our laboratory, we have been doing research on the development of autonomous electronic vehicle. On the many areas, we focus on a real-time control system. So, traffic are full of certain parameters. To mitigate the problem and increase the safety and reliability of the vehicle, a real-time control system for the autonomous electric vehicle is needed. Real-time system can have non-deterministic time elements which can affect the system performance. Some non-deterministic time elements are communication latencies, unpredictable sensor activation, response to the human user, or environmental conditions. In this paper, we use in fact the latencies in SPI communication between devices and relays into Arduino microcontroller in fetching and analyzing data from sensors. One of our objectives is to study the real-time execution of a motor position and control with rotary encoder as a diagonal sensor with SPI uses used for communication. 2. Modeling open-loop control system architecture. In continuous control design, analysis can be carried out using continuous control design analysis can be carried out using the Laplace transform. The plan PS and controller CS are given by YS equal to PS US and US equal to CS ES. The transfer function from the reference to the regular signal is determined by sensitivity function SS. ES divided by RS equal to 1 plus 1 plus PS CS. In contrast, the transfer function from the reference to the output is given by the complementary sensitivity function TS. And YS divided by RS equal to PSCS divided by 1 plus PSCS. For example, a commonly used professional integral differential PID controller is represented as continuous controller using the Laplace variable in 5 CS equal to KP plus KA plus divided by S plus KDS equal to KPS plus KE plus KDS quadrat divided by S. KP, KA, and KS, KP, KA, and KD denote the proportional integral differential gain values respectively. The primary controller into computer digital controller, computer-based digital controller, we need to convert the continuous controller into a discrete controller by transforming the transfer function from S domain or continuous to Z domain or discrete. One method is the trapezoidal or twisting transformation, S equal to 2, Z plus 1 divided by TS, Z minus 1. 3. Sampling time value determination method. A motor encoder is used to monitor motor's rotation. The rotary encoder TP is 60 mm diameter hollow shaft TP incremental RE that produce A, B, and Z pulse signals with a resolution of 5,000 pulses per rotation. The data from the rotary encoder is directed to microcontroller 2 to be analyzed and transformed into analog signals. The main control MISI-1 to data from MISI-2 on hydraulic pressure or HP. Analysis result will be sent to the digital potentiometer to change driver voltage and to rotate the motor. In control MISI-2, timer-based interrupt is used to determine sampling time. One sampling time TS consists of 4 elements. TS equal to T1 plus T2 plus T3 plus T4. P1 is the period to read input. T2 is the period for processing all signal and calculating the control command value UT. T3 is the period for inserting the command signal to the DC motor driver, and the T4 denotes the margin time. In the figure, we can see how sampling works. The solid black upward arrow is the control interrupt. The arrow post interrupt is represented by the red broken outward arrow. The symbol K and TS denote the sampling counter and the sampling period according to the controller's interrupt. The interaction between controller's time and rotary encoder's pulse interrupt is that controller's interrupt occurs every sampling time, while the area pulse interrupt occurring time depends on the angular speed of the motor. As for the communication and digital potentiometer, we use a digital potentiometer to control the motor driver. The digital potentiometer that we use is AD5209 at 256 or H-bit position the PM that can act as voltage difference. 0 position being the lowest voltage and 255 position is the highest. The digital potentiometer is random access, thus a position can be reached instantly without the need to be slowly decremented or incremented from the previous position. Digital potentiometer communicates with SPI. Every SPI message consists of 1 byte data and message burst that will be saved in the register. The digital potentiometer will only execute this message when the GS pen is deactivated. Result and discussion. We carry out experiment to measure the length of time consumption of the following three processes. The angle input signal Y1 T from the RE and process input signal Y2 T from the HP sensor. Calculating control signal UT, sending the signal UT from the signal controller MEC1 and DC motor driver. Figure 4 and Figure 5 are flow chart of the program subroutines and microcontrollers. As one can see in Figure 4, in MEC1, we use timer interrupt. Every ATS time, program will report its condition. Meanwhile, in MEC2, we use trigger interrupt to capture pulses from rotary encoder, as one can see in Figure 5. As mentioned before, rotary encoder pulses depend on the speed of the motor. We carried out two experiments to see the characteristic of the rotary encoder pulse signals. Figure 6A is the pulse signal with the RA rotaries at 41 plus 41.7 RPM. While Figure 6B is when the rotary encoder rotates at speed of 19.9 RPM. As one can see, the faster the motor rotation, the closer the pulses will be. Keeping track of the deterministic pulse count from the rotary encoder needs dedicated interrupt subroutines. We can house the controller or trigger source and time contentions with other subroutines. To solve this problem, a second dedicated microcontroller is used so that main controller can be free to perform other functions. Next, we implemented analog signal processing by MEC1. The analog signal in Figure 7 was measured at the brake pedal assembly in CV. The signal was produced in the following action. The brake pedal was pushed from the initial angle of 0 degree to 10 degree. The brake pedal was held steady at 10 degree position for a certain amount of time. Then went back to the initial angle of 0 degree after releasing the foot pressure on the brake pedal. The section made the motor go back and forth. It means CW and CCW rotation are executed. We set the gain of the analog signal of the rotary encoder as 0.24 per degree. After measurement, we found that the total processing time of the bulk style analog converter inside MEC2 was around 320 nanoseconds. We set up a data logger with a sampling time of 2 milliseconds for calibration. Based data from data logger, we can recognize any delay of the processed signal from the original signal. By using oscilloscope, time consumption for ADC reading of analog signal YT, calculation of simple multiplication UT equal to 3 divided by 4 YT, and sending UT through the AC channel was measured 4.1 microsecond, 1.2 microsecond, and 4 microsecond respectively. Finally, we examined data processing in the PM. First is data transfer sheet. We conducted experiment with SPI speed of 8 MHz, but turned out the PM produced wobbly voltage. It can be seen in Figure 9. This wobbly happened because digital potentiometer misinterpreted commands due to incompatible speed. After several experiments, we found that the PM SPI speed is below 1 MHz. Next, we experimented the response capability of the PM in executing commands. We reached the time interval between two instructions inside the main controller MEC1 and observed the output signal. We found that the fastest interval between two instructions that the PM still work properly is 2 microseconds. Finally, we measured the time delay of the output signal due to processing inside the PM. We found that delay time is almost 2 microseconds from this experiment result. Conclusion. In this study, some non-deterministic factor inside our open loop system investigated. The following conclusion can be taken from experiment. The total processing time of the boost to analog converter is around 320 nanoseconds. Processing time inside the controller, calculating the control signal from reading signal through the ADC pin, executing a simple multiplication, and sending calculated value through the ADC pin is 9.3 microseconds. The DPM SPI speed is found to be below 1 MHz, and the time interval in DPM is 2 microseconds. The consumption time inside the main controller reading the signal by the ADC is 4.1 microseconds, executing a simple multiplication 1.2 microseconds, and sending the control signal by the AC 4 microseconds. When the calculation time of the controller algorithm is T2, we have to set the sampling time TS equal to T2 plus 0.01 millisecond or more. From the experiment analysis results, for designing a real-time processing control system of the brake, we obtained the appropriate sampling time TS value of 25 milliseconds. That was our presentation, and thank you for your time.
Thanks, Mr. Eric, for your presentation. Any question from the audience? No, no one present. Okay, I have a question to you about why you choose SPI rather than Canvas. Mr. Eric, your audio is we can hear your Okay. Mr. Eric, your audio is troubled. Hello, Mr. Eric. Your audio still we cannot hear your voice. Mr. Eric, I'm sorry because we have a limited time. So my question you can answer maybe send to me to a direct message, I think, because we have a limited time. So we can end your presentation. I'm sorry, very sorry. Okay, we are going to the next presenter, I think. The first presenter is Medrim Mirdanis. He will talk about the development of human-machine interface based graphical user interface for telecontrol system of a ship mounted to GOF manipulator. So, Mr. Medrim, are you joining with us?
Yeah, Mr. Laya, thank you.
Okay.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Midri Merdanis. I am from Research Center for Smart Mechatronics, National Research and Innovation Agency. Today I want to share our research with the title is Development of Human-Machine Interface Based Graphical User Interface for Telecontrol System of a Ship Mounted to DOF Manipulator. And this is the authors of this paper. Midri Merdanis, Dr. Edward Yasid, Rizky Andri Ardiansa, and Yaya Sulaiman. This is the outline of this presentation. It consists of 5 sessions: introduction, IM design, result and discussion, concluding remark, and reference. Before I explain about the IME software, let me discuss a little about the turret. A turret, are also known as RWS or RCWS, Remote Controlled Weapon System, is a remotely operated weaponized system often equipped with fire control system, which can be installed on a ground combat vehicle or sea and air-based combat platform. And this turret mechanism can move through DOF, through degree of freedom or through axis, azimuth and elevation, and then remotely operated via cable in the control box, the control room. In the left side is our design turret prototype. And in the right side is the example of the turret from the other country. Let's move to HMI. HMI is human-machine interface. It is an interface that allows human to interact with machine. And one type of HMI that is widely used today is an interface software based on a graphical user interface. And this type of HMI is easier to be operated by operator than text-based or command-based HMI. In this slide, we can see that the turret consists of several sensors and actuator, and all the sensor and actuator can be monitored or can be controlled simultaneously, real time, and all the process in this HMI software, including the running object tracking based on image processing algorithm, must be run simultaneously to real time. So in this paper, we focus on two parts of optimization. First is how to organize, how to monitor, or how to control all the data from sensor and actuator real time. And second is how to make all process can run simultaneously, real time without hang, lag, and overlapping between process. This is the block diagram of proposed telecontrol system. In the console box, we use a PC or workstation as data processing, and we use laptop for experiment, and it will be connected to via wired cable to the turret mechanism. In this turret mechanism, we use a microcontroller Arduino Mega as a data processing, and it will be connected to several sensor and actuator, as can we see in the block diagram. This is the real component we use it in this research. It consists of color camera, thermal camera, IMU, LRF, joystick, horizontal and vertical motor, and electrical circuit. This is the all component and the communication media and pin we use it in this research. In this table, we can see that several sensors can be directly connected to the PC or laptop, but the other sensor must be connected via microcontroller. To create a HMI software in the PC or laptop, we use a Kitty IDE, but to create a microcontroller software, we're using Arduino IDE. This is the flowchart of the system. In this flowchart, we can see that this turret can move in two modes, first in manual and second in automatic. Manual, we can move the turret using the button in the HMI software, or we can use the joystick. And for the automatic mode, in automatic mode, the operator must select the object first, and the system will give an order to the turret mechanism to follow that object using object tracking algorithm. And all the process must be run together. So in this research, we propose two parts of optimization. First is how to organize all the data real time. So we propose the data communication technique, which divide the data using identifier. And second, how to make all process can run simultaneously without hang, lag, and overlapping between process. We propose the data processing technique using multi-thread or parallel processing. This is the schema, the diagram of the multi-thread or parallel processing in data processing technique. As we can see in this slide, in multi-thread or parallel processing, all the process will be divided into several parts, and every part will be run in the different thread of the CPU. So based on our experiment, the program, the HMI software can run smoothly without hang or lag. And if we use the sequential mode, all the process will be run sequence one by one. Based on our experiment, it can the software can become lag or hang. So we use a multi-thread to solve the problem. Second optimization is in data communication technique. To organize, to monitor, to control all the data simultaneously, real time. So we use this equation X and Y, where notation X is a data identifier and Y is the value of the data. And in this table, we can see the detail of the identifier we use in this research. For the example, if we want to give a value, the speed value of the vertical motor or elevation motor, we use the identifier K. For the example, K 100. So we give a speed value 100 to the vertical motor. This is the result and discussion. As we can see in this slide, this is a snapshot of our HMI software. Based on our experiment, we can see that all the data such as color camera, from thermal camera, LRF, and all the button can run properly without lag or hang. In addition, we use two tools, Task Manager and hardware monitor, CPU ID hardware monitor, to take a deeper look at data processing of this HMI software to see the CPU utilization or CPU load in every thread of the CPU. When we use the Task Manager, we see the CPU utilization, and this is the average of the CPU utilization. We test 5 load sequence, and as we can see in this slide, and this is the result. This is the detail of the CPU utilization in every thread of the CPU. The CPU consists of 8 threads, and the detail can be seen in this graph. This is the experiment of the data communication technique. Several experiments have been performed which show that the data communication process can run well without any hang or lag, and this performance has been indicated by the good response of the 2 DOF manipulator to the microcontroller via terminal in the PC and laptop. And this is experiment to monitor and to move the turret using a laptop and the PC, and the detail I will show the demo video. This is our turret mechanism. This is elevation, and this is azimuth. As we can see in this video, that the HMI software can display the data from the turret. For the example, the camera RGB and camera thermal, and etc. This is the second video. we can see that the turret, the HME software can move the turret. For the example, the elevation using the button from the HME software. And this is we're using a joystick to move the turret. Conclusion. The development of human-machine interface based on graphical user interface for a chip mounted to the manipulator telecontrol has been proposed in this paper. And the HME software is installed on a PC or laptop and designed for easiness of operator. The feature cover real-time control and monitoring as well as object tracking system. And data processing and communication technique are also proposed to make the HME software run effective without overlap or hang, and based on the experiment result, so that the manipulator system control process is able to run well in the real time, and data communication process also work effective without any hang or lag, as indicated by the smoothness motion of manipulator system and the appearance of the request data when it's operated via HME software developed. However, the detail and the in-depth experiment are required for further analysis and recommended as a future work. This is our reference. Thank you.
Okay, thank you, Mr. Maidrin. Any question from the audience? No question. I have one question for you. Regarding your presentation, I can see the method of your control system. This is maybe the out of your presentation, yeah.
Yeah.
Maybe you can tell us about what the next control system that you implement in your system, like PID or something like that.
Yeah, thank you, Mr. Dayat. Yeah, in this research, we have been developed two types of control. One is PID, PD, and second is fuzzy. But it will be discussed in the next paper. In this paper, we focus to show the software development method technique in the HME software development. Yeah, thank you.
Maybe from Mr. Dr. Purwadi.
Thank you, Mr. Dayat. Yes, I have two questions. The first one about the software itself. So it is built using multi-thread methodology.
Yeah.
Is there any priority in this thread regarding the three threads that you have already shown? This is the first question. The second question is the speed of communication. You said that you use a new data load, identifier, and then the value. Is there the first one, the physical layer? What do you use as a physical layer? And the second one, the speed. How much the speed communication between your computer and turret? Thank you.
Yeah, thank you, Mr. Purwadi. The first question is about multi-thread. Yeah, before we have been developed the software using the sequential process, and based on our experiment, the lag and the software is not run well, so it's have a lag, some lag, and sometimes the button is not responding. So next we use the multi-thread process or parallel processing. In this paper, we use the ET library, eFuture, to implement the multi-thread or parallel processing technique. And based on our experiment, the lag, the software, the HMI software is running well without lag or hang. Yeah, and the second, the communication physical layer. The communication layer between the control box and the turret mechanism, we use the RS232. We use physical cable. So based on our experiment, we have been test the detail of the time of the real communication, but based on after several testing, we see it's fast, but the detail time we have in test several microsecond or like that.
Okay, so for the question, there is no priority between the thread that you have made. Usually we have a priority for the input. For example, the tombol or the button push button is a priority, for example, for the security reason or the safety reason. So yeah, it's just a sub idea for you. Thank you very much, Pak Midriam, Pak Dayat. Thank you.
Thank you.
Okay. Thank you, Dr. Purwadi and Mr. Maidin for nice discussion. Next, we are moving to the last presenter. The last presenter is Mr. Sarjono Trihatmo. He will talk about identification of potential electromagnetic disturbance at 1172 MHz in autonomous EV routes. Mr. Sarjono? Yep, okay.
Can you hear me?
Yeah, okay, good. Please, technical program, play the video presentation.
So good day, ladies and gentlemen. My name is Sarjono Trihatmo. I will present my research work entitled Identification of Potential Electromagnetic Disturbances at 2172 MHz in Autonomous Electric Vehicle Routes. This presentation consists about 10 slides and will finish in 10 minutes. So we begin with the introduction. The development of electric vehicles leads to the development of autonomous vehicles, since the autonomous technology is integrated better with electric engines. Autonomous cars use control systems, sensor systems, and navigation systems such as GPS receivers. All of these systems are based on electronic circuits that are potentially influenced by electromagnetic field. Electromagnetic field interference may cause electronic circuits to experience malfunctions. For example, a failure of a GPS receiver to deliver correct data may lead an autonomous car to a danger situation, such as experiencing a collision with obstacles. In order to avoid such a failure, then it needs to develop a motion planning that enables autonomous vehicles not only to avoid collision with obstacles, but also to follow paths along which the risk of being interfered by electromagnetic field is minimum. This presented research is a preliminary work for the next research on developing motion planning. For developing a motion planning, it needs to have a map that consists the characteristic of EM field. So in this work, we identify the potential electromagnetic disturbances in vehicles environment. So next slide. A source of electromagnetic field can be obtained not only inside electric cars, such as electronic instruments and inverters, but also outside electric cars, such as radio, TV transmitter, and also base transmitter stations. The increased use of wireless mobile and broadcast communication results in presence of potential electromagnetic interference source into the electronics components of autonomous electric vehicle. This experiment focuses on observing the electromagnetic field at the frequency of 2172 megahertz. This frequency was selected since it was trialed by Indonesian Ministry of Communication and Information Technology as a 5G frequency candidate. In this research, we use CISPR 25 standard documents to define the limit of electromagnetic disturbances. In the table, we can see that the electromagnetic field at 2172 megahertz is a potential disturbance if the measured peak voltage at the receiver antenna exceeds the value of 26 dB microvolt, or equal to the field strength with the value of 0.00002 volt per meter. So the area of measurement was made in a location inside the campus of the Center for Science and Technology in the suburb of Jakarta. The location is regarded as a typical area in the suburb. In the environment, there is a transmitter, 3-story buildings, and vegetations. In order to simplify the typical route in suburbs, only a circular route was chosen since the track already represents shadow and non-shadowed condition. We indicate section A, B as north track, B, C as west, C, D as south, and D, E as east track, respectively, while the pivot A, B, C, and D are the corner of each track. The 5G transmitter station is indicated with a red star. A control tower with 80 meters in age and about a 6-meter radius is indicated on the with a yellow circle. The measurement was made along the track circularly with point A as the starting point. Okay, the method of measurement was made by using the NADA field meter. The sampling time was set to 1 second. A person walked along the circular route while holding the field meter. So a distance of about 1 meter between samples can be obtained. Measurement of electric field is done 6 times along the circular track uninterruptedly with 480 to 500 measurement points per circular track. The average of about 9 neighboring measured electric fields in a location was calculated to obtain the local mean. So the result, in this slide, we can see the characteristic of electric field on the circular track. The y-axis is the value of the field strength in volt per meter, and the x-axis is the distance of measurement point to the reference point A, where A is the starting point. The characteristic of electric field on the north track is fluctuated and shows a maximum value of nearly 3 volt per meter. It is equal to 130 dB microvolt. While in the south track, the electromagnetic field characteristic is relatively flat and shows low values. The field strength on the east track is fluctuated but tends to increase from the south to the north. On contrary, on the west track, it tends to decrease from the south to the north. The next slide explains the phenomena. So the left figure is the environment surrounding the north track, and the right figure is surrounding the south. As it was explained before, that the transmitter station is located northwest of the measurement area. There is a location on the north track where the value is maximum. Starting from the reference point A, the northeast, the electric field begins to fluctuate because some measurement points are hidden by vegetation and some other not. The electric field shows the maximum in an open area. This is the area between control tower and vegetation. And then the electric field decreases in the area south of the control tower before it increases again and reaches another maximum in the next open area. In contrast, the electric field on the south track shows low values since the track is hidden by building and vegetation. Next slide. On the east track, in the left figure, since the transmitter station is located on the north of the measurement area, the field strength on the east track increases from the south to the north. The fluctuation on the electric field is caused by the presence of the trees and on the left side of the east track. So on the west track, however, the field strength decreases from the south to the north, decreases with decreasing distance of measurement point from the transmitter. It can be explained as follows. When we walk toward the transmitter from the south to the north, the transmitter begins to be hidden by vegetation. On the north of the west track, the right figure, the transmitter is totally hidden by trees. Okay, let's to sum up, potential electromagnetic disturbances occur in the environment around which there is a transmitter station. The results of the experiment also show that the measured potential electromagnetic disturbance values vary due to the surrounding vegetation, building, and electromagnetic infrastructures. In some locations, the field strength reaches a value of nearly 3 volt per meter, which is equivalent to the value of 130 dB microvolt. This value is very high compared to the threshold requirement that is stated in the CISPR 25 standard document, in which the limit is 26 dB microvolt. Even in the area that is surrounded by buildings and vegetation, the values may exceed the limits. Then, the design of an autonomous car must consider the potential electromagnetic disturbances. If a shielding is an option, then a shielding material with an attenuation of more than 100 dB is required. So, a safe trajectory planning is an alternative solution that can be made, where a safe trajectory can be defined as a trajectory along which the disturbance is minimum. So, thank you for your attention, and please feel free to ask me if there is a question. Once again, thank you very much.
Thank you, Mr. Sarjono, for your nice sharing information. Any question from the audience? No question. I have one question for you.
Please, Mr. Dan.
Why you choose that frequency to your research? What about the another frequency? as I know, in Indonesia, 5G has many frequency, I think.
Yeah, sure. Thank you very much for your question. This is a nice question to be discussed. Yeah, actually. So at the first, so we measured the field, the electromagnetic field in the area. So we found there was a high value of the frequency of 2,172 megahertz. Yeah, we didn't expect that there is a frequency, the 2,172. So we begin to search. What is the application of this frequency actually? Yeah. So we search the literature. Then we know that in the Cap Dirjen Keputusan Dirjen SDPPI, in Kominfo, stated that in this frequency is actually allocated for trial for 5G. For 5G. This is the why. So we choose this frequency with the reason that the next base station will will transmit the 5G, the 5G in order to substitute the 4G technology. So this frequency is quite high compared to other frequency in the environment at the time. I hope it answered the question partly.
Yep, I think the next question is your research is depend on the environment of the measurement, I think. So if we have a different environment, what your research is can be generalized to the another environment, I think.
That's why I call it as a typical area of the environment. So in the suburb, so it doesn't represent the environment in the city. What is called in English, I forgot. So it is in the suburb, in the rural area. So for example, there is vegetation and open area and transmitter. 3-story buildings. So I can, even if I haven't done the research in such other areas, but I'm sure that it can be also specimens or something. Is a specimen for the other to simulate the other environment.
Okay, thank you. I think it's enough.
I hope it satisfies your question. So otherwise, we can open a discussion next year. Thank you.
Okay, thank you, Miss. I think the time is up. Finally, we reach the end of the session. Before we closing the session, please open video to take a screen capture. Mr. Ricky, please. Okay. We will take a screen capture. Mr. White. Okay, I think it's enough. On 3, 2, 1. And the next screen on 3, 2, 1. Okay, thank you very much for all presenter and the audience. I hope we can see in the next ICRAMET. I'm Dayat Kurniawan. Assalamualaikum warahmatullahi wabarakatuh.
Mr. Dayat, can I have a question? Not technically. Can I receive, for example, a screenshot of my presentation? I forgot to my screenshot.
Okay, I will send the screen capture to you, Mr. Sarjono.
Okay, thank you very much.
Recording stopped. Recording in progress. Recording in progress.
Tomorrow's world. Technology that makes work and life easier. We have mastered the fundamentals and cover all products that communicate with wireless technology or depend on it. Where communication implies responsibility and values, it requires special protection. Information also means reducing uncertainty, radio monitoring and radio location, secure communications, broadcast and media, and test and measurement. That is our world. For almost a century, we've been helping to shape the technology-driven universe we live in. We were there at the very beginning, set milestones, and drive the developments of our time. We have always been and will continue to be an independent company. Development, production, and worldwide service under one name. We create solutions. We are Roda and Schwartz.
Jurnal Elektronika dan Telekomunikasi or JET is a journal published by Pusat Penelitian Elektronika dan Telekomunikasi LIPI. JET presents high-quality articles on the latest research and development in the field of electronics, telecommunication, and micro or nanoelectronics engineering. JET provides a platform to share research in the areas such as digital signal and image processing, network theory and circuit design, radar and sonar technology, antenna and wave propagation, wireless and optical communication, microelectronic system, electromagnetic and electronics materials, emerging and advanced fabrication technology, and so on. JET is indexed by internationally renowned indexers such as the OAJ, Google Scholar, Mandalay, and etc. JET is also ranked at Center 2 in Kemenristek BRIN accreditation system. There are 2 JET editions published every year, and all of them are available in open access to support global exchange of knowledge. All submissions in JET are accepted online, and each submission will be blindly reviewed by at least 2 peer reviewers. Most importantly, all submissions are free of charge, and therefore, no article processing fee applies. For more info, please visit www.journalet.com or visit our social media accounts.
National Research and Innovation Agency, a synergy in an orchestra. Established through the Presidential Regulation Number 78 of 2021, National Research and Innovation Agency. To enhance science and technology's contribution to the national development and to improve the research and innovation ecosystem in Indonesia. The National Research and Innovation Agency is a government agency that is directly responsible to the President of the Republic of Indonesia. Consists of 7 deputies, supported by 12 research institutes, have 85 research centers, Executive Secretariat, Executive Inspectorate, Center for Data and Information, Center for Technology Services, and Polytechnic Institute of Nuclear Technology, Indonesia. Through the 3 directions: science and technology resources mobilization, providing a favorable research ecosystem, building an economy foundations based on research. The presence of National Research and Innovation Agency is to achieve Indonesia's goals as a developed country in 2045. Also to make Indonesia as a global reference for sciences, bringing advantages on science and technology development, policy making, and societies.
Today's world is a network of data and signals. The gap between vision and reality is closing. A thirst for knowledge and the search for new frontiers are the driving force behind innovation. We develop and produce top-quality, durable products that enable progress. Cultures and markets may differ, but people and technology bring us closer together. The essence of our products: technology for people who are building tomorrow's world. Technology that makes work and life easier. We have mastered the fundamentals and cover all products that communicate with wireless technology or depend on it. Where communication implies responsibility and values, it requires special protection. Information also means reducing uncertainty. Radio monitoring and radio location, secure communications, broadcast and media, and test and measurement. That is our world. For almost a century, we've been helping to shape the technology-driven universe we live in. We were there at the very beginning, set milestones, and drive the developments of our time. We have always been and will continue to be an independent company. Development, production, and worldwide service under one name. We create solutions. We are Roda and Schwartz.
Jurnal Elektronika dan Telekomunikasi or JET is a journal published by Pusat Penelitian Elektronika dan Telekomunikasi LIPI. JET presents high-quality articles on the latest research and development in the field of electronics, telecommunication, and micro or nanoelectronics engineering. JET provides a platform to share research in the areas such as digital signal and image processing, network theory and circuit design, radar and sonar technology, antenna and wave propagation, wireless and optical communication, microelectronic system, electromagnetic and electronics materials, emerging and advanced fabrication technology, and so on. JET is indexed by internationally renowned indexers such as DOAJ, Google Scholar, Mendeley, and etc. JET is also ranked as Center 2 in Kemendristek BRIN accreditation system. There are 2 JET editions published every year, and all of them are available in open access to support global exchange of knowledge. All submissions in JET are accepted online, and each submission will be blindly reviewed by at least 2 peer reviewers. Most importantly, all submissions are free of charge and therefore no article processing fee applies. For more info, please visit www.journalet.com or visit our social media accounts.
National Research and Innovation Agency, a synergy in an orchestra. Established through the Presidential Regulation Number 78 of 2021 about the National Research and Innovation Agency. To enhance science and technology's contribution to the national development and to improve the research and innovation ecosystem in Indonesia. The National Research and Innovation Agency is a government agency that is directly responsible to the President of the Republic of Indonesia. Consists of 7 deputies, supported by 12 research institutes, have 85 research centers, Executive Secretariat, Executive Inspectorate, Center for Data and Information, Center for Technology Services, and Polytechnic Institute of Nuclear Technology, Indonesia. Through the 3 directions: science and technology resources mobilization, providing a favorable research ecosystem, building an economy foundations based on research. The presence of National Research and Innovation Agency is to achieve Indonesia's goals as a developed country in 2045. Also to make Indonesia as a global reference for sciences, bringing advantages on science and technology development, policy making, and societies.
Today's world is a network of data and signals. The gap between vision and reality is closing. A thirst for knowledge and the search for new frontiers are the driving force behind innovation. We develop and produce top-quality, durable products that enable progress. Cultures and markets may differ, but people and technology bring us closer together. The essence of our products: technology for people who are building tomorrow's world. Technology that makes work and life easier. We have mastered the fundamentals and cover all products that communicate with wireless technology or depend on it. Where communication implies responsibility and values, it requires special protection. Information also means reducing uncertainty. Radio monitoring and radio location, secure communications, broadcast and media, and test and measurement. That is our world. For almost a century, we've been helping to shape the technology-driven universe we live in. We were there at the very beginning, set milestones, and drive the developments of our time. We have always been and will continue to be an independent company. Development, production, and worldwide service under one name. We create solutions. We are Roda and Schwartz.
Jurnal Elektronika dan Telekomunikasi or JET is a journal published by Pusat Penelitian Elektronika dan Telekomunikasi LIPI. JET presents high-quality articles on the latest research and development in the field of electronics, telecommunication, and micro or nanoelectronics engineering. JET provides a platform to share research in the areas such as digital signal and image processing, network theory and circuit design, radar and sonar technology, antenna and wave propagation, wireless and optical communication, microelectronic system, electromagnetic and electronics materials, emerging and advanced fabrication technology, and so on. JET is indexed by internationally renowned indexers such as DOAJ, Google Scholar, Mendeley, and etc. JET is also ranked as Center 2 in Kemenristek BRIN accreditation system. There are 2 JET editions published every year, and all of them are available in open access to support global exchange of knowledge. All submissions in JET are accepted online. and each submission will be blindly reviewed by at least 2 peer reviewers. Most importantly, all submissions are free of charge and therefore no article processing fee applies. For more info, please visit www.journalet.com or visit our social media accounts.
National Research and Innovation Agency, a synergy in an orchestra. Established through the Presidential Regulation Number 78 of 2021 about the National Research and Innovation Agency. To enhance science and technology's contribution to the national development and to improve the research and innovation ecosystem in Indonesia. The National Research and Innovation Agency is a government agency that is directly responsible to the President of the Republic of Indonesia. Consists of 7 deputies, supported by 12 research institutes, have 85 research centers, Executive Secretariat, Executive Inspectorate, Center for Data and Information, Center for Technology Services, and Polytechnic Institute of Nuclear Technology, Indonesia. Through the 3 directions: science and technology resources mobilization, providing a favorable research ecosystem, building an economy foundations based on research. The presence of National Research and Innovation Agency is to achieve Indonesia's goals as a developed country in 2045. Also to make Indonesia as a global reference for sciences, bringing advantages on science and technology development, policy making, and societies.
Today's world is a network of data and signals. The gap between vision and reality is closing. A thirst for knowledge and the search for new frontiers are the driving force behind innovation. We develop and produce top-quality, durable products that enable progress. Cultures and markets may differ, but people and technology bring us closer together. The essence of our products: technology for people who are building tomorrow's world. Technology that makes work and life easier. We have mastered the fundamentals and cover all products that communicate with wireless technology or depend on it. Where communication implies responsibility and values, it requires special protection. Information also means reducing uncertainty. Radio monitoring and radio location, secure communications, broadcast and media, and test and measurement. That is our world. For almost a century, we've been helping to shape the technology-driven universe we live in. We were there at the very beginning, set milestones, and drive the developments of our time. We have always been and will continue to be an independent company. Development, production, and worldwide service under one name. We create solutions. We are Roda and Schwartz.
Ladies and gentlemen, welcome back to ICRAMET 2022. Now we are having our second keynote talk by Professor Thomas D. Antopoulos. This session will be moderated by Dr. Yusuf Nurwijayanto. First, I would like to introduce you to Dr. Yusuf Nurwijayanto. He received his Master of Engineering and PhD degrees in Electrical Engineering from Osaka University, Japan in 2010 and 2013, respectively. Since 2005, he joined the Indonesian Institute of Sciences, or known as LIPI, Indonesia that now has changed the name into National Research and Innovation Agency for Indonesia, or known as BRIN. Currently, he is positioned as the head of Research Center for Electronics in BRIN. His research interests are microwave and radio engineering, optic and photonic engineering, and fiber, wireless, or Wi-Fi technology. Please welcome Dr. Yusuf Nurwijayanto.
Thank you. Thank you, Dr. Ardita, for the introduction. Dear all participants in this ICRAMET 2022. In here, this is my pleasure to moderate this very interesting talk from the Professor Thomas G. Autopoulos from the Division of Physical Science and Engineering, King Abdullah University of Science and Technology, Chaos. The title of this talk is regarding about scalable manufacturing of sustainable electronics. Welcome the Professor Thomas in this our interesting conference. I think in the Saudi Arabia is about a fairly early morning in there. Thank you very much for coming in this session and give our keynote in this conference. So before the conference start, maybe I would like to introduce Professor Thomas. In here, I saw the education of the Professor Thomas is already graduate from the PhD from the Stanford University, and then get the bachelor degree in the Stanford University also. And currently he work as the professor of material science at the King Abdullah University of Science and Technology, Kingdom of Saudi Arabia. And also he has the many experience in here. I saw his working experience and research experience, and his research interest is regarding the properties of material, applying of fundamental understanding to develop improved material and device for a wide range of the application in energy harvesting, generation, electronics, display and lighting, and sensor. And maybe another research interest also innovative manufacturing technology for large area nanoelectronics, where the device and ultimately system level performance is determined by the device physical dimension rather than strictly by the active material. So in this time, you have about 45 minutes, and I will give the talk for you. Please, Professor Thomas. Thank you very much.
Thank you, Dr. Yusuf, and thank you, the organizers, for giving me the opportunity to present some of our recent work in the area of scalable nanomanufacturing, sustainable electronics. It is a great pleasure. It is 9 o'clock here in the morning, and it's an afternoon for you after lunch. So I hope I'll be able to entertain you for the coming 40 minutes, but also I hope to present some work that many in the audience have not come across before. It is not a perfect match for the conference, but I have a little bit of an element of radio frequency electronics in the application side. I hope you can hear me well as well. I haven't checked that. Great. So today I will talk a little bit about the scalable nanomanufacturing of emerging forms of electronics, specifically large area electronics. But before I go into the main topic of my talk, I'll talk a little bit about the history of electronics. So what I have in this diagram here is a brief history of electronics, starting with the invention of the tube rectifier, the triode, essentially the predecessor of transistor. Then we had, of course, 1947. This year is the 75th anniversary of the transistor discovery. We had essentially a bipolar junction transistor, then followed by the integrated circuits. And fast forward to modern day electronics. What we essentially have today in front of us, in our hands, is a truly nanotechnology in action. So if we take one of our smartphones and dissect it and identify the microprocessor, and then we cut that microprocessor through, what we will find inside is some of the most sophisticated electronic devices, so-called FinFET, is a variant of the field effect transistor. And what I find personally amazing with these devices essentially is some of the minimum features you can identify. The fin in this specific transistor is a three-dimensional transistor, is a feature that actually you can count the silicon atoms in parts of it from one side to the other. It's a truly nanotechnology in action, and we own it. It's not anymore hype, it is a reality. I remember when I was a student where we were discussing essentially transistor going below a couple of 100 nanometers, and it sounded amazing. And now we are already reaching to a point where physical limitation becoming really unsurmountable. So for example, we have these critical features being reduced down to less than 5 nanometers. So it's big question marks what else is coming our way in the future in terms of the state-of-the-art silicon electronics. However, what silicon has managed to do through this extreme downscaling is to pack more and more devices per unit area of a silicon chip. So this is an evolution of the number of transistors per square millimeter. And essentially where we are today, we are somewhere there and essentially entering this hyper scaling area, and where essentially a lot of interesting integration protocols come into place. And we have already now several billion of transistors being squeezed within a few millimeter square. So a tremendous technological achievement. However, this comes at a cost. And although it was not my intention to talk about it, I think it becomes now, it is a very important point. What is the cost we pay in terms of the environmental impact of manufacturing this state-of-the-art electronics? So I recently came across a very interesting analysis, can be found in this paper by Gupta et al., where essentially they tried to track down the carbon emission of ICT sector. And they have a few interesting examples. And this is, in this slide, I present the example of Apple, for example, where the analysis of the total carbon emissions can be split into the different components of the different products. And what we see here is a very large fraction of it is just caused by the manufacturing of this state-of-the-art integrated circuit alone. And then comes the board flexes, aluminum casing, and then a little bit about the product use. Essentially, these products don't use a lot of energy, or that has on its own a carbon emission footprint, but most of the carbon emission footprint comes from the manufacturing. So the key points we can take here: manufacturing is really, really critical and will become even more critical in the years ahead of us. Hardware use accounts only for 19%. And the hardware life cycle comprises of over 98%. So the take-home message here is that the carbon output of this state-of-the-art microelectronics are single-handedly the biggest contributor to the carbon footprint of silicon microelectronics. We can also analyze the carbon emission footprint of products based on whether they are battery operated or constantly plugged into the mains. This is another interesting plot from the same study, where essentially they have summarized the battery operated devices. There's a gamut of devices here. We see iPads, Pixel Go, iPhones, etc. And they split the breakdown of the carbon footprint to sections such as the ones caused by during production, transport, or use. So the most interesting one is the production and use. And as you can see, battery-operated devices, most of the carbon footprint originates from the production stage, and very relatively little is being caused during the use of these products. The situation changes if we move and analyze the always connected devices, like my desktop computer I have in front of me, or like our TVs. So essentially what you see here is that the situation changes dramatically. And now the carbon footprint associated with the use of these products over the lifetime becomes the dominant factor, the green shaded areas here for all these products. So the key points here is essentially what I've just said. So what one can do, essentially, we know how to minimize the carbon footprint caused by the use. How we can do that? Simply, we can rely or switch to energy sources which are more renewable, greener energy sources. And that's exactly what's been predicted and is shown in this plot. Moving away from coal, which is the most polluting, for example, energy source, to renewable energy sources such as hydro power and wind and solar potentially can minimize the carbon footprint associated with the actual use of the device. But doing that has no impact whatsoever on the production carbon footprint of these electronics, because the production of these electronics, it is really polluting and it takes a lot of energy. And as we going smaller and smaller in feature size, this demand becomes even more stringent, and essentially we ending up spending more energy for producing these devices. And we see this being kind of reflected in the yield, manufacturing yield of state-of-the-art electronics, which is actually reducing, and the cause of this reduction is actually reflecting also on the overall cost of the transistor, the number of transistors we can buy per US dollar. So the major challenges that we're facing, and we have to really consider these major challenges for any future or emerging technologies, is first, improve manufacturing. We have to come up with better ways of doing or making this, building these electronics. I believe this is not easy to implement for silicon because it's such an established technology, but may be the case for emerging technologies. That's exactly what I would like to highlight in my talk today. And of course, develop more and better, more efficient renewables. So if I wanted to highlight or summarize the interests of my personal interest in terms of research, I will say that my group is focusing a lot on new renewable energy sources, specifically photovoltaics. But today I'm not going to talk about it. Instead, I will focus more on scalable nano manufacturing, essentially new ways of building future generations of electronics that are simple and economical to manufacture, but at the same time do not compromise the performance that we can achieve, and how we use these nano manufacturing paradigms for application in emerging electronics. I will show you a few examples of the technology we've been developing and then how we use these technologies to demonstrate prototypical devices. And some of them essentially will be radio frequency diode devices. This is my main focus. So going back to this chart, it's very difficult, and what I've shown you about established tech, where essentially we are reaching to a point where our FinFET technologies have minimum features of around 5 nanometers. So many people question what comes next our way. And of course, knowing a bit of the past, we can predict a little bit better the future. So the good news is that, of course, we don't hit a hard wall here. We have already a lot of interesting developments in recent years. A few examples of such developments include new concepts, quantum computers, a lot of talk about quantum computers. I believe this is a technology here to stay. Perhaps quantum computers will be hitting the cloud. It won't be something that we can take with us in the very near future. But there might be other technologies like neuromorphic, which may enable certain applications that are currently inaccessible or not very efficient using just conventional digital computing. What I'm personally more interested in is about the new forms of electronics, such as large area electronics. I believe in the future, a lot of these emerging electronics will be the ones that dominating our landscape, essentially our daily life. But before we start covering our world with these new forms of electronics, we better have plans on how we can efficiently manufacturing with a minimum of environmental impact, but also take a look at the total life cycle analysis of the products. What do we do with these products once the lifetime has come to an end? Can we recycle them? Can we reclaim them? Can we reuse them? So we start seriously thinking about how we will be implementing all the different stages so we can minimize the environmental impact. So what these new forms of electronics will look like, here is a slide with a few pictures of recent developments, relatively recent development, the last 10 years. We have seen now companies like Pragmatic in UK fabricating microprocessors on foil. This is all unipolar based microprocessors utilizing metal oxide semiconductor transistors. We have also soft electronics, like this example from University of Tokyo, Professor Takao Samea, where essentially you can have skin-like electronic with a lot of interesting functionalities. We may even see transient electronics like this example from John Rogers in Northwestern, where essentially you create electronics that you can implant in your body, perform a specific function, and then they dissolve away without us having to operate again, essentially, non-invasively dissolve away in our body in a very biocompatible manner and completely disappear. Of course, these developments create a lot of new opportunities. Hopefully, this will lead to new industries which are more eco-friendly and more sustainable. And that's exactly the areas where I believe personally research and development centers, industry and universities come together to really identify these important technologies, develop them, but also find the right applications. And I think this is where essentially the next 10 years will be quite critical in developing all these new futuristic applications, but also identifying the problems and the bottlenecks. These are all great and sound fantastic, but there are a lot of economic challenges with this task. One of the major challenges is a technical challenge. What we have actually discovered is that the moment we're deviating from the state-of-the-art silicon electronics to more relaxed device feature size, which are made via economical manufacturing techniques like printing, we pay a penalty. And that penalty is the performance loss. Essentially, we have devices made of silicon that can operate at hundreds of gigahertz, but the moment we have a printed device, which is much larger, can be manufactured much more economically with a minimum environmental impact, then the performance of this device is very poor. To a point where all this emerging large area electronics can't really interface directly with silicon because they're not able to operate at the required frequency domain. For example, printed electronics are very rarely interfaced via Wi-Fi or Bluetooth frequencies with silicon electronics. We always need to have a silicon chip accompanying this large area device in order to interface with existing infrastructure. And the reason being come down to the fundamental device engineering. So this is a bit of more technical, but just shows a schematic I drew of a field effect transistor. And what we essentially, if we overlook the impact of capacitances and parasitic capacitance, or as well as a junction capacitance of the devices, then the ultimate operating frequency of a device like that comes down to the mobility of the carriers in the semiconductor you're using. If we use p-type silicon or n-type silicon, then this mobility is 1,000 centimeters squared per volt second, divided by the L square. This is channel length. This is the distance between the source and drain electrodes. And in silicon, this channel length is very, very small. It's in the tenths of nanometers. However, when we go and talk about printed electronics, this dimension here is on the tenths of micrometers. So essentially, we have 1,000 times or several orders of magnitude difference in the device feature size. And why is this the case? Simply because we can combine economical manufacturing, such as scalable printing technologies, with high resolution features. So the question we ask ourselves is, could we, in the area of large area electronics, take advantage of the extreme downscaling, just like silicon done in the past 50 years? To understand better the problem, we have to look at length scales in nature. We know that what we would like essentially to do is to have the ability to nano-manufacture features at all scales nano-manufacturing, if you like. If we look at natural self-assembly, we know nature can take single atoms and build us through biological processes. And so we know it is possible. But when it comes down to technical implementation of a similar idea, then we realize there is a gamut of complementary technologies, but not a single technologies, a patterning technology or manufacturing technology that spans across the all length scales. So we have essentially for the large area patterning, we have technologies like printing and photolithography. And if we want to really probe down to the nanometer scale, then we have some sort of a scanning probe lithographies, E-beam, high-end, expensive, and not easy to scale up technologies. So there is no single, essentially, manufacturing approach that one can adopt in order to bridge the nano world with the macro world. And that's exactly where I believe this performance gaps is originating. On one hand, we have the high-end technologies that we can build our beautiful silicon microelectronics. But on the other hand, we have the cost benefits associated with the printing technologies, but this comes at the cost of performance. So how do we bridge this gap? My group has been focusing on developing simple yet versatile patterning techniques that enable us to actually bridge this performance gap and hopefully develop devices where we can be manufactured over large areas, but at the same time can perform at a very high level. How we do that? This is one example we have been developing, and one of these technologies is the so-called adhesion lithography. It's essentially a variant of conventional lift-off photolithography. So in order to understand even with a basic knowledge of electronics manufacturing, we can consider this very basic schematic. We start with a substrate, and then we essentially deposit a metal electrode. Then what do? We apply a self-assembled monolayer directly on this metal. So these self-assembled monolayers are specific molecules, a nanometer or 2 nanometer in length, that contain an end group, which is essentially defines the surface energy of that surface, and the head group, which is very critical because this head group is a metallophilic head group. Essentially, is designed to react only with the metal one, but not with the substrate. So by essentially dipping this substrate in a liquid containing the self-assembled monolayers, this monolayer will be essentially able to self-form on the surface of the metal, but will not interact with the substrate. And then the tail, which is just an aliphatic spacer, and that can be tuned from a handful of atoms to a tenth of atoms through very simple chemistry. So what we essentially end up doing is to change the surface energy characteristics of this metal one. And then what we do, we process a second metal layer, metal 2, shown here, over this whole structure. Now, what we essentially discover is that the interface between metal 2 and metal 1 is mediated by this self-assembled monolayer. Essentially, what we're doing is we weakening this binding, so the adhesion force between metal 2 and metal 1 is very, very small as compared to the adhesion force between metal 2 and the substrate. And then through mechanical delamination, essentially just applying a glue or a tape over the structure, we can mechanically delaminate it, exfoliate it, and essentially removing this overlap, because this interface is very weakly bound with each other. So essentially it's a very small adhesion force. We can delaminate it while the metal 2 interface with substrate directly remains in place. Essentially, what do we do here? We're removing all overlaps between metal 2 and metal 1 very selectively without really worrying about it. And then what we have is a coplanar structure that looks like that. And essentially the metal 2, if you get everything right, is isolated from metal 1 through this self-assembled monolayer, a very, very small distance of a few nanometers. And then what we can do, we can place this device on an oxygen plasma or other plasma atmosphere and burn it away within a few seconds. So essentially we end up then with a very clean metal 2, metal 1 adjacent, closely adjacent to each other on top of the substrate. And as you can imagine, this is a photograph explaining the process steps I've shown you. And if you really want to understand the process and how simple it is, I have this little video I'll be showing here. Essentially, what do we see here? Now we have metal 2 evaporated everywhere on top of metal 1 that contains the self-assembled monolayer. Then we apply the glue. We allow this glue to dry. And then essentially we just physically delaminate that adhesion layer form atop. And you see now we're removing all these overlapping areas between metal 1 and metal 2. This is pretty simple and straightforward. And we can do that over large area substrates. So this is one example how we actually perform this mechanical delamination through adhesion lithography over 4-inch wafer. What we didn't expect is to see how small this gap between the two metals will be, these coplanar metals. So this is a cross-sectional TEM analysis. This is transmission electron microscope analysis shown here, where we see essentially gold and aluminum can be patterned very closely together, fully electrically isolated from each other, and separated by a distance of approximately 10 nanometers. And this is the plan view of this nanogap. So essentially, we see an intergranule fracture and the formation, the spontaneous formation of a nanogap. Why this is interesting? Essentially, we have two metals, and these metals can be tuned accordingly to have a low and a high work function. And that's exactly what we need for creating light-emitting diodes, photodetectors, or Schottky diodes. And considering the small distance between the two electrodes, we expect these devices to exhibit very interesting performance characteristics. And most importantly, the same process is compatible with large area manufacturing and a lot of different substrate materials. So here we show how interdigitated electrodes with a total width, essentially the length at which these two electrodes run along each other, varying from a couple of centimeters dispersed interdigitated electrodes to 5 meters. So essentially we have a very high aspect ratio nanogap formation, and we can do even these nanogaps, we can manufacture them on plastic substrates using different electrode materials. In this case, we have used PET as a substrate. We have a indium tin oxide transparent electrode, and what we see here is aluminum electrodes, discs separated from the ITO, the global ITO electrode, by this nanogap. So essentially, we have a lot of flexibility on how we can implement this type of technology. More recently, we've been able to simplify the process even more. And the information can be found on this paper shown here. So what we've done here, we wanted to really remove the process of delamination, the mechanical delamination, because it's not a standardized process. It's something that we need to develop, and potentially industry may be hesitant in doing so. So what have we done instead? We have patterned the metal 1, applied the sum, and then the metal 2 is being replaced by a bimetallic metal. So essentially 2-layer metal, 2 different metal, starting with the so-called interlayer metal, very thin layer, and then a thicker second metal, the green area shown here. And we discover if we play with the right thickness of this interlayer and the green second metallic layer, we can induce tensile stresses at the interface with metal 1. To a point where these tensile stresses are so great that any material, any metal 2, this bimetallic electrode deposed on metal 1 will spontaneously delaminate. And that's exactly what we have experimentally observed. And how this delamination look like is shown in this little area here, where essentially we have the originally metal 1 covered entirely by metal 2, but over the metal 1, once this thickness has exceeded the critical value, we have the spontaneously delamination and rolling of this metal 2 from the areas where metal 1 is pre-patterned. So, and how this looks like is a few more images shown here. Essentially, we have spontaneous delamination and the exposure of metal 1 and metal 2, and separated by a tiny 10 nanometer or so nanogap. And these nanogaps essentially maintain a fully electrically isolating in their nature. So essentially, the metal 1 and metal 2 are fully electrically isolated. They are not really shorted. And we're very surprised with that very interesting a high yield we can obtain. And this is how this process looks like in a wafer scale. So essentially we have devices which look like that when taken out of the chamber. But if we wash them away and we remove all the delaminated metal, which we can reclaim and reuse, then we end up with a very clean self-formed nanogaps between the two metals we have chosen. And this is how this self-forming nanogap it looks. So if we grow this bimetallic electrode below this critical thickness where self-delamination occurs, we can take it out of the evaporating chamber, and then put it in a solvent bath and mechanically agitate it. And we can actually instigate that delamination essentially at will. So in this case, we have just shaked a little bit this solvent bath in the wafer, and we see all delamination taking place. Essentially, all the overlapping areas popping out and being washed aside. And then we can use this wafer for creating our electronic devices. So one of the most interesting devices we have decided to demonstrate back then, it was a radio frequency diode. We have essentially two electrodes which can be tuned to have a high work function and a low work function. In this case, gold and aluminum. And then we thought of by placing a semiconductor like a zinc oxide, which can be solution processed in the nano gap. Don't forget this gap between the gold and aluminum. It's very small, it's 10 nanometers. Therefore, we assume that the majority carriers in zinc oxide, which are electrons, could be actually transit these devices at a very short times. The transit time will be very short because essentially the distance is very small. And 1 over this transit time will give us the ultimate cutoff frequency of these devices, which doesn't take much to calculate, that could be very, very high. So to do that, we have moved ahead and tested the hypothesis. Radio frequency diodes will be very interesting technology because we find direct application in the Internet of Things device ecosystem. They're present, whether this is a telecommunication node or essentially energy harvesting node. Diodes are a must-have element. And what is important with the diodes is the operating frequency, as already mentioned. So this is a chart we have published 5 years ago. And what we essentially try to capture here is how the operating frequency of a diode, so this is 1 gigahertz, relates to the application space. And clearly from this plot, you can see that the higher, of course, the operating frequency, the broader the application space of the technology you can have. And that's exactly what we're aiming for here. So essentially, we have a technology, a manufacturing paradigm, which is very scalable, but at the same time, provide us access to the very small feature sizes, which is the nano gap, which is critical for the overall device operation. So that was the line of thinking we had when we were developing these devices. So what we've done, and more information can be found in this paper published a couple of years ago, we have performed the adhesion lithography up to 0.8, shown here. So essentially we end up with a very nicely empty nanogap electrode. And the last thing, the few steps we did is to deposit a semiconductor precursor. So essentially this was a zinc oxide. We started from a zinc acetate, for example. We dissolve it in a conventional solvent. It can even be water, and then annihilate at a couple of 100 degrees Celsius to convert it to its stable metal oxide semiconductor form. And it's very simple and straightforward. So we did make these devices, and this is how essentially this device look like. We have a kind of a RF layout device shown here, which is circular, and we have the ground signal microwave probe landing in this corner of the device, and that allows us to probe the operating characteristics. And this is how the device look like. Essentially, the zinc oxide is very thin layer, only 10-20 nanometers above, covers the nano gap, and the nano gap between aluminum and gold is very clean, as you can see, and very tiny. And is enough to deliver essentially functional devices. So this is how the current voltage characteristics of these devices look like. So in these cases, we have in the left here, we have a device with different circumference size. One is 250 microns, and we're going 5,000 microns, a 5 millimeter circumference, so essentially much larger devices. And we can see that we can tune the current driving capabilities of the diodes by changing the size of the diode. We can also tune the semiconductor. Here, essentially, we have introduced aluminum dopant into the zinc oxide to overcome or remove some of the trapping sites we know to exist because of chemical deficiencies in the semiconductor. And then we can calculate the rectification ratio. And as you can see, the rectification ratio taken as the maximum current divided by the minimum current in the reverse bias direction can be up to 1 million. So it's more than enough for a lot of application we have in mind. Then what we've done next is to probe the ultimate intrinsic cutoff frequency. And we can see here by playing with a semiconductor, for example, for a standard device circumference of 1 millimeter, we can get potential cutoff frequencies up to 60 gigahertz if we tune the semiconductor. And then we can make the device even smaller, and we have actually extrapolated or predicted operating frequencies of hundreds of gigahertz. This is truly amazing, considering the simplicity with which these devices were fabricated. And if we test them, of course, in air, vacuum, of course, the environment plays a major role. So we have to consider as well encapsulation technologies for practical application. So most importantly, the devices can be fabricated on a large wafer scale and then taken and combined with a bias T and a functional generator. Essentially, these are VNA measurements, and we can create a little rectifying circuit. And what is important here, we launch in an RF signal and we see what comes at the end. And what we found, essentially, we can create a DC output up to frequencies of tens of gigahertz, telling us that the extrinsic frequency of this device is pretty high. And we can increase this frequency by optimizing both the device layout as well as the semiconductor. And at the time, these were essentially among the fastest solution processed RF diodes demonstrated in the literature. We've done exactly the same process, but instead of using zinc oxide, we use an organic semiconductor, this polymeric semiconductor, which was p-doped with this molecular dopant. And indeed, we were able to demonstrate devices that are very nice in terms of diodic behavior, but also very fast. In this case, we have demonstrated a cutoff frequencies of 14 gigahertz using this solution processed organic semiconductor. Sorry for the very busy slide in this case. And even more recently, we're able to simplify the process even more. We took the nanogaps, we solution processed our metal oxide precursor, and then what we've done, we took a big flash lamp and illuminated the whole device for 1 millisecond. And what we discover, a lot of this xenon flash light is absorbed by the metal heats up momentarily and converts the precursor of the metal oxide into its metal oxide semiconductor phase rapidly. And why this is the case? Because this momentarily, the metals can increase up to 600 degrees Celsius. And because the nanogaps are so tiny, anything that is in there can undergo thermal annealing process, but for a very brief moment in time, so brief that you can actually perform the same processing step even on plastic substrates, and the plastic substrate is not affected. So we took this self-formed flash sintered devices and we measure the cutoff frequencies, and we realize that again, like we've seen with the conventionally thermally annealed devices, that as we shrink the diode's diameter, essentially the circumference, we can get a much faster device because the RC constant becomes smaller and smaller. Since then, we have learned a lot about also engineering and designing the diodes in a way that are more efficient. These circular devices are by no means the most efficient design we can actually implement. But what is the take-home message here is that extrinsic frequencies now for these flash sintered diodes can exceed 40 gigahertz. So essentially, we're having a super well-behaving diode at a very high frequencies, and this diode can really be manufactured using minimal material usage, but also minimal energy as compared to conventional diode technologies available in the market. So if we were to compare our devices, these 40 plus gigahertz we have demonstrated in 2021, we have essentially devices which are really, really high performing. And to our knowledge, these are the fastest RF diodes ever created via solution processing routes. It's not the semiconductor that makes a difference, it's essentially the extreme downscaled dimensions of our diodes, essentially the distance between our Schottky contact and our ohmic contact in this coplanar configuration we have developed. And finally, I have a few slides remaining. We use the same exactly technologies, the self-assembled, the fusion lithography using self-assembled monolayers to fabricate traditional, thin film transistors as well. And essentially what the aim of this project is to take the traditional TFT, which is very difficult to essentially have a perfectly aligned gate in between the source and drain contacts, and remove essentially these parasitic overlaps. This, using conventional lithography, takes time and money, simply because as this channel length becomes smaller and smaller, registration using sophisticated equipment becomes problematic, and of course cost, increases the cost if you really want to get it absolutely right. So what we've done in our case, we were essentially able to take the substrate, pattern the metal one electrode, which essentially will act as the gate electrode, then apply the self-assembled monolayer. Then we have a crossbar common electrode, metal 2, which is essentially then the overlapping regions is removed through adhesion lithography, either through the glue or self-forming, spontaneously delamination, and essentially automatically forming the source and drain electrodes across the gate electrode. So essentially we have a self-formed, self-aligned gate transistor architecture, which are very simple to manufacture and requires no registration, mask aligners, etc. And the last thing remaining is to actually deposit the semiconductor. In this case, we have used oxides, 2D materials, a number of a gamut of semiconducting materials atop these structures. And how this structure look like really is shown here from the top. Essentially, we see initially we have this gate electrode, which is originally overlapped by these gold electrodes, but then this overlap is removed through the process of adhesion lithography. And finally, we deposit the semiconductor. Of course, in this case, the semiconductor is a transparent metal oxide. You don't see it really, but we have a fully functional devices in place. And because they are self-aligned gates, there is no parasitic overlaps. So essentially, we don't have this parasitic capacitances associated with the overlaps. And we do hope, and we will be reporting it soon, that these devices, as a result, can be really operated at a very high frequencies. So essentially, we have a singular manufacturing process that can be applied to fabricate radio frequency diodes and potentially a radio frequency modulatable load device, such as an active transistor device. This is the missing element for our large area electronics, the transistors that can really operate at gigahertz frequencies without requiring extreme manufacturing complexity. Essentially, less manufacturing complexity, minimized carbon footprint, lower cost. That's exactly what we're trying to achieve in my group. So without want to take more of your time, I would like to just summarize the contribution I've just presented. I hope I did present my case and convince you that nano manufacturing at all scales, it is possible and not necessarily will rely on complicated established technologies. We need to think outside the box, and we need to come up with more efficient ways of creating the future generation of this large area electronics. And this is a list of different devices that we have demonstrated in my lab. I've shown today how we made large area RF electronics like diodes, but we also been demonstrating using the nano-gap technology, ultra-fast photodetectors and nano-gap light emitting diodes, memories, sensors, and we will soon be reporting also how we can use these nano-gaps for creating ultra-sensitive bioelectronic devices. And with this, I would like to thank you for your attention, and also to thank all the collaborators that have helped and contributed to the to the work I have presented, and my group that have most of these shown in this picture have at some stage contributed to the work presented before you today. Thank you very much for your attention.
Thank you very much, Professor Thomas, for your very interesting talk today. The time is of more than 40 minutes, I think. Okay, and here the Professor Thomas already explained relating the scalable manufacturing and emerging electronics, and explained regarding also fabrication process in the nano manufacturing, and also application in the improved solar cell technology, also large area RF electronics such as the RF diodes and inorganic also, and the metal nanogap, RF diodes, and also self-alignment gate transistor. Maybe the time is for the question and answer. If you have a question, please raise your hand. We have the one question from Yulia Firdaus. I think your friend, Professor Thomas. Please, Dr. Yulia.
Yes.
Yeah.
Hi, Thomas. How are you?
Hi, Julia. Nice to hear you.
Yeah, I still see that my picture is in the last slide.
Yeah.
Okay, so I have two questions actually. So which material do you think is best for nanogap? I mean, which material you prefer to use as a semiconductor? I can see that I think like inorganic still better than organic so far. What is the bottleneck for that? I think it's the mobility. Is that true?
Yeah.
And then the second one is, I mean, you're mentioning about this carbon footprint, and then of course it is difficult to replace the established technology like the silicon, right? And do you believe that using this larger area nanogaps will at some point you know, give some segments and contribute to this decrease in the carbon footprint? That's my question. Thank you.
Yeah, thank you, Julia. Both questions are very good. Starting with the first question about what material is the best. I think when it comes down to the semiconductor, I think there are challenges in the technology we're developing. We have to identify first the best electrode materials. We're still processing a lot of new ideas and trying to implement them. We have not yet identified the ideal electrode materials. We have a good ohmic contacts and we have bad ohmic contacts. And sometimes the self-assembled monolayer doesn't work with the right material we want to utilize. So there is a lot of chemical developments, chemistry and implementation to be performed there. When it comes down to the semiconductor, why metal oxides appear to be better, and they are better, is simply because we are able to inject charges with much more efficiently into those inorganics than we are at the organics. Organics, we still suffer from a contact resistances because of the van der Waals interactions between the semiconductor and the metal injecting contact. We are trying to overcome this through surface modification of the contacts, using monolayers as in injecting intralayers. There are solutions, but this is the fundamental issue, and there's a lot of interesting work to be done there. So this is essentially the practical issues, and that's why organics a little bit worse than inorganics. But our recent work on organic diodes, which showed 14 gigahertz, is pretty impressive. It's not far away, much far away from the inorganic zinc oxide based and IGZO based RF diodes we made. Now, for the second question about the footprint, I'm afraid electronic industry footprint won't be reducing. I hope it will, but we haven't seen any example in the past where one technology, no matter how much better it might be, will reduce the carbon footprint. Often a more efficient technology will contribute to the proliferation of these devices. We'll have even more devices which are going to be offsetting any benefits. We have seen this with lighting industry, where we thought LEDs will be essentially make lighting much more efficient. It did make lighting more efficient, but at the same time, we now have LEDs everywhere, much more than we had incandescent lamps. So the overall power consumption going to lighting hasn't been really dropping. Similar process, I think, will occur with electronics. But what I'm trying to address here is not changing the way silicon chips will be manufactured, but making sure that the future generation of these larger electronics can be manufactured using as little energy as possible, therefore minimizing the carbon footprint. Perhaps we have to really pay a lot of attention on the materials and the substrates we're going to be using. For example, can we use biocompatible substrates together with metal oxides? Metal oxides are a very interesting technology as a semiconductor because most of them are fully biocompatible. You can drop them in your garden, it will dissolve away. It's not going to be a problem to the environment. So perhaps we have to start thinking more about green, more circular electronics that can be manufactured using these alternative technologies. This is what we're trying to do, but I don't believe there will be a reduction in the overall carbon footprint. As long the energy we're using coming from renewables, I think there will be some sort of effort and contribution to offsetting any carbon footprints quite effectively. I do think this is kind of the future for these emerging forms of electronics.
Okay. Okay, I think enough Dr. Julia. Yeah, maybe if you can continue to discuss by email or something like that. Maybe I have one short question from the Dr. Wayman. Short question, maybe Dr. Wayman, please.
Short question. Thank you, Prof. Thomas, for very interesting talk. So my question is about the way you make the nano gap. So the first approach where you use the glue, so it seems the glue is selectively delaminate at where the gap exists between metal 1 and metal 2. So how can the metal 2 remain intact in substrate there? So that's my question. Is it from the stress or? Yeah.
So exactly, perhaps I did not explain it very well. So metal 2 adheres on the substrate very well. We designed it to do that very well. But when comes atop the metal 1, because the self-assembled monolayer is there, the self-assembled monolayer has a very small surface energy to a point where the metal 2 does not stick on that at all. It just sits there. So the adhesion forces are very, very weak. And this is the reason when we peel it off, those regions delaminate while the interface between metal 2 and substrate remains very, very strong, and the metal remains there. Essentially, there's a fine balance between the gluer we are using and this process. If you use the wrong adhesion layer, a wrong glue, then you remove everything. So there is a window of adhesion parameters that allow us to perform this lift-off step.
Okay, I think enough, Dr. Wayman. Yeah, you can continue discuss by email maybe. Okay, thank you very much, Professor Thomas, for your very interesting talk today. Maybe just to summarize, maybe this is very interesting for the future, for the application in the nano manufacturing, for the solar cell, and then also RF electronics, and possible for another application like such as the photodetector and sensor. Maybe for the final one, we would like to, can you stop your screen, please?
Yes.
Okay. Maybe this is just our token of appreciation from the ICRAMET committee to Professor Thomas Diantopoulos from KAUS, Saudi Arabia. This is in recognition for the delivery of keynote talk in the 11th International Conference on Radar, Antenna, Microwave, Electronic, and Telecommunication ICRAMET. Okay, thank you very much for your presentation, and thank you for the all participants in here. And the time I will give back to the Master Ceremony, Dr. Ardita, please. Thank you very much.
Thank you for the honor.
Thanks to Prof. Thomas Diantopoulos, and also thank you to Dr. Yusuf Nurwijayanto. Moving on, we are having the second patron session today by Rohdian Swars, presented by Mr. Jurgen Kauschik, Mr. Andreas Lechner, Mr. Albert Leisner, and the Q&A session will be led by Mr. Kwek Ji Yao. Also, here with us, Mr. Firdaus Gutri as invited participant from Rohdian Swars. This session will be moderated by Mr. Arif Budi Santiko, NV. Arif Budiko Santiko, MT received his Bachelor of Engineering in 2009 from 10 November Institute of Technology or ITS Surabaya, and he received his Master of Engineering in Bandung from Bandung Institute of Technology in 2022. His research interests are radio frequency devices technology, BPF, power divider, substrate integrated waveguide filter, and he joined Indonesian Institute of Science, or now changed into BRIN in 2011. Please welcome Mr. Arif Budi Santiko.
Okay. Okay, good afternoon, participant ICRAMET 2022.
I'm Arif Budi from Research Center for Telecommunication BRIN. Will be serving as your moderator in this session. And welcome to patron session of Roden and Schwartz. First, let me talk about Roden and Schwartz. Roden and Schwartz is the company provides the technology such as wireless communication and RF test and measurement, broadcast and media, second, and air traffic control and military radio communication, cybersecurity and network technology. And thank you for your coming, Mr. Kwek Chiao as representative assistant manager and engineer, and Mr. Firdaus Kutri. Our interesting topic that will be presented by Roden Sweat is about ISA radar. Is a active electronic scan array radar front-end testing. This presentation will have duration about 50 minutes, 30 minutes for presenter and 50 minutes for question and answer. The participant can ask directly by raise hand in question answer session, and also you can write question on this Zoom chat. Let me talk abstract. The capabilities of modern ISA radar design depend significantly on the performance state-of-the-art transmissive module. In this webinar, our expert tackle the question of how to precisely validate TRM performance in the large array antenna and reduce complexity of testing TRM significantly with the help of the latest test system from Roden and Schwartz. Participants will learn about, first, solution for high test speed and throughput, second, multiple tests with one setup, and third, powerful test library to minimize testing effort, and fourth, how often device under test interface ensure high degree of confidentiality and flexibility at the same time. Now, moving along to our session, which presents Jürgen Kauscher as Project Manager for EMC, Andreas Lexner for System Development Engineer, Albert Glebner for Project Manager Network Analyzer, and Kwek Chiao as Assistant Manager Application Engineering. And for presenters, the time is yours.
Welcome to our webinar, AESA radar front-end testing. AESA radars are very complex. Today we want to show you how Roden and Schwartz can support you in testing during development and production. Together with me are Albert Gleisner, who will show the network analyzer details, and Andreas Lechner, who will show live test with a demo device and the test software details. My name is Jürgen Kauscher, and first I will give you an introduction to AESAs in general. AESA are the modern type of radars which allow multifunctional, multi-target and multi-role capabilities which all modern radars have. In addition, they are used for SAR, synthetic aperture radars, for example in space-based testing, satellite-based testings. The core of such a radar is the phased array antenna with thousands of antenna elements, and behind each of these antennas sits a TRM, transmit-receive module, which is the core element of the radar and is very important for the performance of the radar. This TRM itself is quite a complex device consisting of a phase shifter and attenuator and switch between transmit-receive, which requires a sophisticated control of the device during test. In addition, it has all the transmit chain, like power amplifier incorporated, and the receive chain with low noise amplifier and other components like filters, limiters, and combination of these. For such a module, for the characterization, you require many different measurements, and these are very different in type. On one hand, you test all the gain and phase with S parameter sets, but also power measurements like 1 dB compression point or frequency selective measurements like for the spurious test or filter measurements. In addition, time measurements, pulse characterization, rise-fall time, power droop, and noise figure. Combining all these different measurements typically makes these settings very complex and error-prone because you have many different types of measurement, different cablings, different parameters. In addition, the big challenge, second big challenge, is the test time. Because if you characterize such a module, for example, in production, you have thousands of different gain phase states in combination with all the other measurements. And that results in kind of 50,000 single test results, which must be analyzed and tested. A third topic is that the development of a TRM itself is already a very complex issue. And that is the core competence of a company. Developing the test systems around that, the test setups, requires in addition capacity and is very critical for the time to the market. And the fourth topic is the tests on such a TRM are always very similar, but the TRM itself is dedicated to the device. And that is always very special. To make such a setup, we will first have a look at one of the core components, which is the network analyzer, and Albert will show us the details of the network analyzer ZNA.
Okay. Jürgen, thank you very much giving me the chance to introduce our ZNA analyzers. So the ZNA analyzers are the new class of high-end vector network analyzers from Rohde & Schwarz. As such, they stand for a very high, excellent RF performance, where the very low trace noise, the stability, or extremely high sensitivity are just one of the, or some of the key characteristics which could be mentioned here. So the instrument is based on a comprehensive hardware infrastructure with a multi-channel concept and multi-source concept, which can be completed by a variety of options like the new internal combiner. Finally, on top we have a wide range of software personalities which allow for a complete characterization even of sophisticated devices like amplifier, receivers, transceivers, or like presented in this presentation, TR modules. Let me present some numbers. Just in brief, so far instruments were launched with frequency ranges from 10 MHz to 26.5 or 43.5 GHz. Both are available with ports with 2 and 4 test ports. Maybe the most common specification for a network analyzer is the dynamic range. Besides a specified value of 129 dB, we can reach up to 170 dB, an incredible number which can be reached in the lower frequency range, of course here using options and, for example, 1 Hz IF bandwidth. The maximum power ranges up to 20 dBm and is combined with a very high power sweep range of 100 dB. The noise floor is also an outstanding quantity here, with a specified value of -120 dBm or a typical value of up to 150 dBm, which ensures noise-free and very accurate results even with very low signals or very fast antenna testing. Finally, here you find some numbers for stability and the temperature dependence, providing also high accuracy even a long while after calibration. Let's have a look to the hardware. Here I'd like to present you the front-end picture of the fully loaded 4-port instrument. So to make you acquainted with all these lines and boxes, let me pick out some options. With the brown-colored and green-colored boxes, the generator and receiver attenuators are shown. And of course, we provide this common option, which is the direct generator and receiver access. Here the blue boxes and lines symbolize a new option. In principle, it allows you a selection if the reference signal should be split up before the step attenuator and or after the step attenuator. In the end, this option allows to pick up the signal even for very high gain devices before the step attenuator, allowing to have a fairly high signal in the reference channel, even with a very low stimulation power. So in the end, this ensures that you have low noise, traces, and accurate results, even with a very low stimulus power with high gain devices. As a new option, we provide as well an internal combiner for two-tone signal. The instruments can be equipped with pulse modulators and pulse generators, so there is one pulse modulator per port available. The 4-port unit comes with 2 sources by default, and this can be expanded with an option to have up to 4 internal sources, so even intermodulation measurement with on a double converting device can be carried out with high flexibility without the need of external boxes. And finally, you find here the multi-receiver concept, meaning there is a separate reference and measurement receiver per port. So the 4-port unit provides up to 8 true receivers without any multiplexing, so you can easily carry out multi-antenna, multi-receiver measurements. Finally, let's have a brief view on the software capabilities. So whatever your challenge might be, like here, dealt in this presentation, TR module testing or testing of related devices like amplifier mixers or antenna testing, ZNA has a wide range of solutions ready for you, which consists in the control of the multiple generators, configuration of multiple receivers. There are features and options for extensive amplifier testing, for mixer and converter testing. You can have the mixer phase without further accessories, and there is, for example, also a special feature to measure even the group delay on embedded LO converters or to find spurs with the spectrum analyzer mode. All this is completed with a nice configuration method, which is called DUT-oriented configuration, and completed by special calibration procedures like the smarter call. So that's been with a brief introduction of the ZNA vector network analyzers. Thank you so far, and I'd like to hand back to Jürgen. Thank you.
Thank you, Albert. And that is what makes the ZNA the ideal component for such tests. It can cover all the different tests just in one box. And that is also the setup we have today here. Of course, you can also use the predecessor of the ZNA, the ZVA, which is running in thousands of labs already for TRM tests, together with the signal conditioning box ZWAX TRM, for the same purpose, having all these tests available. And it's also possible to combine this to smaller system solutions together with specialized signal conditioning, which allows also multiplexing and very flexible module control, emulating all the typical interfaces like LVDS or RS422, 485, or, and that's on the right side, you can also have complete turnkey solutions covering all the requirements you have in a complete project. So far, the hardware configuration, which reduces the setups to a few core components. What is missing now is the automation, which allows to run these tests in a very convenient way. And Andreas will show us this now.
Thank you, Jürgen. I will show you now the Rode & Schwarz standard software for TRM testing. Because of the many different requirements that TR module customers usually have, we have decided to use the common Rode & Schwarz sequencer software called TS-Run. This creates a flexible environment for radar testing solutions. You can arrange the tests in your preferred way, and you can adjust many predefined parameters for each test. Some parameters can be set here in the software in the TRM test system dialog. These are the global settings that has to be done for the complete test plan. In some applications, additional RF switching is required, For that, we have implemented an application unit dialog where you can describe all the different logical RF paths with the corresponding Skippy commands. All instruments has to be registered in the Skippy connections dialog here together with the remote control interface. Here you can see the complete list of implemented tests that we currently have. Via a double click on a single test, you can open up a test plan with a test in it, and you can see here the white yellow lines which shows the parameters that can be modified by a customer. For example, you can change here the frequency to your specification of your DUT. It could be, for example, 5 GHz up to 6 GHz. Of course, you can also adjust things like the source power, the measurement points, or the measurement bandwidth. If you want to add more than one test to the test plan, you have to open up the test editor. Here in the test editor, you can easily add tests via drag and drop here to the test plan. This is the way how you build up your complete test plan. In some cases, it makes sense to add a test more than once to measure a test with different parameters. There is some basic functionality here in the Commands tab where you can add declarations, if then else decisions, or loops. This is necessary if you want to repeat a test more than once. If you click on the OK, the editor is closed and you can see all the parameters of your complete test plan here in the yellow-white list. By clicking on a single test, you will see only the parameters of that test. If we save the test plan, all the setted parameters will be stored in that test plan file. Now I would like to show you a live test run with our low-power DEMO TR module. For that, I have prepared a test plan with 19 steps. 3 common tests for setting up global DUT parameters, 8 RX tests, and 6 TX tests. The first test is for reading the barcode from the DUT. This is helpful if you want to see the serial number of the DUT in the report. The second test is DUT selection. This is necessary if you have a multi-channel DUT or if you have more than one DUT connected to your instrument. The change pulse settings possibility if it's necessary during a test plan run to change the pulse width or the duty cycle. Here in the receiver tests, we have the RX intermodulation and the RX noise figure test that is currently not yet implemented for the ZNA, but this will be launched very soon. It's already on the roadmap. Now, via a click on the Run button, but first I want to show you the real instrument. Here we can see the instrument screen of the ZNA. And if I run now the test plan, here the measurement report tab opens automatically. On the right side, you can see the power sweeps for the compression point measurement. And here on the left side, you can see how the live report is generated directly with measurement graphs. This is the S-parameter test. Here you can see the different attenuation states and now the different phase states. Now we are measuring the filter curve of the DUT, so it was a little bit short. So here you can already see the result in the report. Due to the high dynamic range of the ZNA and the spectrum analyzer option, we can measure spurious emission very fast and to very low levels. The internal pulse modulators enables the network analyzer to measure all TX tests directly without any additional components. The measurement result looks very similar to the RX tests because the ZNA internal triggering ensures that we are measuring only during the pulse. The pulse profile test that we can see here is the only test that shows us the real shape of the RF pulse. Additionally, you can see it now here in the report. After the complete test plan run, a final report is generated. Currently, there are 3 formats available: an Excel report, a PDF report, and S-parameter test generates additionally S2P files for every state. By clicking on the Reports tab, you could open up the file browser where you can see the Excel report that shows us a summary sheet here on the first page with the pass-fail verdict coming from the limit management we saw at the beginning. Here every test has a line for its results. So how you perhaps already recognized, we have a fail here for the phase error in the RxS parameter test. Now if we want to analyze this in detail, we can have a look here at the different sheets. For example, here for the Rx phase error. And here you can see how the measurement curve crosses the limit line. This is the reason why we see in the summary sheet here the fail. If you like more printable reports, then perhaps the PDF report is the right choice for you. For a very detailed analysis of all gain phase states or generating correction data, we having a zip container that contains all the S2P files of all the states. Now I would like to show you the calibration concept of the software. The calibration is a very powerful function of the TRM software. The idea is that you create your test plan first and you adjust your test plan with the test parameters to your DUT requirements. If you have a rough test plan, you should run it in a calibration requirement collecting mode without any DUT. After that, you could start the calibration. The calibration sorts the requirements for an operator-friendly calibration process. This means screwing for different calibration equipment connections like power meter or calibration unit will be reduced as much as possible. Finally, you could have very complex test plans with short calibrations. Additionally, you will benefit from less screwing cycles that ends in a longer equipment life and less operator interactions, which avoid handling errors. Another important point is the DUT control. Many TRM development or production facilities are classified areas, and it is not possible that other companies writing DUT control software. This is the reason why many customers do the whole test automation by themselves. But we solved that problem with a DOT control interface that is completely open source. We deliver a full implemented source code example with the software to make it as easy as possible for you to implement your own duty control. In an unclassified scenario, we could offer this implementation on a project basis. Here you can see how the interface works. Every test, this is a gray box here, invokes
Recording in progress.
Kita masih mute. Tidak.
Okay, sorry for the technical issues. Now we are trying to solve, so please wait a minute. Thank you.
Here we can see the rating correction data. We having a zip container. You could have your own duty control. In an unclassified scenario, we could offer this implementation on a project basis. Here you can see how the interface works. Every test, this is a gray box here, invokes the digital control implementation at many points to give you the chance to change the DOT state during a test. Every function call gets the test information of the currently executed test. This helps if the DOT needs special commands for specific tests. If you need a full automated solution for your high-power DOT, we can offer full integrated switching solutions with amplifiers, high-power couplers, and port multiplexers for multi-channel DOTs. That's from my side. And now back to you, Jürgen.
Thank you, Andreas. So let's have a short look at the summary. The complex and error-prone testing is now by the software reduced to a one-time parameter definition that makes the testing much easier and reproducible. Especially in production, requires a very efficient testing of thousands of TR modules, so the test time based on the long experience of Rohde and Schwarz and TRM tests ensure a high throughput in test. The test configuration is reduced to only a few core components, which simplifies the test setup and calibration. And customer-specific test requirements are covered by parameterization, open DOT control, and the possibility of a customization so that the specialities of every TR module which are not standardized are covered and the core know-how of the TRM is protected. We have presented you an open and efficient TR module test solution. If you need any further information, please don't hesitate to contact us. Thank you, Albert. Thank you, Andreas, for the presentation. And thank you to you all listening out there. We will be happy to support you in your TRM testing in future.
Okay, thank you presenters for addressing interesting topic. And we have 50 minutes for our participant. If you have any question, please raise your hand or type in meeting chat.
Mr. Budi, sorry, I think you are still unmute yourself. We cannot hear you.
Yes. On meeting chat, there is no question. And how about the participants? Okay. Okay, Mr. In chat room from Mr. Yu Wahyu from Research Center and Telecommunications. Does the TRM measurement system work for all different types of products?
Thank you, Professor Arif. So I'm Craig here, so I will answer the questions. So basically, the TRM system that we showed here is mainly for the front-end testing. So if your product is at the front end, of course, all the parametric that has been shown in the presentation can be tested. So all kind of parameters such as the spurious measurement, the noise figures, the S parameters, all these are possible and can be tested in a very, very fast speeds according to the systems. And in fact that because each of these TRM module, they have their own control systems as mentioned in the presentation. So there is a possibility to control these TRM modules here. So if your product is basically at the front end side, even for example, the phase array antennas, or the phase shifting or the any modules that is in the front end, yeah, this system can indeed make the measurements.
Okay, thank you.
Okay, thank you. We have 10 minutes left and maybe have some question from participants. Can raise hand or chat in meeting chat. Okay, raise hand. This is for Mr. Dayat Kurniawan. Now it's yours. You unmute. You unmute.
Okay, sorry.
Okay.
Okay,
Okay.
I have a question. Can you tell us about your product related with 5G or 6G texting? Or maybe like a MIMO system, I think.
Basically, if you look at the systems here that we have, it is mainly 4-port systems, if you can see. So internally, there is 4 source, coherent source, but mainly these systems here testing is what we can do is mainly for the radar systems. So where you have the modulated pulse measurements, right? So pulse measurement can be sent out through these four ports that comes out. But of course, this is not exactly a MIMO system indeed, yeah, but just you can test it in terms of phase coherence between different ports. So this is very important, especially if you are talking about phase coherence in terms of you want to make sure that each output has a different but defined phase. So these are usually very important for the antenna measurements. Yeah. So also for the TRM. But in terms of MIMO wise, these systems does not really cater for the MIMO because it is only generating pulse signals modulated, and it is not for the communication part of the testing.
I think the next question about your TRM modules is support MIMO system. How many antenna that can support your model TRM?
Yes, definitely. Of course, that is possible because any, like for example, as I said, if it's antenna wise, definitely we can test with this system here.
Many antennas, like 4.4 or something more than 4 antenna for MIMO support.
You mean
How many antennas?
You mean you want to know what kind of antenna? Are you?
No. How many antennas can be installed on your TRM module?
Oh, how many antenna?
Yeah.
Four antennas. Yeah, but that's the reason why if you have phase array, which could be many thousands or more than that, so there is a switch systems in this antenna system here, or these TRM systems here. So there's a switches. So although we just have 4 ports that can be measured, but with these switching systems, you can actually test them in sequence, and then of course then you can test many more antennas if you have in them or in arrays. So this testing is then become very fast indeed, from based on the system here.
If we want to set up with more than 4 antenna, it means we must add TRM module again.
Yes, with the switch system, yes.
Okay, thanks. I think enough for me.
Thank you.
Okay, we have 4 minutes left. Maybe one question for participants. From chat room, there's no. There is 4 minutes left for one question. Okay. Okay, maybe Mr. Kwek Chio, the time is over. And on behalf of Committee ICRAMET 2022, we would like to present you with token of appreciation.
Thank you.
Wait. This is a token of appreciation awarded to Jürgen Kauser, Andres Lechner, Albert Gleitner, and Kwek Chiao from Rohde and Schwarz in recognition for delivery of a patron talk in the 11th International Conference on Radar Antenna, Microwave, Electronic and Telecommunication, ICRAMET 2022. And thank you, Mr. Kwek Chiao.
Thank you.
Okay, now let's get to MC.
Thanks to Mr. Arif Budi Santiko, Andreas Lechner, Mr. Albert Gleisner, and Mr. Kwek Chiao from Rohde and Schwarz. Now we are starting our second parallel session from session 4 to session 7. The main room will be divided into 2 breakout rooms. And similar to before, our host will first assign presenters who are presenting in the respective session based on the program schedule. For the rest of the participants, you are free to move between rooms by clicking the breakout rooms to join the available rooms. And here are some reminders for presenters that has been also outlined in the guidelines. 1, keep the naming convention according to the guidelines so our host can monitor if any presenters are in incorrect rooms. We encourage you to keep logged on during the break. For the presenters that are in their assigned sessions, please turn on the video for the whole session, including when you are not presenting. Please be reminded it is compulsory for presenters to be present at their respective Q&A sessions. Do not forget to fill in your attendance form as the presenter when you are in your own session. Please also have your presentation slides ready for the Q&A sessions. For all the participants who want to ask some questions during the Q&A, please use the raise hand menu that can be accessed from the reactions menu in your Zoom application. After the first session, there will be short afternoon breaks. Please remain logged on in your breakout room since the rest of the program will be conducted in the breakout rooms. I'd like to remind everyone to stay focused and engaged during this session as well. Thank you, and please enjoy the parallel session.
Recording in progress.
Good day, everybody. I think we can start. I'm the moderator for session 5, remote sensing and radar systems. My name is Frans Paul Pieterse. I'm from the Council of Scientific and Industrial Research, which is based in Pretoria, South Africa. So first, I just want to quickly read the list of presenters in the session. So first of all is Iman Firmansyah from the National Research and Innovation Agency, BRIN. Then we will have Guo Bai from Southwest Jiatong University in China. Thirdly, we will have Bayu Satya Achitama from the National Research and Innovation Agency, BRIN. And then finally, we'll have Budaman Putra Ashmur Roman from the National Research and Innovation Agency, BRIN, also in Indonesia. So just a few notes that I want to quickly share with you. So for the presenters, please keep your video on until the end of the session so that we can have a screen capture session at the end. For everybody in this room, please fill in the attendance form, which will be shared by the co-host in the chat. For the presenters, while presenting, have your slides ready, so that you are ready when questions are presented to you after your presentation is given. All of the presenters should be present during their own question and answer session. And finally, if any participants have a question, then you should just raise your hand, and then I will ask you to unmute yourself and share your video, and then you can ask your question. So yes, I think we should start. So Mr. Iman Firmansyah, are you ready? I think your time can start now.
Yes, I'm ready. You can start my video. Hello everyone, my name is Iman Firmansyah. I am from National Research and Innovation Agency, or BRIN. So in today's presentation, I'm going to explain about FPGA-based implementation of IQ chip signal generator using memory-based technique. Okay, so this is our outline for today's presentation. The first, I would like to introduce the objective of our research, and then it is followed by introduction to chip signal, and then how to develop IQ chip signal using FPGA, and then we are going to show you our experimental result, and finally it will be summarized by a conclusion. Okay, so this is our objective. So in this study, we evaluate an FPGA-based IQ chip signal using FPGA by leveraging a memory-based technique. So our contribution is how to reduce the FPGA result. So we perform that by using single block of accumulator as an address generator to generate the IQ chip signal. Okay, let me first introduce what the chip signal is. So basically, chip signal is a sinusoidal wave whose frequency increase from low to high or lower from high to low. And then due to signal properties, usually it can be found in radar application, particularly to increase the range resolution, or we can say by using chip signal, we are able to detect two different objects. And this is equation for the chip signal. As we can see that the chip signal consists of cosine wave and sine wave. So for or we can, in other words, we can say this is for the real part and imaginary part. And then the beta means the frequency bandwidth that will be covered in the next slide. Before we perform experiment, we try to simulate our target chip signal. So this is the simulation result. As we can see in this experiment, we perform the experiment by generating chip signal with the 10 megahertz of frequency bandwidth within 10 microseconds. So as we can see, this chip signal consists of real and imaginary part, where the duration is 10 microseconds. As we can see, this is 10 microseconds, and for the bandwidth, it is 10 megahertz of bandwidth. So both for real part and imaginary part are similar. And then where we can find the chip signal generator. Okay, this is one example of where we can find the chip signal generator. This is the block diagram for the radar application. This is for the transmitter circuit, and this is for the receiver circuit. So as we can see, the chip signal generator lies here. So it will produce a chip signal that will be modulated and then transmitted and then received. Okay, in this study, we propose design in order to reduce the FPGA resource. That's why we realize our chip signal using memory-based techniques. This is the simple one, and then to reduce the circuit, we use one single accumulator as an address pointer, where this address will point the lookup table that store the data for the real part and imaginary part, and then the content of this LUT or lookup table will be generated by DSA controller to DSA to produce the chip signal, both for real part and imaginary part. And then by implementing the mentioned purpose design, we are able to generate the circuit that will be implemented into FPGA. So in our experiment, we use a Cyclone 5 Cyclone for FPGA from Altera or Intel. As we can see that similar to the previous one, we are able to generate the accumulator as an address generator, and then we also produce we use lookup table for the real and imaginary part, and this part is the DSC controller that will interface with the external DSC chip to generate real and imaginary part of the chip signal. So in experimental setup, we use cyclone for FPGA, and then to generate the digital signal to analog signal, we use 14-bit resolution of DSC, AD9767 DSC. So this DSC board consists of 2-channel DSC that will be used for generating real and imaginary part of the signal. And then the output will be analyzed or captured by using digital USB oscilloscope or spectrum analyzer. Okay, so this is our experimental result. As we can see that by implementing our proposed design, we are able to generate real or imaginary part, or we can say I and Q chip signal simultaneously at the same time. This is for the real part, and this is for imaginary part. As we can see that the chip duration is 10 microseconds. So if we measure from the beginning until the end, the duration is 10 microseconds. So this is our experimental shot. And how about the bandwidth of the chip signal? Okay, so we, by using let's say spectrum analyzer, we are able to measure the bandwidth of our chip signal. As we can see, both for the real and imaginary part, we are able to measure the bandwidth of our chip signal. As we can see, the bandwidth is more or less 10 megahertz for the real part, and for imaginary part, it also produces the same bandwidth. But chip signal has the similar bandwidth, 10 megahertz. Okay, so because in previous slide, we mentioned that our contribution is how to reduce the FPGA circuit. This is, which means that our design can be used in small FPGA. That's why we use only single accumulator. As we can see from our experimental result, by implementing our proposed design, we are able to use the FPGA resource as small as possible. As we can see from this experiment, our design only consumes only 1% of logic element of cyclone for FPGA. So this means that our design requires less FPGA. So we don't have to use medium to high-class FPGA. And then for the experiment, we use 10 megahertz of frequency clock that will be used to trigger the external DSC. Okay, so this is our conclusion. We can summarize that in this experiment, we are able to generate the IQ chip signal by using FPGA simultaneously at the same time. So our generated chip signal produce similar properties compared to the simulated one. So between the simulation and the experimental are comparable. And then in this study, to reduce the FPGA resource, we employ the single accumulator. That is, this implementation effectively reduce the FPGA resource. Okay, that's all from me. Thanks for listening. Terima kasih.
Okay, thank you very much. That was very interesting. Are there any questions for Mr. Firmansyah? I do not see any questions. Okay, so I have a question then. You said that you used 42 logical elements to implement the, sorry?
Yes, okay. Okay, go ahead.
Okay, sorry. Okay, so you said you used 42 logical elements to implement this for DDS in this case.
Yes.
How many elements do such devices usually use then compared to what your system use? Do you know that perhaps?
Okay, thank you for the question. So that question is a little bit tricky to answer, but for the detail, in my experimental research, I didn't calculate in every single circuit. So what I saw you just the whole circuit. So, but usually when we develop a higher resolution, let's say in our cases, I just use only 4-bit DSC and then more or less 10 kilo of data inside for the lookup table. That's why I only requires 1%. But let's say when we want to increase the bandwidth of the chirp signal, as a result, we need to use a higher resolution, not only DSC, but also the data. Of course, it will require more FPGA logic, but it's depend on the application. So in my study, okay. So in my study, I just saw that our proposed design can use small FPGA, but if you want to change the specification, it requires more FPGA research, of course. Okay, thank you.
Okay, thank you very much. So I think we can go on to the next presentation. So that is Guo Bai from Southwest Yatong University in China. So please play the presentation.
Hello, everyone. It is my great honor to participate in this conference. My name is Guo Bai. I come from Southwest Jiaotong University, China. Today, I'm going to introduce a novel method for diagnosis of time-modulated arrays based on compressive sensing. The time-modulated arrays have been widely proposed, and this figure is a typical structure of a time-modulated array. The time-modulated array is composed of a traditional antenna array and the specific feed network, which composed of a power source with RF switches, which are controlled by a FPGA. This kind of structure can reduce the hardware cost and enhance the radiation characteristics. However, the RF switches and the antenna elements can fail in a TMA due to the continuous on and off switching operation, which can greatly affect the performance of TMA and result the decrease of directivity and the radiation efficiency, the increase of side lobe levels, and the undesired sideband radiations. Here, for example, the left figure is normalized time sequence distribution of a 16-element linear TMA in one period, which is optimized by differential evolution algorithm. And this kind of time modulation can simultaneously realize the beamforming at the center frequency F0 and the first harmonic frequency F0 plus minus Fp, where the Fp is the time modulation frequency. Specifically, the TMA produces a low SL pattern at the center frequency F0 and a flat top pattern at the first harmonic frequency. And if we consume that there are two elements are failed, so we can see that both the low side lobe level pattern and the flat top pattern are greatly distorted. So it is necessary to find where the element are failed so that we can replace them to correct the radiation pattern. So in this paper, a novel method is proposed for diagnosing impaired TMAs to determine the locations of the failed elements and restore their excitations. The comprehensive sensing framework is applied to the diagnosis for TMAs, and the novel frequency joint diagnosis method is proposed to improve the diagnosis accuracy and reduce the number of sampling points. So next, we are going to introduce the mathematical formulation of our proposed method. First, the array factor of a planar TMA can be expressed as this formula, where the UNT is the time modulation function, which can be expanded into the Fourier series due to its periodicity. And here, ANK, we call the Fourier coefficient, and it can be calculated by this integration of the time modulation function. So use the Fourier series, we can replace this formula into this one. Here, the WNK, we call the equivalent excitations of the nth element at the frequency of F0 plus minus KFP. And if there are some elements are failed, using the difference between the original pattern and the impaired pattern, a virtual pattern can be expressed by this formula, which generated by the delta WNK, and this stands for the impaired element excitations. So the diagnosis problem for TMAs can be expressed as a sparse recovery problem at the case harmonic frequency. So here is a L0 norm minimization problem, but this kind of problem can be hard to solve using conventional method. So here, a multi-frequency joint diagnosis method for equivalent excitations at different frequencies can be considered. And this kind of problem actually is the regularized problem of the L0 norm minimization problem. And we used a mixed L1 and the L2 norm to replace the L0 norm. And this kind of mixed the L1, L2 norm is defined as this formula. So this kind of problem is actually a convex programming problem, and can be solved efficiently by some commercial toolbox or open access toolbox. Here, we use the open access toolbox called the CVX toolbox to solve this problem. And next, we are going to show some numerical examples for validation. And first, the 16 element TMA we just discussed before are considered, and there are, as shown in these two figures, these two elements are failed both at the F0 and F0 plus FP frequency. And using the proposed method, the two failed elements are determined and their excitation amplitude are restored by using 6 measurements with a signal to noise ratio of 15 dB. So this result shows that our proposed method can successfully find the field elements. And using the equivalent excitations, we can also estimate the time modulation function of these two field elements. As for the planar TMA, in this two figure, we can also find the field elements as shown here and here at the center frequency and the first harmonic frequency. And the results are better than that of the L1 normal minimization methods, which are widely used in comprehensive sensing frameworks. So as for the time consuming of the proposed method, and the CPU time is also better than that of the conventional CS-based method, such as L1 normal method. So this result shows that our proposed method very good for the diagnosis for time modulated arrays. So in this work, a new diagnosis method for impaired TMA based on the CS is proposed, and the proposed method can jointly diagnose the equivalent excitations of each frequency and then determine the location of the field elements and recover their time modulation functions. Finally, the numerical examples and the comparison, including linear TMA and planar TMA, successfully demonstrate the effectiveness of the proposed method. So this is the reference of our paper. So that's all about my presentation. If you have any question about our work, please contact me through this email. Finally, thank you very much.
Okay, thank you very much. This is also a very interesting presentation. So I see in the chat there are two questions. So I'm just going to read the first question then. For compressive sensing reconstruction algorithm, do you consider other methods like from the class of matching pursuits, etc.? To my knowledge, convex optimization could lead to NP-hard problem.
Okay, thanks for the question. So for the CS reconstruction algorithms, there are about 3 kinds of algorithms for addressing the CS problem. One of them is the matching pursuits. Okay, this is also a good and fast method for addressing the CS diagnosis problem. However, this problem cannot be applied to some high noise circumstance because it is computation method will lead some wrong or no sparse result for the signal recovery. The convex optimization is known as its high robustness for solving the sparse reconstruction problem. However, it also, as the answer shows, it also can lead to some NP-hard problem. As I discussed in my presentation, so the L0 norm minimization problem is actually a NP-hard problem, but in our paper it was transformed to a convex problem, so it can be successfully solved by the convex optimization problem. So that's all I want to say about this question.
Okay, thank you very much. I see there's another question, but we are a little bit tight on time at this moment. So I think if the person asking a question can just perhaps send you an email and ask you via email. So can the co-host please play the presentation for Bayu Satya Aditama, please?
Okay, ladies and gentlemen, greetings. My name is Bayu Satya Aditama, and I am from Research Center for Remote Sensing of National Research and Innovation Agency, or BRIN. In this moment, I will present about our project or research, which is development of the NOAA-19 satellite data receiver ingest system based on FPGA. This research is led by Mr. Ali Syahputra Nasution. This presentation mainly will discuss about the introduction and the background of why this research is held, and the second, the design system of the solution we are offering in this research, and the third is the results of the implementation of our design, and the last is the conclusion of this research. Meteorological satellite data is widely used by many ministries and institutions in Indonesia, and it is received by our receiver system or ground station. And in the right-hand side of the table of the slide, we can see a table describing characteristic of each meteorological satellite that we are acquired. And we can, in this particular research, we can focus only to the data rate characteristics of each satellite. NOAA-19, it has the lowest number of data rate, which is 0.7 megabit per second, and Landsat 8 and 9 has the highest number of data rate. This data rate in the future will only getting higher and higher, so the data will be transferred faster. This is happened due to the advancing technology of satellite system, and this is require some subsystem of the receiver system to be upgraded or to be improved. But the problem is the majority of system vendors, they only offers end-to-end solution of receiver system. So it is a very low chance they are providing only some subsystem of the receiver system. And the subsystem that requires further development is ingest card, and it has very high correlation with the data rate characteristic of its satellite. Basically, an ingest card is a device, so the data from the modulator can be ingested to the PC computer in the form of the raw data of its satellite. Currently, the working workflow of our system is the antenna send the RF signal to the demodulator, and the demodulator send data to the ingest card, and the ingest card will be processed the data from the demodulator into the form of raw data and store in the PC ingest. This research, through the research, we propose an FPGA-based ingest card, which the main goal of its development is the capability of receive data stream and clock from the demodulator of NOAA-19 satellite, and will give output via the UART serial interface. The overview of the design that we are developed is the FPGA-based design. The ingest card FPGA-based design will get data from the demodulator via serial data adapter, and it will output the data and save the data to the desktop PC through the serial UART to USB converter, or popular with FTDI. The development workflow of the system, it is a generic FPGA design and development workflow, which is consists of a design entry, which is a stage where we code the VHDL or very low code, And then we are doing functional simulation, do some synthesization by the software, implementation, timing simulation, and device programming into the FPGA development board. And the hardware and the software that we are using in this research are a PC which has an Intel i7 processor and 16 GB of RAM, and the main device is the FPGA development board, which has Altera Cyclone 4 as its FPGA core. And also we are using the existing demodulator in our office, which are Quorum LRD 100 and FTDI USB to RS422 and Altera Quartus software. The design, the schematic of the design is, as we can see in the left-hand side of this slide, the clock demode and the data demode. It is a represent of the data that coming from the demodulator into the FPGA or ingest card of our design. So the data demode, it will go into the serial into parallel converter block. The output of this block has to output. It is a parallel 8-bit data and parallel 32-bit data, and we can focus on only on the 8-bit parallel data in this particular research. After that, it will come to the block that will bypass the data, and then it will come into the block UART converter block. So basically, this block will convert the serial data 8-bit into the UART compatible serial data, and it will output the UART-TXP and UART-TXIN. Basically, it's a UART which has same data but with opposite polarity of its UART. In the right-hand side of the slide, we can see the assigned label of the schematic into the physical pinout of the development board. And this is, we can see the picture of the actual implementation of the design. The demodulator, we can see, is the silver device in the back, and the FPGA development board is the blue device. Based on the test result, this FPGA design able to convert the data from the demodulator into the UART data. And we can see the result of the data that is stored later. But first, we can see the signal, the timing that is resulting from this design. We can see from the clock demode and the data demode pin or label, it is the data from the demodulator. And we can also focus on the UART-TXN and UART-TXP. By looking into this signal, we can say that the UART-TXN and TXP, this design is able to convert the data from the demodulator into the UART-TXN or UART-TXP. And we can see the save or the stored data, resulting data from this design later in this presentation. And we need also to set up the computer so they able to receive the UART data with the desired settings. And this is the resulting data from our ingest card, our FPGA ingest card. The resulting data in this test is about 72.7 megabytes of size. And we can see in the right-hand side of the slide, it has its hexadecimal format of raw data files that is stored in the PC ingest, and by this research, we can safely say that the ingest card, FPGA in the ingest card that we are designed and developed, it able to store the data from the demodulator and convert it into the UART compatible data and store it into the PC. So the conclusion of this research is the development of an FPGA-based ingest system is already carried out. The design of this ingest system shows that it is capable to receive real-time data from the NOAA-19 satellite and convert it into the UART data and store it in the PC. And this design will be further developed so it is able to receive other satellite data, maybe like METOP or GPSS. And also if we decide, if we want to using the higher speed data transfer from the FPGA phase into the PC phase, we can use the FTDI UART, which has a higher speed capability. And that's all from us, and thank you.
Thank you very much. Does anybody have any questions for the speaker?
Okay, I have one question, please.
Okay, please go ahead.
Okay, thank you very much. Thank you for the nice presentation. So I have one question. So could you please tell me the reason why you develop your design using FPGA? According to your presentation, you only receive in serial data, UART. Is it possible to replace with, let's say, with ARM microcontroller and something like that? Okay, thank you very much.
Okay, thank you, Mr. Iman, for the question. Basically, if we want to replace the FPGA to the ARM or another microcontroller based, we can do that actually, but our main big goal is to be able to process data from the demodulator that receive data from the satellite, and it has a specific characteristic that it needs to be it needs the ingest card to be able to process data with many parallel data input and parallel data output. So for our main big goal, using FPGA is the best option, but for only particular topic into converting data from demodulator to UART, we can simply replace it to the ARM or another microcontroller.
Okay, thank you very much.
Okay, are there any other questions for the speaker? Okay, so thank you very much. It was a very interesting presentation. I think we can then move on to our final presenter. So Mr. Budiman Putra Asmor Roman. So can a co-host please play the presentation? Thanks.
Okay, hello everyone. Now in this session, I am Budiman Putra Asmaur Rahman from Research Center for Telecommunication BRIN. Will present the result of our study titled Toward a Compact and a Reconfigurable Radar UAV for Remote Vital Sign Detection. So about 10 minutes ahead, I will give the presentation with this outline. First, we will describe the radar for disaster, and then we'll explain the research objective, continuous wave radar for vital sign detection, system integration of radar UAV system, experimental setup, result of preliminary evaluation, and finally we will make a conclusion from this study. So now radar systems have been explored for helping search and rescue mission in post-disaster area. And one of the approach is by using the radar to search the survivor behind the debris. And this is the scheme. So this is the radar. This radar is put on the top of the debris. And then the radar will detect the vital sign of the survivor inside of the debris. And all of these pictures are the application of radar in some different areas and countries. So we can conclude that the use of radar for detecting or searching survivor has been explored in many areas and by many researchers. However, although this technology is very helpful, this approach is actually not effective because we need to put the radar in every suspected area. And of course, it is dangerous for SAR personnel. And based on this background, now many researchers try to develop a radar UAV system for supporting the survivor search mission. And this technology can be remotely controlled by SAR personnel so that the personnel don't need to visit every suspected area. However, in the very large observation area, a more advanced technology is needed to make a mission can be completely fast. Since we understand that the time is very crucial in case of SAR mission. So we think the use multiple compact and small radar UAV system is more promising. So this is the illustration in case we employ the multiple compact radar UAV system for helping search and rescue mission. And some researchers has explored the use of a radar UAV for vital sign detection, such as Rong et al. In the 2021. I used the commercial ultra-weapon radar for detecting the human vital sign. Rahman et al. Used the 2 single-channel X-band MDU 1020 radars to detect the vital sign. And then the Nakata et al. In the 2018 used a microwave solution MDU 1100T with frequency 10.5 GHz radar modules. And actually there are many other research correlate with this topic. However, most of the studies I use commercial off-the-shelf radar. Of course, the radar has fixed parameter and configuration so that we cannot easily change them. And besides, some of them also employ a big and complex radar UAV system. You know that in the situation of the disaster, after disaster, we need a compact, flexible, and easily deployed system. Thus, in this study, we try to propose a compact, small, and reconfigurable radar UAV system for survivor search mission. And in the current state of development of radar UAV, we employ a continuous wave radar system for vital sign detection. And this is how the system works. So the CW Doppler radar works by transmitting an electromagnetic wave we express as T in the time domain with a singleton frequency F. And this is the mathematical expression. So F is the frequency and this is the phase of the internal radar. And when this signal hits human at a distance D, there is a periodic movement because of the human respiration and also the heartbeat. This is the amplitude and also the frequency respiration, and this is the amplitude and frequency of heartbeat. Because the total distance acquired by the radar signal is 2D, so that the received signal expressed by the RT like this, can be expressed like this. And the signal is then processed and analyzed for check the existence of the respiration or heartbeat. And this is the development system. So we use the SBC, single board computer, SDR, software driven radio, and also LNA, low noise amplifier. And we employ 2 antennas, transmitting and receiving antenna. And we put the transmitting and receiving antenna in here. And this is a single board computer, SDR, also LNA. We also employ the external power supply for powering the SBC, SDR, and also LNA. For the SDR, we use LAM SDR mini with a frequency 10 megahertz until 3.5 gigahertz. And in the experiment, we use antenna with frequency rings 1.5 until 9.5 gigahertz and 0.9 until 6.5 gigahertz. To evaluate the developed system, we have done some experiments with this setup. So this is the setup, this is the antenna, and this is the SDR. And to simulate the drone vibration during hovering, we install the unbalanced motor in the right and in the left side. And we also employ the artificial human respiration in here, and we also put the artificial human respiration behind the barrier to simulate the obscured detection case. And for the first evaluation, we check the waterfall frequency display with two different respiration rate, 0.3 until 0.6 hertz. And from these two features, we can observe and distinguish the pattern of those frequencies which confirm the work of the system. Then we compare the signal recorded in direct detection and also obscured detection with three different respiration rates. And from all of these features, we can see clearly that the amplitude in the obscured case become lower than in the direct case. This is caused by the attenuation of the signal by the barrier. And in the third evaluation, we observe the effect of vibration to the radar signal. And this is in the respiration rate 0.3 hertz, 0.6 hertz, and 0.8 hertz. And we can see clearly that the vibration makes the noise, and the noise can mask the recorded vital sign. However, the respiration in all observed cases still can be detected, and the respiration rate can be distinguished. And the conclusion of this study is, first, we have reported on the progress on the development of UAV-borne radar based on SDR for remote vital sign detection. Then the preliminary feasibility evaluation of respiration detection has been presented and confirmed. And an advanced signal processing technique is required to enhance the detected vital sign, to maximize the detectability, and to anticipate various possible conditions, especially in the post-disaster environment. I think that's all I want to talk to you. Thank you very much for your attention, and let me know if you have any question. Thank you.
Thank you very, very much. It's very nice to see some research that can actually lead to some people's lives getting saved. So there is a question in the chat from Mr. Iman. Do you want to ask the question yourself, or should I just read it? Okay, I'm just gonna read the question then. What kind of communication interface or protocol used by SPC, the SDR, and LNA to avoid a data bottleneck? Thank you.
Okay, I answer now.
Yes, please.
Okay. Okay, thank you, Mr. Iman, for the question. So for now, we use the existing communication provided by the LAM from the SDR. So the SDR, we use LAM SDR mini, and this SDR provides serial communication. So now we use the serial communication, and as you know, the radar system, we use the continuous wave radar, that works based on the Doppler shift frequency. So the frequency is low. The frequency is very low, so it's no problem with the data rates for now. And for the LNA to the SDR, we also use the serial communication provided by the LNA. So almost all of the data we use the serial, but in the future, it is possible to use the higher data rates, for example, by use network or USB 3.0 that's maybe provided by the SDR, for example, by using the SRP or others. So that's my answer for the question.
Thank you very much. I have a question. So what processing platform do you use to process the data from the SDR? Is it just a desktop PC or using something smaller at this stage?
Oh, yes. Thank you for the question. So for now, we use the SBC, and it is very common product, Raspberry Pi, but now we also try to develop on the higher spec SBC like Jetson Nano and others. So it's depend on the purpose of the application of the drone radar system.
Okay, thank you very much. How far are you from actually implementing the system on actual UAV?
Yes. Now we are in the step of testing and evaluation in the laboratory environment. And this is the preliminary step. Actually, we have developed with the big drone with a very more complex system. And in this study, we try to minimize or make a simpler system so that it can be implemented in the multiple drone system scheme. So that's our purpose actually.
Okay, thank you very much. Thank you for all of the presenters that presented today and the participants that joined. Before the session is concluded, I want to ask that all of the presenters please switch on their cameras so that we can have a screen capture session. Okay, I'm going to count on the count of 3. Can the co-host please capture the screen capture? 1, 2, 3. Okay, thank you very much, everybody. Thanks for attending this session. Have a good day.
Thank you very much.
Good afternoon, everybody. Welcome back. Welcome to these sessions. This is the session 7, maybe the last session on this conference today on the track of remote sensing and radar system. We will have 4 presenters today, all of them from National Research and Innovation Agency, and the last from South Africa. And before we proceed to the first presenter, I just to remind you again that keep the video on for all presentation and the participation, because in the end of the session we will have a capture session. And I just to remind that presentation 15 minutes, including question and answer. And for all of you want to ask questions, just use raise hand functions, and maybe you can also use chat box as well. Next, we will start on the first presenter from Research Center and National Research and Innovation Agency, Mr. Hari Septanto. So you can start your presentation right now.
Good afternoon, ladies and gentlemen. My name is Hari Septanto from Research Center for Smart Mechatronics, Research Organization of Electronics and Informatics of BRIN. This work, entitled A Novel Rule for Designing 3-Stages Piecewise Linear NLFM chip, was prepared with my colleague Utama Sujana from Samsung Research Indonesia and Joko Supriyanto from Institut Teknologi Bandung. In radar system, the pulse compression principle mostly use the linear frequency modulation chip. Meanwhile, nonlinear frequency modulation (NLFM) has received extensive attention due to its properties to suppress the peak side lobe. Most of the NLFMs consider their instantaneous function as a smooth polynomial function. However, its basis function is a piecewise continuous function, and or also we call it the piecewise linear NLFM. So the piecewise linear NLFM can be viewed as a concatenation of several LFM stages with different chirp rates. And this work proposes the design rule for specific type of the piecewise linear NLFM, called 3 stages piecewise linear NLFM. This is in the right side. We can see this is the concatenation of the 3 stages of LFM. So an NLFM may have the property to suppress the peak side lobe. However, if we choose the parameters, this is the F, T1, T1. If we choose the parameters inappropriate, the side lobe of the NLFM will be increased instead of suppressed. So, the question is, what is the rule to find the parameters? This is the rule, but before I explain the rule, we see the left side. This is the formula of the 3 stages piecewise linear NLFM, and this is in form in a discrete time form. We can see that T is n time the sampling time, and the n is the number of samples. This is the rule. The rule is consists of the how to find the delta F and how to find the number of samples. You can see that this is the delta F. So delta F is 1/4 5 of the bandwidth, the F maximum, F the bandwidth, and this bandwidth per 5, and the P1 and P3, this is the number of sample of stage 1 and stage 3. And how this rule count? So the idea is, so we observe some existing good NLFMs. So we see that the good NLFM, they have the most the large portion in the middle, that most the almost or is the linear, the LFM LFM shape, and they has a small portion in the beginning and in the end. And so this is the rule. We give the portion in this rule 5 and 6. So we also did empirical trials using GNU Radio Octave, and then we carried out simulation for 4 jobs scenarios, 4 jobs specification. That's this specification based on the bandwidth and the pulse width of the job. And for each job specification, we simulate. We also carried out the simulation with 3 different numbers of sample. That is the oversampling. We call it oversampling. This is the highest number of samples. And 2 is also meet the Nyquist criteria, but close to the Nyquist criteria. And the 3rd is with the inadequately sampling frequency. And of course, it didn't meet the Nyquist criteria. We obtained this job specification from these references that we will show in the end of this slide. And this is we not show to you all the figures of the match filtering result, but this is the example of the scenario B. We simulate the one object detection in this case. So we can see that when we have the highest number sample, we can see clearly where is the object, and when we use the inadequate sampling, we can see there are grading loops here, and the maximum set loop level for all scenarios is about the minus 19 dB. So it is lower than the LFM, and we calculate the minus 19 dB is with the highest number of samples. So in this case, in this scenario, is the top figure. However, this minus 19 dB is actually not are not better than some existing reported NLMs. But for example, in SAIDI, it has the better peak side loop level. They use 65 stages piecewise linear NLFM job, whose parameters were obtained through a sophisticated optimization algorithm. And actually, in their paper, they didn't show the value of the parameters, and it is in contrast to our simplicity. We provide the simple rule, and we can calculate it quickly. And this is the next simulation result. So the large number of samples implies a smooth mesh filtering output. Yeah, you can see in the left side, in the left figure. This is a smooth, but in practically, a higher number of samples requires a higher sampling capability of an analog to digital converter device, and also need more memory. And however, even the inadequately sampling frequency shows degrading lobes, but if we compare degrading lobes shows in the LFM and NLFM. The NLFM ones shows the lower than the degrading lobe, lower than the LFMs. And besides we simulate one object detection, we also simulate two object detection. We can see also for two object detection, we can see that the big side lobe separation also occurs in this case. So this is the conclusion. We concluding that the rule for determining the three stages piecewise linear LFM tube has been presented, and all the match filtering outputs of the design LFM tube show the suppression of the side lobes. And based on that simulation, our proposed rule promises to be applied to other job specification. However, to prove it analytically, for this generalization, to prove it analytically, it will be challenging for further research. So this research is supported by Rumah Program Pengembangan Antariksa BRIN tahun 2022, and these are for references that we showed to you in the previous slide. Thank you very much.
Thank you for interesting presentation. So we come to the question and answer sessions. We have 2 minutes left. Maybe there is questions for participants. There is a questions. What is the difference between NLFM and exponential chirp? Thank you. You can answer right now.
Yeah. Thank you, Mr. Moderator. Thank you for the question, Pak Iman. So actually, exponential chirp is part of NLFM. So there is many kind of nonlinear frequency modulation. We identify the non-linearity is the curve of the instantaneous frequency. And when the curve of instantaneous frequency is exponential, it is also a nonlinear. So that's the answer.
Okay. There is also one question from Mr. Bambang Setiadi. Why 3 stages, not 5 or 7? Can we generalize the number of stages?
Okay. Thank you very much for the question. Yes. It is possible. Why 3, 5, or 7? The idea is the main reference that I challenge to make our research is better is a paper from a conference that they propose 3 stages. They propose 2 stages and 3 stages, and they only propose that two stages and 3 stages nonlinear is possible to suppress the side lobes, the maximum side lobe. But they in that paper they didn't define how what the rule to make it a suppression. So we find the rule, and our rule result in a better set of suppression that the main paper we refer. Yeah. And why not 5 and 7? Oh, it's also nice nice challenging, I think. Nice challenge for us to define the rule. Yeah.
Okay. Thank you very much. Due to the time limitation, so I will conclude for this presentation. Thank you very much. We will next move to the second presenter from Mr. Joko Widodo. Are you ready? I think so. The time is yours. You can start your presentation right now.
Thank you, Mr. Chairman. Good afternoon, ladies and gentlemen. My name is Joko Widodo from Research Center for Remote Sensing, National Research and Innovation Agency. Today, I would like to present my presentation with title Time Series Lens Subsidence Analysis based on persistent scatter interferometric synthetic aperture radar methods of Jakarta City regions using TerraSAR-X spacebound data. Let me to share my screen. Okay, and there are several of the background related to our research. First, lens subsidence is the main hazard, the stability of the lens surface in the Jakarta capital city. Second, lens subsidence can be caused by a combination of several factors such as the natural compaction of sediment or rocks, loading, excessive groundwater extraction, and tectonic activity. Third, the subsidence has stopped since the enactment of regulation on groundwater extraction. For land subsidence caused by human activities is 76.92%, and more than half, 59.75%, is caused by groundwater extraction. Objective of our research are first to determine to what extent the PSINSAR method with TerraSAR-X data can be used to observe the land subsidence in Jakarta. Second, to study the magnitude and distribution of existing land subsidence. And third, to study various aspects of the analysis regarding geology and its impact on infrastructure. This is the background related to the concept. Based on the data, we will employ the phase difference between many images, and then based on the difference of phase, we will calculate land subsidence in Jakarta City. This is the method and material. The method starting from determine area of interest. After that, we reading the images, and then we select of the common area, import of all of the SAR images, and then we do co-registration, and then we calculate, we generate reflectivity and amplitude stability index map, and then we select a ground control point and external dam of synthetic amplitudes INSAR coordinates. And then because of phase INSAR, we will process atmospheric phase, and then we will remove the noise. And then after that, we will do single permanent scattering processing. And then the last process, we will do geocodec and visualization. This is the image of the TerraSAR X satellite we use in this research. And then this is research location in Jakarta. And then here is information of the data used in this research. We use 29 data that already acquisition from October 2017 until June 2021. And then all of the data is in mode descending like this. Okay, this is the normal baseline of the data. Actually, we use data already recorded in 2019 March as a master, and then other data used as a slave of this processing. And then this is the data statistic which used in this processing. This is the result of the phase INSAR Jakarta. We generated 91,000 sparse point using TerraSAR data. Every point here has information about the land subsidence in Jakarta region. Okay, and here is the result of land subsidence in Pantai Indah Kapuk, Jakarta. This is the displacement of Jakarta is 98 millimeter or 9.8 centimeter, starting from 2017 until 2020 here. In the time series of the data based on phase INSAR processing. And then here land subsidence in Sunter, Jakarta. Here the land subsidence cumulative displacement is 43.4 millimeter. It means that land subsidence occur in here. Okay, here actually evidence of land subsidence in Jakarta. You can see here in Muara Angke, some land of Jakarta under the sea level around 2.4 meter here, and this is the top of the wall. Right now, actually, between sea level and the land, we have a barrier, but you can imagine is the wall destroyed, and then what happened here? It will be flooding happen here and dangerous for everybody. And then in here you can also see the evidence because of land subsidence. Actually, some crack happen here. This is effect of the land subsidence. This is other evidence also same, but actually this is in different area in northern part of Jakarta also. You can see here land subsidence already happen also here, and then this is also caused the damage of the building here. Some crack happen also in the wall like this, and this is in the floor. In the floor also there is some cracks. Okay, and this is other evidence actually. If we make a comparison between land subsidence and well monitoring, in here in Cengkareng look like that actually the condition is dynamic like this, and then actually displacement also occur follow the groundwater level condition here. We also try to analysis correlation between land subsidence data and cost data. Here we take data in Tanjung Priok actually. Then we try to compare the data. In here, Actually, we have the same trend between the result of the PS-insert method and also the result of the COTS data. Okay, this is overlay between land subsidence and geological map of Jakarta. Mostly subsidence in Jakarta occur in the northern part of Jakarta. This is maybe related to the geological conditions, sediment in here not yet in compact condition. So that way, and then the surface decrease and decrease. But in here, even though it's not in the northern part of Jakarta, but in here also in West Jakarta, land subsidence also occur. Actually, this is related to the groundwater extraction in Jakarta. Okay, based on our research, we have a conclusion. First, the time series analysis of the land subsidence of Jakarta has been achieved well by utilizing 29 scene of TerraSAR data. Second, from the analysis, it is concluded that land subsidence predominantly occur in both areas, North Jakarta and West Jakarta. And third, this land subsidence is presumable caused by geological factor, especially sedimentary compaction, and exacerbated by excessive groundwater extraction. Okay, that's all our presentation. Thank you.
Thank you for the interesting presentation. So I will open the question and answer sessions. Maybe the participant or speaker can raise your hand, or maybe you can ask directly to the presenter. Waiting for the questions, I have some questions because to you. First question is, is this method time series analysis just only appropriate for TerraSAR X spaceborne only, or can be applied to other spaceborne? The first, and the second is, how do you validate the crack on the building is caused by the land subsidence, not caused by other factors? Maybe you can answer about that.
Okay, thank you. Actually, time series processing by using permanent persistent scatter interferometric SAR is general method. We can use any data of SAR like TerraSAR X, and then LOS2 data, and then other data maybe Sentinel. We can use for analysis. And then related to the crack of the building, actually we also makes some interview with a participant with in the field to make sure that the crack of the building caused by land subsidence or not. So based on their information, and then we try to simulate what happened in the field.
I see. Thank you for the answering, and I'm waiting for other questions. Maybe in the from a chat box. I will check it later moment. There is no questions. Maybe one questions again. I just curious in your slide. There is a minus velocity and plus velocity millimeter per year. What is that mean? Plus velocity. Can you tell me more detail?
Okay. Minus velocity it means there is land subsidence occur in the area, and then plus velocity it means that there is uplift. So maybe because of sedimentation, something like this, and then we can detect based on this processing.
I see. Thank you. There is one question for Mr. Bambang Setiadi. FPS insert technique is sensitive to error and noise in radar image, which can affect the accuracy and reliability of the result. In your study, how to overcome these disadvantages?
Okay, we work based on amplitude stability index. Actually, we only choose the pixel that's very stable, more than 0.8 and 0.9. So that based on this step, we hope that the result will be okay and valid.
Okay, thank you. Because due to the time limitation, I think this further is finished. Thank you very much for your presentations. We will move to the third presenter. I will invite Mr. Apapat Hidayatullah to present their presentations on the title in private rainfall detection of rain radar using high precision circuit and speckle filtering. So, Mr. Papa, time is yours.
Hello everyone, my name is Bapak Hidayatullah. I am from Research Center for Smart Mechatronics, National Research and Innovation Agency, Indonesia. Today, I'd like to present our research entitled An Improved Rainfall Detection of Rain Radar Using High Precision Circuit and Speckle Filter. Let me first introduce the existing rain scanner. A rain scanner developed using an X-band marine radar has been operated and is able to observe rainfall up to 44 kilometers of range with 120 meters spatial resolution. The rain scanner extracts rain objects by applying the clutter map method to eliminate non-rainfall signal. However, the observation data revealed instability in the clutter removal products. One of the main factors contributing to the instability is the precision of the signal conversion before sampling. The existing circuit uses an optical sensor to convert the both signal level. The drawback is high rise and potent on the signal. Further impact of the low precision circuit is the increase of speckle. Speckle is an isolated range of bins with valid data surrounded by bins with no data. This is the illustration of speckle during clear sky conditions. In the weather radar data, speckle filtering is conducted after the clutter removal. For the solution, we propose a high-speed and precision circuit and a speckle filtering algorithm. As mentioned before, this research proposed two methods. The first method is high-precision level converter circuit. The radar signal consists of pulse signal and video signal. Heading, pairing, and trigger is pulse signal with 12 volts amplitude, while the video signal is reflected signal with varies amplitude around 0 to -9 volts. Furthermore, the characteristic of radar signal can be seen in table here. Its signal should be adjusted to meet the ADC input requirement, which is negative or positive 5 volts. The proposed circuit consists of a voltage divider and unity gain. The circuit utilizing a high-speed and low-noise operational amplifier. And this is the block diagram of the proposed circuit. Second method is speckle filtering. Speckles formed by unfit clutter removal process or by unwanted individual target echo should be filtered to obtain a more accurate radar image. The filtering is conducted by measuring the width of the target pixels. In this case, a target with 5 by 5 pixel width or less is regarded as non-precipitation target and should be removed. For example, as shown in this illustration, if pixel 5 is assumed as a rainfall, adjacent pixel 3 is considered part of the target. However, Since the pixel width is less than 5 by 5, the target is set as a non-precipitation and should be set to no data. This algorithm implemented in Python by using find counter function from OpenCV library. This algorithm has a weakness when the target pixels form a diagonal line larger than 5 pixels, which will be considered as a rainfall, even though this is rare occurrence. The measurement results on the rise and fall times of the radar pulse signal by the existing and the proposed circuit are shown in this table. Based on these results, the rise and fall time performed by a proposed circuit shows a significant improvement and closer to the input signal. Therefore, the proposed circuit has been proven to function as a high-precision radar pulse signal level converter. The result of the signal acquisition on the existing circuit are out of sync, as shown in this plot. The trigger signal of the existing circuit is slightly shifted because it has higher rise and fall times. This problem was successfully fixed in the proposed circuit. As shown in this plot, the trigger and PDO look more synchronous. The PDO signal appears right at the falling edge of the trigger signal. Besides that, the amplitude of the output signal acquisition of the proposed circuit has a higher values. This is because the output of the proposed circuit has a unity gain circuit that can work as isolation between the output and the ADC input, so that the voltage drop is smaller. The acquired radar reflectivity signal is then processed to produce a radar image. To examine the ground clutter detection of the existing and the proposed signal conditioning circuit, an observation test was carried out under clear sky condition. The comparison of ground clutter image produced by both the device can be seen in these pictures. It shows that the proposed high-precision circuit has better detection results. The clutter object is easy to distinguish. The rain signal is the result of the reduction between the reflectivity signal during rainy condition and clear sky condition. The result of this process delivers some speckle as shown in this image. Left image is the result of a radar image with an existing circuit, while right image uses the proposed circuit. From this image, it can be seen that the radar image with the proposed circuit typically has fewer speckles. To solve the speckles problems, the results of radar image processing still require image processing. This is done by applying the speckle filter algorithm. The comparison of radar image before and after the application of a speckle filter can be seen in these pictures. Top left picture is radar image in clear sky condition before applying a speckle filter, while the top right image is after applying speckle filter. It can be seen that the speckle filter made is able to remove speckle. However, there is still little speckle left. This is because the remaining speckle size is more than 5 by 5 pixels. Likewise, in rainy condition as shown in bottom pictures. This speckle filter doesn't affect the rain objects because typically the rain object has size of more than 5 by 5 pixels. To compare the rain detection results for each device, the experiment was conducted using 2 X-band radars in different locations with intersection coverage area as shown in these pictures. The blue dot is the location of the radar using the proposed circuit, while the red dot is the location of the radar with the existing circuit. The monitoring areas shown by the black circle, and this experiment was conducted at the same time. The rain detection using radar with a proposed circuit that use high precision circuit have higher reflectivity values. is up to 40 dBz, while on the radar with the optical sensor only has reflectivity up to 30 dBz. The proposed circuit also has a higher sensitivity indicated by the more significant amount of detected brain object with higher intensity. However, validation still needs to be done to improve the estimation of the radar detection results. Finally, we have some conclusions. In this research, a high-precision circuit and speckle filtering algorithm are proposed to improve the rainfall detection of rainfall scanner radar for Bandung City observation. The proposed high-speed and precision circuit consists of both dissipator and unity gain, utilizing a high-speed and low-noise operational amplifier. The measurement research revealed that the rise and fall types performed by the operational amplifier saw a significant improvement closer to the original radar signal. The result of rain detection using radar with high precision circuit has higher reflectivity up to 40 dBz. It has a higher sensitivity indicated by the more significant amount of detected rain with higher intensity. The filtering has been tested and successfully removed the speckle below 5 by 5 pixel width. And these are some differences of this work. So I think this is the end of my presentation, and thank you.
Thank you for your presentation. So we move to the question and answer. There are several questions. First of all, from Dr. Yuyu Wahyu, Mr. Yuyu Wahyu. The question is, if it is estimated which one will be more precise using speckle filtering compared to using dual polarization radar system, which better?
Thank you for the question. Since we have not do the comparison, but so the radar we use is general marine radar, and we don't have don't compare with another. So I don't. I think the president we must do some experiment for answer this question.
Okay. So in
thank you.
So you just only use one polarization, right? Vertical and horizontal polarization. In your radar.
Use for vertical polarization. If I was mistaken, so it's in general marine radar.
Okay, I see. Thank you. The second question is, what kind of filter is implemented for the circuit?
Oh, thank you. The filter in the circuit is used butterworth filter with silent K topology, since it commonly used as an anti-aliasing filter with 5 megahertz frequency cutoff. We choose this because it's easy to design and can be implemented with our system.
Okay, hope done for the answer. We have 2 minutes left. If there is more questions for the participant or other speakers. Just due to you, I think you have a model like ignore that if there is objects similar to the speckle, so you will remove the object. It is correct, and how do you maintain this object?
Oh, yeah, thank you. In this research, actually, this is initial. Maybe we just categorize pixel width 5 by 5 as non-rainfall, less than 5 by 5 as non-rainfall. So as simple as that. So this doesn't have any any artificial intelligence or something like that to categorize the signal. So maybe in further work we can develop this algorithm.
Okay, good luck for your future research. Thank you. Due to the time is up, so I will finish. Thank you very much for your presentations. So I will move to the last presenter today. The 4 presenters come from Mr. Franz Paul Petersen on the title on the importance of accuracy of the estimate of the radar positions for fully coherent jamming of a strip map SAR sensors. So the screen is yours. You can start your presentations right now.
Hello, I'm Franz Paul Petersen, and I'm currently with the Council for Scientific and Industrial Research in Pretoria, South Africa. And this is about the work that I've done with 2 of my colleagues, Johan Smit and Jacques Solhier, on the importance of the accuracy of the estimate of the radar position for fully coherent jamming of a strip map SAR sensor. So SAR has become more common in military scenarios. It is currently being used for different aspects of warfare, ranging from targeting to reconnaissance. This uprise in SAR has led to a need for electronic attack, more commonly known as jamming techniques. The most common way of jamming radars is noise jamming due to the ease of implementation. However, synthetic aperture radars do processing in 2 dimensions, namely downrange and cross-range. This means that SARs typically have very high total integration gain, making it robust against noise jamming, unless you have very powerful transmitters. False target jamming is another known technique, but unlike noise jamming, it is much more difficult to implement, especially against SAR. In something like a pulse Doppler radar, false target jamming can be implemented by simply repeating a slightly modified version of the received signal. In SAR, this is also needed, but in addition, the phase history of the sequence of SAR pulses also has to be correct. Otherwise, you will experience defocusing. We refer to this as fully coherent SAR jamming, meaning that it is coherent in both downrange and cross-range. Previous work looked at techniques of creating false targets in SAR and ways of handling large amounts of data due to the large false images. But up to now, these analyses assumed that the jammer had perfect knowledge of the position of the SAR sensor. It is perhaps a good time to mention that the perfect phase history of the sequence of jamming pulses can only be recreated if the jammer knows the exact position of the SAR sensor. In this work, the relationship between the accuracy with which a jammer knows the position of a SAR sensor and the coherent cross-range integration gain, which is basically a measure of how well the false target focuses in cross-range, was analyzed. In other words, the question of what happens if the jammer does not have perfect knowledge of the SAR sensor was answered. The effect of where the false target was created in relation to the jammer and SAR was also investigated. The approach was to do a numerical analysis of the jamming of a strip map SAR, where the jammer received the SAR signal and used it to create false target signal. This jamming signal represented a single false target point scatterer within an area under protection by the jammer. The jammer then used the position of the SAR sensor to calculate the required time delay to create a phase history that a real scatterer would have if it existed at the same position as that of the false target. This was translated into a sequence of phase errors which were used to calculate the coherent integration gain in cross-range. At this stage, there were no phase errors yet, and the integration gain was used as a reference for the case where the jammer has perfect knowledge of the position. This was followed by the addition of Gaussian errors in azimuth elevation and range estimation of the SAR sensor position by the jammer. The new cross-range integration gain was then calculated for this erroneous position estimate. The process was then followed for false targets at multiple positions within the defended area. Basically, an M by N grid or array of possible positions within the defended area was tested. The process was done for numerous values of azimuth, elevation, and range errors individually, as well as a combination of some. The most noteworthy was shown in this paper, and I will show that to you a little bit later. This figure illustrates the geometry of the scenario that was simulated. Here, T indicates the actual position of the SAR sensor, and E indicates the erroneous estimate of the position as made by the jammer. J is the position of the jammer, and F is the false target at a single position within the defended area. In this case, the SAR platform traveled along the y-axis from -1 to 1 kilometers and traveled perfectly straight and level. The red dashed line indicates the erroneous position that the jammer measured. Also note that for a single result plot, the integration gain for numerous positions of the false target was calculated. These parameters may be of interest. The PRF that was used was 1 kilohertz. The carrier frequency was chosen as 10 gigahertz, so X-band, and both the cross-range integration gain, both the cross-range and downrange resolutions were set to 5 meters. The altitude of the SAR platform was chosen as 3,048 meters, which is just 10,000 feet. And this is measured above ground level. The time that the SAR sensor received for was 30 seconds, which is relevant if you want to get an idea of the total number of SAR pulses. This is a flow diagram of the numerical analysis. The parameters were first set, and then for each SAR pulse that was received, an erroneous position of the SAR sensor was determined for that instance of the SAR platform along its flight path. This erroneous or estimated position was then used to calculate the time delay that was needed for that certain jammer pulse, and this time delay was converted to a phase delay. By knowing the true exact position of the SAR platform, the phase error was then determined, and finally, the phase errors of all pulses were used to calculate the coherent cross-range integration gain. And this was for a single false target at a single position. In these results, the coherent cross-range integration gain for position measurement errors in azimuth can be seen. This was done for a matrix of positions of the false target. As stated, the errors were introduced as Gaussian random variables, and each of these figures have a different standard deviation of measurement error. The figure on the left has a standard deviation of 0.35 millidegrees. Yes, you heard correct, millidegrees. It can be seen that as the error was increased, that the region that had integration gain decreased in cross range, but remained constant in downrange. These are the results for measurement errors in elevation. As the standard deviation of the Gaussian measurement errors in elevation was increased, the region where the false target would have integration gain decreased in downrange while remaining constant in cross range, which is the opposite of the case of the azimuth errors. These are the results for the different measurement errors in range. Firstly, note that the values are not as extremely stringent. Having a range measurement accuracy of 50 meters is much more realizable than angular measurement accuracies in the order of millidegrees. Secondly, the effect of the region where the false target would have integration gain reacts the same as for the azimuth error case, suggesting that the nature of the errors are similar. These results show the effect of having Gaussian measurement errors in azimuth, elevation, and in range. The individual effects of each type of measurement errors seem to combine to form results with a region in which a false target will have cross-range integration gain decreases in both cross-range and downrange. So effectively, the combined effect of azimuth and elevation errors. There's another noteworthy finding here. Considering that a jammer is at a position of 0 kilometers in cross-range and 50 kilometers in downrange, it can be seen that the region in which a false target will have cross-range integration gain remains pretty constant around the jammer position. And it is actually at a maximum value exactly at the same position as the jammer. This suggests that although very stringent accuracies are needed to protect an entire area, the required accuracies for self-protection jamming is much less stringent. And it would be useful if you can make your jammer look like a few trees on a SAR image in military scenarios. In conclusion, SAR was identified as a possible threat in military scenarios, and fully coherent SAR jamming was identified as a possible method of jamming SARs. However, fully coherent SAR jamming has very stringent requirements for the accuracy with which a jammer should know the position of a SAR sensor. And the effects of a jammer making measurement errors while determining the position of a SAR was analyzed in the study. This was done through a numerical analysis where the phase errors of a train of jamming pulses were determined and used to calculate a cross-range integration gain. It was shown that increasing the standard deviation of the azimuth and range errors led to a decrease in the region in which a false target would have a cross-range integration gain in cross-range, while doing the same with elevation errors led to the region decreasing in downrange. Finally, the combined effect showed that the area decreased in both cross-range and downrange when having both azimuth and elevation errors, and range errors as well. It also suggested that self-protection jamming might have less stringent accuracy requirements than standoff jamming. Thank you very much.
Thank you very much for interesting topic on the jamming. So I will open the questions for the participants. You can raise hand right now. You can use raise hand, or you can directly chat on the chat box. Waiting for the question for others. I just want to ask you some question, maybe for verification for you, that to order to get the fully coherent jamming that, as you cite before in your presentation, that the system need to accurately estimate the position of the SAR. So due to the SAR, as usually is the SAR platform itself is mounted on the flying platform that has a specific velocity. It is possible in the reality, in the real conditions, that the SAR jamming can predict accurately the SAR positions for this scenario.
Okay, so the whole idea of this paper was that the jammer will not be able to predict or measure the accuracy of a flying aircraft with a SAR sensor positioned on it. So you use the word estimate. So I'm not sure if you're referring to something like a satellite, which has an orbit that you can very accurately estimate the position of, because in that case, it will be at least possible to estimate the position with enough accuracy. But in terms of an aircraft with a SAR sensor on it, to be able to actually perform fully coherent SAR jamming, you will have to have accuracies in the order of a few millidegrees in azimuth and elevation measurements, which to my knowledge is not possible with the technology that we currently have, even if we have an active radar that is used to actually estimate or measure the position of the platform. And in any case, in a practical military scenario, you do not want to use an active radar, because if you have an active radar, you transmit and you make yourself visible, you expose yourself. So in reality, you would probably want to do some sort of direction finding without using active radar, and perhaps estimate a position using something like passive radar. But yeah, I'm not sure if that answers the question.
Okay, thank you for the answers. Maybe there is one question again, maybe. I think no more questions for this presentation, so I will thank you very much for your presentations. Before concluding these sessions, I just to inform you again, skip on the video. We have capture screen sessions, please, or participants and speaker to turn on your video. I will count down to start the capture sessions. 3, 2, and 1. That's, I think, is enough. So thank you very much for all presenters for very engagement and fruitful discussions for today's conference. So thank you. Before I conclude, thank you very much for the sessions. See you again for tomorrow conference. So see you again. Thank you very much for all.
Ladies and gentlemen, now we have reached the end of the day 1 of the 2022 International Conference on Radar, Antenna, Microwave, Electronics, and Telecommunications. Thank you for your participation during the first day of ICRAMET 2022. We would like to remind you tomorrow is the second and the last day of ICRAMET 2022. There will be 2 keynote talks, 2 patron sessions, and 5 paper presentation sessions, as well as the closing ceremony. Please join us again tomorrow at 8:20 GMT+7. See you all tomorrow. Thank you.
Halo Pak Teguh.
Today's world is a network of data and signals. The gap between vision and reality is closing. A thirst for knowledge and the search for new frontiers are the driving force behind innovation. We develop and produce top-quality, durable products that enable progress. Cultures and markets may differ, but people and technology